we are going to start from the basics of the organic chemistry. Since, you know, in your organic chemistry, lot of concepts from chemical bonding are involved, right? So I'll be covering those concepts, perfect, which are from the chapter chemical bonding. Perfect, I'll be covering those concepts first so that you'll be fit to attend this particular session, so that you'll be fit to cover the entire organic chemistry with us. Point number one. Right after this, we'll go to inductive effect and its applications, right? Then we'll be talking about the resonance, types of conjugation, cross and extended conjugation, steric inhibitance of resonance, resonance energy, okay, mesomeric effect and its applications. Then we shall be covering the topic aromaticity, and at the end of the session, we shall be covering the hyperconjugation and its applications as well. Now, a lot of students must be thinking, what about IUPAC nomenclature? What about IUPAC? My dear students, if I teach IUPAC also in this particular session, then it's going to exceed 14 hours for sure, right? And one YouTube stream can be there for maximum 12 hours. Perfect. So related to your IUPAC, tomorrow in the afternoon, you'll be getting one recording. I'll be providing one recording in the afternoon tomorrow, right? Tomorrow in the afternoon, I'll be providing you one recording in which you shall be covering your complete IUPAC as well. And that recording will be maximum for 2.5 hours. That is a 2.5 hour recording, which you will be getting tomorrow, right, on IUPAC. Perfect. Already? Isomerism does not include here. Isomerism needs another 10 to 12 hours, right? That's again a vast topic. Perfect. Isomerism, we'll do isomerism as well, but not in this particular session. That also needs some like 8 to 10 hours minimum. So let me know once in the chats if you all are ready with your pen and paper. Let me know in the chats quickly if you all are ready with your pen and paper. Let me know, people, quickly. If you all are ready with your pen and paper, everyone. Let me have some water first because the session is going to be long. Quickly. Guys, everything will be done. Relax. Everything will be done. Just remember and follow whatever I'm saying. That's more than sufficient for you. After attending today's session, and after attending tomorrow's 11 a.m. extra problem practice session as well, whatever module, whatever book you want to solve on GOC, you can do that. You can do that. And you'll be solving those questions like this. I'm telling you that. Yeah? Perfect, guys. Purification will be also done. I told you already, I'm not going to skip a single thing. Session duration, I have no idea. Okay? I'm starting the session. And let's see, till the chapter ends, I'll be here with you. And you are going to be with me too. Perfect, guys. So let's get going then. Let's get started. I hope you all are ready with your pen and paper. And please, whatever points I'll be noting on the screen, whatever points I'll be writing on the screen, I would want you all to take a note of every single point, because every single point is going to be equally important, my dear students. And at the same time, at the end of the session, I'll be providing you the handwritten PDF of this particular session also in my Telegram group. I'm pretty much sure you already are there in the Telegram group. Yeah? If not, then do join it right now. Okay? Perfect, guys. Perfect. Yes, JE students can also watch this session. No issues. You can watch this session. So people, let's get going then. So I'm starting this session from a term. That is charged species. This particular session, I'm starting from the term that is charged species. First of all, if you ask me, what is a charged species? What is a charged species? My dear students, any atom or group of atoms, any atom or group of atoms having charge on it. Any atom or group of atoms having charge on it. Having charge on it is something which you call as the charged species. Whenever you see an atom containing any type of charge, be it positive or negative, or whenever you see a group of atoms carrying any sort of charge, be it positive or negative, you'll be calling that as the charged species, right? So charged species is nothing. It is the atom or group of atoms. Atom or group of atoms having any sort of charge on it is something which you'll be calling as charged species, right? Now, my dear students, for the charged species, we define a term. For the charged species, we define a term. What is that term? That term is volume charge density. So the term which I'm going to define, volume charge density, VCD. First of all, this particular term we always define for a charged species, right? We always define for a charged species. And how exactly you guys define it? Volume charge density is nothing. It is the ratio of charge present on the species to that of size of the species. So this particular term VCD, volume charge density, it is defined only for the charged species, number one. And this VCD, it is nothing. It is the ratio of charge present on the species to that of size of the species. Right, people? Now, first of all, try to understand one simple thing which I'm going to tell you right now. Volume charge density, it is directly proportional to charge on species. It is inversely proportional to size of the species. Correct? Now, first of all, imagine I'm taking two species over here. For example, this is one species carrying positive charge. This is one more species which is bigger in size, containing the same amount of positive charge. So how many species have we taken over here? We have taken two species. One species carrying positive, another species carrying equal amount of positive as well. Right? So first of all, if I'm telling you that the charge present on both the species is same, the magnitude of charge on both the species is same, where the difference is lying? The difference lies in the size. The difference lies in the size. This particular species has got more size. If this species has got more size, that means its volume charge density will be less because VCD is inversely proportional to size, right? So more the size of the species, lesser is going to be the VCD, lesser is going to be the volume charge density, right? And over here, since these species are carrying the positive charge, so if I ask you which volume charge density you are defining for these species, you will say it is the positive volume charge density which I'm defining for these two species, right? So I would say positive volume charge density of this particular species will be less than that of positive volume charge density of this particular species. As simple as that. Similarly, my dear students, let's say this is one more species which carries the negative charge, right? I've got one more species which is bigger in size, carrying the same amount of negative charge. First of all, if I ask you, which volume charge density should I define for these two species? You'll exactly say it is the negative volume charge density which you are going to define for these two species. As simple as that. Now, my dear students, imagine that the magnitude of charge present here is same as that of magnitude of charge present here. Imagine the magnitude of charge on both the species is same. Where is the difference? The difference lies in the size. More the size, lesser is going to be the volume charge density. So among these two species, which particular species has lesser negative volume charge density? I would say this particular species, it will be having lesser volume charge density. So point number one. Volume charge density is defined for a charged species, first of all. For any charged species, we define the volume charge density, which is the ratio of the charge present on species divided by size of the species. This volume charge density is of how many types? It's of two types. Positive volume charge density, negative volume charge density. Positive volume charge density is defined for those species which carry positive charge. Negative volume charge density is defined for those species which carry the negative charge, right? And remember, from now onwards, more the charge on the species, more the volume charge density, right? Lesser the size of the species, more the volume charge density, be it positive or negative. I hope this is clear to everyone. Now, people, why am I giving you this term? this volume charge density? Because this volume charge density is related to stability. This volume charge density, it is related to stability. Let me tell you, please and please take a note of every single thing. Let me tell you, stability is inversely proportional to volume charge density. Stability is inversely proportional to volume charge density. What is meant by this particular point? How can we get different types of questions from this particular point? That is something which you will get to know in some time. First of all, remember it directly from now onwards. Stability of the charged species is inversely proportional to VCD. More the VCD, more the volume charge density, lesser is going to be the stability. Lesser the volume charge density, more is going to be the stability. Right? Perfect. Basically, what is the logic for it? Why they are inversely related? My dear students, it's pretty much simple. If volume charge density on the species is more, that means its potential energy is more. And if potential energy is more, stability automatically will be less. Right? As simple as that. More positive, more volume charge density means more potential energy. And more potential energy means less stability. That's it. So, just remember this particular statement from now onwards. Stability is inversely proportional to volume charge density. Now, where do I utilize these terms? Before utilizing these terms, before showing you the application of these terms over here, there are few more things which you need to know first of all, right? And what are those things? Have a look. I believe every one of you would have come across the term electronegativity, right? I believe every one of you would have come across the term electronegativity. How do you exactly define the term electronegativity? My dear students, look at the definition. The tendency of an element to attract the bonded pair of electron towards itself. The tendency of an element to attract the bonded pair of electron towards itself. That defines what? That defines electronegativity of an element. For example, my dear students, have a look. Let's say there's a covalent bond between A and B. Perfect. I'm assuming that the electronegativity of B is greater than that of electronegativity of A. This is something which I'm assuming. Let's say there is a covalent bond between A and B, and I'm assuming electronegativity of B is more than that of A. Now, what does this term mean? What does it mean that electronegativity of B is more? It simply tells you that B has got more tendency. B has got more tendency to attract this bonded pair of electron towards itself. Right? Now, you tell me, if B has got more tendency to attract the bonded pair towards itself, will the electron density towards B increase or decrease? Electron density towards B will increase, and that increase in the electron density towards B is represented by delta negative, and here you'll be writing delta positive. As simple as that, right? As simple as that. Perfect. My dear students, one more thing. Just tell me one thing. In your periodic table, which element is considered to be maximum electronegative? It is fluorine. Remember this. Followed by oxygen, followed by nitrogen. I believe all of you would be knowing this particular thing, right? In your periodic table, fluorine is the most electronegative element, followed by oxygen, followed by nitrogen. Point number one. Point number two. In your periodic table, if you move from left to right, what happens to electronegativity generally? If you ask me, I'll tell you one simple thing. I'll tell you electronegativity, it's inversely proportional to size. Electronegativity, it's inversely proportional to size. Now, as you move from left to right, generally size decreases. If size decreases, that means electronegativity will automatically increase. So remember one simple thing from now onwards. When you move from left to right, electronegativity, it increases. It increases generally, right? Similarly, my dear students, you tell me, when you move from top to the bottom, in the periodic table, what happens to size? Size increases generally. If size increases, electronegativity decreases. Perfect. This is one simple thing which I want all of you to remember from now on, right? Right, people? Perfect. One basic thing which I told you, which I would want all of you to remember from now onwards. right? And my dear students, remember this particular statement as well. Electronegativity, it's inversely proportional to size, because I'll be using this particular statement many a times. I'll be using this particular statement many a times. Now, people, there are few more things which we can conclude from the term electronegativity. There is a lot of other information which we can conclude from the term electronegativity. And what is that information? Try to understand. Try to understand what kind of other information you get from the term electronegativity. I've mentioned over here few points. Just remember them from now onwards. The tendency of an element to hold its valence electrons. Electronegativity gives you the idea about the tendency of an element. Electronegativity gives you the idea about the tendency of an element to hold its valence electrons. My dear students, that element which is more electronegative in nature, that will be having more tendency to hold its valence electrons. For example, let's say I've got carbon and fluorine. Which one is more electronegative? Fluorine is more electronegative. If fluorine is more electronegative, that means fluorine will be having more tendency to hold its valence electrons. So electronegativity gives you the idea about the tendency of an element to hold its valence electrons. More electronegative element can better hold its valence electrons. As simple as that. Right? So fluorine has got more tendency to hold its valence electrons. Point number one. Point number two. Electronegativity gives us the idea about the negative charge holding capacity of an element. Electronegativity, it gives the idea about the negative charge holding capacity of an element. What does it mean? It's pretty much simple. More electronegative element, it can hold negative charge. More electronegative element can sustain negative charge. It can hold negative charge. For example, let's say you have got oxygen carrying negative charge. Let's say you have got carbon carrying negative charge. You have got oxygen carrying negative charge. You have got carbon carrying negative charge. Just tell me one thing in the charts. Which one is more electronegative? Oxygen. If oxygen is more electronegative, that means oxygen can hold this negative charge in a better way than that of carbon. It means that oxygen can hold this negative charge in a better way than that of carbon. Right? So in short, one simple thing which you have to remember from now onwards. What is that simple thing? Electronegativity, it gives us the idea about the negative charge holding capacity of an element. More electronegative element means more will be its tendency to hold the negative charge. Right? More will be its tendency to hold the negative charge. As simple as that. Do remember this particular statement as well. So I would say the negative charge holding capacity of oxygen will be more than that of negative charge holding capacity of carbon. Now, if I ask you one simple thing over here, where do you think is the negative charge more stable? Let's talk in terms of stability. Where do you think is the negative charge more stable? The one which can hold this negative charge? The one which can hold this negative charge properly, I would say there only this negative charge will be stable. You tell me in the charts, where do you think negative charge is more stable? Absolutely, it's going to be oxygen. Right? Absolutely, it's going to be oxygen. Negative charge on oxygen will be more stable than that of negative charge on carbon. And my dear students, remember one important thing, because this thing which I'm going to write over here, I'll be using it many a times from now onwards. What is that? Do remember the negative charge holding capacity. Take a note of it. The negative charge holding capacity of oxygen. The negative charge holding capacity of oxygen is greater than the negative charge holding capacity of 10 carbon atoms. 10 carbon atoms. Now, from this particular statement, you can get the idea of how stable this negative charge on oxygen will be. Right? Take a note of this statement. the negative charge holding capacity of oxygen is greater than the negative charge holding capacity of 10 carbon atoms. Now you can get the idea of how much this negative charge is stable on oxygen, right? This is one very important point. I'll be using it frequently here. Perfect. Now guys, this is something which I've already discussed. Electronegativity of an element, it is inversely proportional to size, right? It is inversely proportional to size. At the same time, there are a few more logics which you need to remember. Have a look. My dear students, when you talk about the orbitals, you have got s orbital, right? You have got p orbital, you have got d orbital, you have got f orbital, right? Now, if I ask you which orbital is closer towards the nucleus, you will say s orbital is closer towards the nucleus. S orbital is closer towards the nucleus, right? Now you understand it like this. For example, if the electron is present in this s orbital, for example. Similarly, there is one more electron present in p, one more electron present in d, one more electron present in f. Can you let me know which electron will be experiencing maximum attraction? Which electron will be experiencing maximum attraction? I'll say that electron which will be closer towards the nucleus, that will be experiencing maximum attraction. Now, my dear students, can you relate this attraction with electronegativity? Can you relate this attraction with electronegativity? You should be able to relate this attraction with electronegativity, right? Tell me. I'm writing a statement. Electronegativity of orbitals is also defined. Which orbital has got more electronegativity? Tell me that. Tell me that in the chats. S followed by P followed by D followed by F. I'm relating attraction with electronegativity, right? Perfect, people? Perfect? Remember this particular point as well. Now. There are a few more basic things which I want to share with you. Try to understand something important. My dear students, in the entire organic chemistry, there is one element which is pretty much common. That is carbon. There is one element which is pretty much common. Which element is that? That is carbon, right? Can you let me know what kind of hybridization carbon shows? I'll say carbon shows spi hybridization. Carbon always shows spi hybridization. Carbon always shows spi hybridization, where I value can be either 1, it can be 2, or it can be 3, right? What does that mean? That means if you particularly talk about carbon, how many different types of hybridizations carbon can show? Carbon can show 3 types of hybridization. Carbon can show 3 types of hybridization, right? First one is going to be sp, then it's going to be sp2, then it's going to be sp3. Carbon can show exactly 3 types of hybridizations, right? sp hybridization, it can show sp2 hybridization. Carbon can even show sp3 hybridization, right? Now, my dear students, you tell me one thing. I hope in your earlier classes you would have at least studied hybridization term once. What happens in hybridization basically? Hybridization, which is a complete theoretical concept, which does not have any experimental background. Hybridization, it is a complete theoretical concept. It does not have any experimental background. One important point. Number two, try to understand what exactly I'm going to say. Hybridization, if I talk about hybridization, what is hybridization all about? If you remember, in hybridization, intermixing of atomic orbitals takes place. Intermixing of atomic orbitals of an atom takes place, right? Which leads to the formation of hybrid orbitals. And you should be knowing number of atomic orbitals participating in the intermixing is equal to the number of hybrid orbitals formed. Number of atomic orbitals participating in the intermixing is always equal to the number of hybrid orbitals formed. For example, I'm talking about carbon. What is the outermost configuration of carbon? It is 2s2 and 2p2, correct? So this is your 2s orbital. These are your 3p orbitals, right? Perfect. This is your s. This is your p. This is p. This is p. One is px, py, pz. Now, my dear students, if I would say it like this, if the s orbital of the carbon and p orbital of the carbon. I'm assuming that these two orbitals are participating in the intermixing. If these two orbitals participate in the intermixing, that means if two orbitals are participating, I'll be getting two hybrid orbitals. Number of atomic orbitals intermixed is equal to the number of hybrid orbitals formed. And this particular hybrid orbital I'll be calling as sp hybrid orbital. This particular hybrid orbital I'll be calling as sp hybrid orbital. Correct? Similarly, imagine that, let's say this s and 2p, this s and these 2p orbitals have participated in the intermixing. So 3 atomic orbitals, if participating in the intermixing, it will lead to the formation of 3 hybrid orbitals like this, right? And each hybrid orbital you'll be calling as sp2 hybrid orbital, right? Similarly, if all these 4 atomic orbitals will participate in the intermixing, it leads to the formation of 4 hybrid orbitals, and I'll be calling each hybrid orbital here as sp3 hybrid orbital, correct? Something which you all must be knowing. So carbon shows how many types of hybridization? sp, sp2 or sp3. Perfect. Now people, one thing. In case of sp hybridization, how many hybrid orbitals do we get? We get 2 hybrid orbitals. This is your first hybrid orbital. And similarly, my dear students, I can say this is your second hybrid orbital. Perfect. These are your 2 sp hybrid orbitals. This is sp, even this is sp hybrid orbital. Perfect. Okay, if I ask you, these hybrid orbitals, if you remember, they are placed in such a way that there should be minimum repulsions between them, right? So that means they are placed at an angle of what? Right here, they are placed at an angle of 180 degree. Perfect. sp2 hybridization. How many hybrid orbitals do we get here? We get 3 hybrid orbitals. This is your first hybrid orbital. This is your second hybrid orbital, right? This is your third hybrid orbital, and they are placed in such a way that there are minimum repulsions between them. So at what angle they'll be? They'll be placed at an angle of 120 degree. Perfect. Similarly, if I talk about sp3 hybridization, in case of sp3 hybridization, how many hybrid orbitals do we get? We get 4 hybrid orbitals. And they are placed in such a way that there should be minimum repulsions and maximum stability between them. Perfect. And they are placed at an angle of what? 109 degree, 28 minutes. I believe this is something which you all already know. Perfect. If not, then remember it from now onwards. Now guys, tell me one thing. See, if I ask you how this sp hybrid orbital was made, basically when one of the s orbital and one of the p orbital of carbon, when they intermixed, they resulted in the formation of 2 hybrid orbitals, sp. So can you let me know, will there be any s character present in this hybrid orbital? Absolutely, there will be some s character present in sp hybrid orbital as well. How do you get the percentage of s character in any hybrid orbital? It's pretty much simple. Try to understand. In your sp hybrid orbital, which is formed when s and p intermixed, so there is some s character here in this hybrid orbital. There is some p character as well. How do you get the percentage of s character? Tell me how many s orbitals participated. One s orbital participated, divided by how many total orbitals participated? 2 total orbitals participated in the intermixing, multiplied by 100. The value comes out to be 50%. What is meant by this 50%? It means this particular hybrid orbital, it contains 50% of s character. What about this hybrid orbital? If I ask you about the percentage of s character in sp2 hybrid orbital, so one s orbital participated and in total 3 orbitals participated, multiplied by 100. The value comes out to be 33%. So I would say in this sp2 hybrid orbital, there will be 33% of s character. Similarly, what is going to be the s character here in sp3 hybrid orbital? It's going to be 25%. Now people, you tell me one thing. sp, sp2, sp3. sp bond angle is 180. Here it's 120. Here it is 109. As you move from left to right here, is the bond angle decreasing or increasing? 180, 120, 109. On moving from left to right, is the bond angle increasing or decreasing? Bond angle is decreasing. On moving from left to right, bond angle is decreasing. At the same time, what is happening to the percentage of s character? 50, 33, 25. On moving from left to right, percentage of S character is also decreasing. When you move from left to right here, bond angle is decreasing as well as percentage of S character is decreasing. So can I say bond angle is directly proportional to percentage of S character? Bond angle is directly proportional to percentage of S character, right? Percentage of S character. Is it clear? Did you get the idea of this particular thing? Did you get the idea of this particular statement? Quickly, let me know in the chats, everyone. So I would say more the bond angle, more the S character. And if you remember, S character is related to electronegativity. If you remember, S character is related to electronegativity. S character is related to electronegativity like this. More the S character, more the electronegativity. More the S character, more the electronegativity. So from this particular slide, what you have to remember? You have to remember something like this. Bond angle, it is directly proportional to percentage of S character, right? Percentage of S character, but it is directly proportional to electronegativity, right? So my dear students, this is the conclusion of the entire thing which I was teaching you till now. I hope this is clear to everyone. I hope this is clear to everyone. I hope this is clear to everyone. Yes? Quickly, let me know in the chats with some fire emojis if you got this particular concept, because this is important. This is important. Quickly, people. Quickly, everyone. Everyone in the chats. This is something which is important. I'll be utilizing this concept everywhere. Yeah, in the chats, everyone. I want the chats to go up continuously. Done and dusted? Done and dusted? Perfect, guys. If this is done and dusted, if this is done and dusted, then let me tell you one more thing. Let me tell you one more thing. Can I write a simple statement like this? Can I say electronegativity of hybrid orbitals is also defined? You are going to answer this question. Electronegativity of hybrid orbitals is also defined. If I have sp hybrid orbital, if I have got sp2 hybrid orbital, if I have got sp3 hybrid orbital, can you tell me which hybrid orbital has got more S character? It is sp. S character is directly proportional to electronegativity. So can I say electronegativity of sp hybrid orbital will be greater than that of electronegativity of sp2, which will be greater than that of electronegativity of sp3. So guys, do remember this particular statement as well. Electronegativity of sp hybrid orbital will be more than that of sp2, than that of what? Than that of sp3, because of the percentage of S character. Yes? Is it clear? Is it clear? In the chats quickly. In the chats quickly. In the chats quickly. In the chats quickly. Everyone. So I believe whatever statements are mentioned here, I believe these statements will be absolutely clear to you. Number one, electronegativity is directly proportional to percentage of S character. Electronegativity of sp hybrid orbital is greater than that of sp2, is greater than that of sp3. You know the logic, you know the reason. Point number three. Point number three. This is just one example which is going to clear you one simple thing. See guys, let me make the molecule again like this. This is H, this is C, then you have got triple bonded carbon, right? Then you have got CH and double bond CH2. Double bond CH2. Now people, tell me just one simple thing. Tell me about this particular carbon. How many sigma bonds it's forming? How many sigma bonds it's forming? It's forming 1 and 2. It's forming 2 sigma bonds. It's forming 2 sigma bonds. It's forming 2 sigma bonds. Try to understand one more thing. I hope you know the term called as steric number. I hope you know the term called as steric number. What is steric number? Steric number means sigma plus lone pair. Sigma plus lone pair. If the steric number comes out to be 2, the hybridization is sp. If it is 3, the hybridization is sp2. If it is 4, the hybridization is sp3. Okay. Now, if I talk about this particular carbon, how many valence electrons carbon has? How many valence electrons carbon has? 4. 4 valence electrons. How many sigma bonds it's forming? It's forming 2 sigma bonds. It's forming 2 sigma bonds. Carbon has 4 valence electrons. And how many sigma bonds it's forming? It's forming 2 sigma bonds. Now tell me, how many total bonds this carbon is forming? 1, 2, 3, 4. Carbon is forming 4 bonds, right? And in order to form 4 bonds, can I say carbon would have utilized all its 4 valence electrons? Absolutely, carbon would have utilized all its 4 electrons or its 4 valence electrons. Carbon had 4 valence electrons and it has utilized all those 4 valence electrons for the bonding. So how many lone pairs this carbon will be having? It will be having 0 lone pair. If I ask you steric number of this carbon, sigma plus lone pair, 2 plus 0, that is 2. If steric number is 2, that means hybridization is sp. So this particular carbon has got the sp hybridization here, right? Yes. Right, people? In the similar way, look at this particular carbon. Look at this particular carbon. How many sigma it's forming? 1 and 2. So again, I'll say this carbon is sp hybridized. How many sigma this is forming? 1 sigma, 2 sigma, and 1 more with hydrogen, right? So 3 sigma it's forming, so it's sp2. This particular carbon, how many sigma it's forming? 1 and 2 with hydrogen. So this again sp2, right? So I believe from the structure you can easily let me know. You can easily let me know the hybridization of different atoms. Yes, hybridization of different atoms. I believe this is clear. Just tell me one thing. Just tell me one thing. Do you know how to calculate lone pairs? Do you know how to calculate lone pairs? Just tell me that, yes or no? Yes or no? Do you know how to calculate lone pairs? Quickly, guys, everyone in the chats. What do you think? Yes or no? Honestly, there is no need to be shy or something. I'm here to teach you everything. That's why I told I'll be starting exactly from basics. One example I'll take by means of which you'll understand how to calculate the lone pairs. Okay? One example I'll take. One example I'll take. Then I'll come to this particular case which I have drawn over here. I'm keeping this case on hold. One simple example I'll take which will make you clear every single thing. See, for example, if you have got the molecule XCF4, if I particularly talk about xenon, xenon is a noble gas, right? If it's a noble gas, right? In its outermost shell, how many electrons will be there? 8 valence electrons. So xenon has got 8 valence electrons. Correct? Tell me how many surrounding atoms it has? It has 4 surrounding atoms. The number of surrounding atoms is equal to the number of sigma bonds. The number of surrounding atoms is equal to the number of sigma bonds. Now you tell me, xenon had 8 valence electrons and it's forming how many bonds? 4 bonds. So out of 8 valence electrons, can I say xenon has utilized 4 of its valence electrons to form 4 bonds? Out of 8 valence electrons, xenon has utilized 4 of its valence electrons to form 4 bonds. So how many valence electrons will be still there? There'll be 4 valence electrons left on xenon as such in its outermost shell. So these valence electrons, they have not participated in the bonding. And you'll be calling these as the lone pairs. So xenon has how many lone pairs? Xenon has 2 lone pairs. 4 electrons means 2 lone pairs. Simple. Right? For example, take the case of water, H2O. Take the case of water. If I talk about oxygen, it's a group 16 element. How many valence electrons oxygen has? How many valence electrons oxygen has? 6. There are 6 valence electrons with oxygen. How many surrounding atoms are there? 2 surrounding atoms. The number of surrounding atoms is equal to number of sigma bonds, right? So out of 6 valence electrons, it has used 2 valence electrons to form 2 sigma bonds. So how many electrons will be left on oxygen as such? I'll say 4. 4 electrons means how many lone pairs? I'll say 2 lone pairs. This is 1 lone pair. This is 1 more lone pair. Correct? Simple and basic. Simple and basic. For example, you have got NH4 positive. This is the last example which I'm showing here. NH4 positive. Look at this nitrogen. How many valence electron it has? 5. But there's a positive charge. If there's a positive, subtract this positive. So the value comes out to be 4. How many surrounding atoms are there? 4 surrounding atoms. The number of surrounding atoms is equal to the number of sigma. It had 4 valence electrons and it has used all these 4 valence electrons to form 4 bonds. So how many lone pairs will be there? No. There'll be no lone pair on nitrogen. Perfect. And I believe if you got to know how to calculate sigma, how to calculate lone pairs, you can calculate the steric number, which is sigma plus lone pair, sigma plus lone pair, sigma plus lone pair. And once you get the steric number, you can easily talk about the hybridization. If the steric number is 5, hybridization is sp3d. If the steric number is 6, hybridization is sp3d2. Right? And so on. Perfect. I believe this basic thing is clear. Right? Now people try to understand one thing. I gave you one particular molecule over here. If you look at this particular carbon, it is sp hybridized. This particular carbon is sp2 hybridized. Let me just show you these two carbon atoms which I'm going to take into consideration. These are the two carbon atoms which I've taken into consideration. One is sp, one is sp2. If this is sp hybridized, can I say its s character will be more? If it is s character is more, that means its electronegativity will be more. If its electronegativity is more, that means it has got more tendency to attract the bonded pair towards itself. So this particular bonded pair will be attracted towards this carbon, due to which it gets delta negative, and this particular carbon gets delta positive. Right? Right, people? So what happened? Due to the difference in hybridization, can I say a partial polar character got developed here? Right? Can I say due to the difference in hybridization, a polar character got generated over here? That is the point which I have mentioned over here. The molecule can become partially polar. The molecule can become partially polar. Because of what? Because of the difference in the hybridization. Is this statement clear? Is this statement clear? Is this statement clear? People say yes or no in the chats. Everyone. Everyone. Someone is saying, sir, you are looking so sad today. Why would I look so sad? I'm happy with the work which I do. Yeah. That's the reason why you guys are here. Quickly, people. Is it clear? I think this particular slide will be absolutely clear to you. Electronegativity is directly proportional to S character. S character is directly proportional to bond angle. Remember that. sp hybrid orbital, its electronegativity is more than that of sp2, than that of sp3. One more point. Number 3. Due to the difference in hybridization, a partial polar character gets developed in a molecule. Yeah? I believe this is clear. Now, guys, now comes one more important thing. Have you heard about something called as angle strain? These are some points, guys. These are some points which we are frequently going to use. Try to understand. There's a term which I mentioned over here. Angle strain in cyclic compounds. What is meant by it and why do I need it? Try to understand. If you look at this particular carbon, right, there'll be some 2 hydrogens which will be associated with it. Perfect. Right? Carbon has to form 4 bonds. 1, 2, 3, 4. Perfect. If I ask you what is the hybridization of this carbon, you'll directly say it's sp3 hybridized. 4 sigma bonds, no lone pair. That means steric number 4, sp3. This sp3 hybridized. If this carbon is sp3 hybridized, so what is the expected bond angle here? Expected bond angle is 109 degree 28 minutes. This expected bond angle. But my dear students, if I ask you, look at the angle between these 2 bonds. Is it exactly 109.28? You'll say no, it is just 60. If I talk about the actual bond angle, actual bond angle here is 60. Look at this particular molecule. Look at the other molecule. Look at this particular carbon. It's forming. These are 2 hydrogens associated with it. Now, what about its hybridization? It's again sp3. Perfect. What is the expected bond angle? Expected bond angle is 109 degree 28. But what is the expected bond angle here? What is the actual bond angle here? Actual bond angle is 90. Right? Actual bond angle is 90. Now, my dear students, try to understand one simple thing and remember it from now onwards. Whenever in a molecule, the actual bond angle is not equal to the expected bond angle. Whenever in a molecule, the actual bond angle is not equal to the expected bond angle, we say that molecule is under angular strain. So this particular molecule is under strain. Can I say even this particular molecule is under strain? Absolutely, this particular molecule is under strain as well. This particular molecule will be also under strain. This particular molecule will be also under strain. So can I say all these molecules here, they are under strain? Absolutely, they are under strain. Now, what is the consequence of this strain? What is the consequence of this strain? Try to understand. What is the consequence of this strain? What will happen due to this strain? That is important. Have a look. I'm going to make the first molecule over here. I'm going to make the first molecule over here again. Perfect. This is your molecule which I took in the beginning, right? And these are the two hydrogen atoms. These are the two hydrogen atoms. Now, my dear students, if I ask you, this angle should be how much? I'm using the term should be. This angle should have been 109. This angle should have been 109. So this particular angle, it should have been 109. It should have been 109. But how much it is? It is less than that. If this angle has decreased, what about the outer angle? Can I say outer angle would have increased? This angle, it should have been 109, but it's 60. So this angle has decreased. So outer angle would have increased. Yes. So if outer angle has increased, before that, let me tell you, these bonds over here, these are called as exocyclic bonds. These are called as exocyclic bonds. And these particular bonds, these are called as endocyclic bonds. These are called as endocyclic bonds. Now you tell me, this particular bond angle should have been 109, but it's 60, it's less than that. That means the outer bond angle would have increased. And more the bond angle, more the electronegativity. More the bond angle, more the electronegativity, right? More the bond angle, more the electronegativity. So my dear students, just compare one thing. Just compare one thing. Tell me about this particular carbon and this particular carbon. Tell me, which particular molecule among these two is under more strain? Here the difference is more. Here the difference is comparatively less. So this molecule is under more strain. If this is under more strain, so can I say this particular bond angle here will be more as compared to this particular bond angle? Bond angle is directly proportional to electronegativity. So if I ask you, what about the electronegativity of this particular carbon, 1 and 2? Can you tell me which carbon will be more electronegative among these two? Is it going to be 1 or 2? Which carbon, 1 or 2? Which one will be more electronegative? You tell me that only. Which carbon will be more electronegative? Quickly in the charts. Absolutely, this carbon will be more electronegative than this, than this, than this. Is it clear? So in short, what is the conclusion here? What is the conclusion here? Conclusion is very much simple. More the angle strain, more the electronegativity. More the angle strain, more the electronegativity. I believe this particular statement is clear. More the angle strain, more the electronegativity. So I can write a simple statement. Do remember this? Electronegativity is directly proportional to what? It is directly proportional to angle strain. More the angle strain, more is going to be the electronegativity. I believe this particular point is also clear to you. Yes? Right, people? Is it clear? Okay, if it is clear, over here I've taken two rings. This is a 3-membered ring, this is a 4-membered ring, and I've joined them. Right? My dear students, if you look at this particular carbon, which I'm calling as carbon 1, for example, I'm calling this carbon as carbon 2, for example. Okay? Now, among these two rings, can you let me know which ring is under more strain? 3-membered ring. It is under more strain than that of 4-membered ring. 4-membered ring is under more strain than that of 5-membered, than that of 6-membered. So can I say this particular ring is under more angular strain? If this ring is under more angular strain, more the strain, more the electronegativity. So can I say electronegativity of this particular carbon? Electronegativity of this particular carbon will be more than that of this. Okay. If electronegativity of this carbon is more, so it has got more tendency to attract the bonded pair towards itself. So I'll say if it has got more tendency to attract the bonded pair towards itself, that is the reason why this carbon will get delta negative, this carbon will get delta positive. Agreed? Now tell me one thing. Can I say due to the difference in the angular strains, again partial polar character got developed in the molecule? Yes. Can I say due to the difference in the angular strains, again I would say partial polar character got developed in this molecule. So do remember one thing, due to the difference in the angular strains, partial polar character can get developed in the molecule. Yes or no in the chats, everyone? Yes or no in the chats, everyone? Yes or no in the chats, everyone? Quickly. Yes or no, everyone in the chats, quickly. Everyone in the chats. Guys, this is complete basics which I'm teaching you. And you have to remember each and every point. Agreed? Perfect. Wonderful. Wonderful, guys. Now, your screen will be blinking a bit because electricity is over. So maybe we might have to shift to dark mode soon. And I hope every one of you is fine with that. Yeah, we might have to shift to the dark mode soon. And the people who watch my sessions regularly, they would know exactly what this dark mode is. All right. So people, the things, the basics which I was teaching you till now, where do we use this basics? 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 Before utilizing all these concepts in the questions, there is one more thing which I would want to share with you. My dear students, there is a term called as stability of the charges. There is a term called as stability of the charge. For example, let's say we have got the carbon carrying negative charge, we have got nitrogen carrying negative charge. Carbon carrying negative, nitrogen carrying negative. Tell me one thing, whether these elements, whether they belong to same period or same group, what do you think? Carbon, nitrogen, they belong to same period. They belong to same period. My dear students, whenever you have to compare the stability of the charges, whenever you have to compare stability of the charges on the elements which belong to same period, you will be giving your answer as per electronegativity. You will be giving your answer as per electronegativity. And as per electronegativity is concerned, negative charge is more stable on more electronegative element. Negative charge is more stable on more electronegative element, right? Whenever you have to compare the stability of the charges on the elements which belong to same period, at that time, electronegativity plays a role. Negative charge is more stable on more electronegative element. Similarly, opposite of this, positive charge will be more stable on less electronegative element, less electronegative element, less electronegative element. Now, look at the case. For example, carbon carrying negative, nitrogen carrying negative, oxygen carrying negative. These elements, they belong to same period. And whenever you have to compare the stability of the charges on the elements which belong to same period, which concept? Electronegativity. And negative charge is more stable on more electronegative, right? Which one is more electronegative? Oxygen. So negative charge will be maximum stable here, followed by this, correct? This is the stability order of the negative charges. For example, you have got carbon carrying positive, nitrogen carrying positive, oxygen carrying positive. Again, have a look. These elements, they belong to same period. In the period, we prioritize electronegativity. And you know, positive charge is more stable on less electronegative element. Positive charge is more stable on less electronegative. So which one is less electronegative among these? Carbon. So positive charge will be more stable here, followed by this, This is the stability order. Right? Let me know if this particular slide is clear. Whenever you have to compare the stability of the charges on the elements which belong to same period, you will be talking in terms of electronegativity. Negative charge is more stable on more electronegative. Positive charge is more stable on less electronegative. As simple as that. Clear? Point number one. My dear students, since I told you positive charge is more stable on less electronegative. Now the question is, can positive charge be more stable on less electronegative anytime? Can positive charge be more stable on less electronegative anytime? See, I think I'm telling you the reverse way. Since we know positive charge is more stable on less electronegative. Now the point is, can positive charge become more stable on more electronegative? Is there any case like that as well? Yes. Yes. My dear students, try to understand. This is the carbon carrying positive. This is the oxygen carrying positive. Carbon carrying positive, oxygen carrying positive. Carbon and oxygen, do they belong to same period or same group? They belong to same period, right? And in the period, we'll look after electronegativity. We know normally positive charge is more stable on less electronegative. So where should be the positive charge more stable? Positive charge should be more stable on carbon, because that is, carbon is less electronegative than oxygen. But here, the case is reverse. Positive charge is more stable on oxygen here. Why is that? Because look at the octet of oxygen. 2, 4, 6 and 8. The octet is complete. Look at the octet of carbon. 2, 4, 6. This is incomplete octet. This is incomplete octet. Here you have got complete octet. Here you have got complete octet. Let me tell you, positive charge can become more stable on more electronegative as well if the octet is complete. If the octet is complete, that is the statement which I have written over here. Positive charge can become more stable on more electronegative element when its octet is complete. Is this point clear? Is this point clear? Normally, what is the trend? Carbon, oxygen, they belong to same period. Same period, electronegativity plays a role. Positive charge is normally more stable on less electronegative. So this positive charge on carbon should be more stable. But here, oxygen carrying positive is more stable. Positive on oxygen is more stable. Why is that? Because here the octet is complete. Here the octet is incomplete. So do remember, positive charge can become more stable on more electronegative element if the octet is getting complete. Yes or no in the chats? Everyone, quickly in the chats. My dear students, remember these points. Remember these points. Remember these points. Now comes one more point. Now comes one more point. Whenever you have to compare the stability of the charges on the elements which belong to same group, whenever you need to compare the stability of the charges on the elements which belong to same group, at that point of time, you are not going to consider electronegativity. You are going to prioritize volume charge density. You are going to prioritize volume charge density. Along the period, always talk in terms of electronegativity. Group, talk in terms of VCD. Talk in terms of VCD. And I hope you know your volume charge density is equal to charge present on the species divided by size of the species. And you must be knowing, already have discussed, stability is inversely proportional to volume charge density. Right? These are the two things which you have to remember, nothing else. Now we will try to understand. Try to understand. Try to understand. Chlorine carrying negative, bromine carrying negative, iodine carrying negative. Do these elements, do they belong to same period or same group? You tell me the answer. Do they belong to same period or same group? These elements belong to same group. And in the group, VCD plays a role. In the group, VCD plays a role. The charge on every species is same, but the size is different. This particular species has got more size. More size means less VCD. Less volume charge density means more stability. Now tell me, where is the negative charge more stable? I would say this is the stability order of negative charge. Yes. I hope you are getting this. I hope you are getting this. Again, chlorine carrying positive, bromine carrying positive, iodine carrying positive. Now you have to answer me. You have to answer me. Whether these elements, whether they belong to same period or same group. Whether these elements belong to same period or same group. They belong to same group. In the group, VCD plays the role. Volume charge density plays the role. Now you tell me, the charge everywhere is same. The charge everywhere is same. But the difference lies in size. Iodine, it has got more size. More size, less volume charge density. Less the volume charge density, more the stability. So where is the positive charge more stable? This is going to be the stability order. Say yes or no in the chats if it's clear. Say yes or no in the chats if it's clear. Everyone. Quickly, people, everyone in the chats. Guys, I want the Josh to be high all the time. It's a big marathon. It is a big marathon, okay? So you have to keep me motivating as well with your chats. I want the chats to run continuously. And I can see not everyone has liked the session yet. So do like the session right now. Right now means right now. Or else you're over, you're gone. Yeah. Everyone, people, everyone. Everyone in the chats, yeah? Perfect. Whatever concepts we have discussed till now, I'm going to utilize all the concepts now in the questions. But before showing you the questions, just a quick revision of everything. Just a quick revision of everything. Whenever we need to compare the stability of the charges on the elements which belong to same period, we have to talk in terms of electronegativity. Negative charge is more stable on, more electronegative. Positive charge is more stable on, less electronegative. Number one. Number two, whenever we need to compare the stability of the charges on the elements which belong to same group, volume charge density plays a role. Volume charge density plays the role. Stability is inversely proportional to VCD. That's all. That's all. Now, people, try to solve the questions which I'm giving you. Almost, I have got more than 500 questions today. Almost, more than 500 questions today. All right. Arrange the following in the stability order. Can you let me know where is the positive charge maximum stable? I would want to see your answers first. I would want to see your answers first. I would want to see your answers first. Where is the positive charge more stable among all these 4 or 5 species? Quickly, everyone, quickly. You should be in a position to answer this question. You should be in a position to answer this question. You should be in a position to answer this question. Everyone. Everyone means everyone. Are you sure? Are you sure? What kind of logic did you use here? See, guys. Carbon positive, nitrogen positive, oxygen positive, fluorine positive. These elements belong to same period. In the period, electronegativity plays a role, right? Positive charge is more stable on less electronegative. Positive charge is more stable on less electronegative. Look at the second question. Carbon carrying negative, nitrogen negative, oxygen negative, fluorine negative. Carbon, nitrogen, oxygen, fluorine. Again, they belong to same period. Electronegativity plays a role. Electronegativity plays a role. Negative charge is more stable on more electronegative. Negative charge is more stable on more electronegative. So this is the stability order. Sulfur carrying negative, chlorine carrying negative. Where is the negative charge more stable? Sulfur and chlorine, same period. Electronegativity. Electronegativity plays a role. Negative charge is more stable on more electronegative. So which one is more electronegative among these? Chlorine. So negative charge is more stable here. Oxygen negative. This is oxygen, this is sulfur, this is Se, this is Te. They belong to same group. They belong to same group. We have to consider VCD here. We have to consider VCD here. Now charge everywhere is same. Look at the size. Down the group size increases. Size is maximum here. Size is maximum here. And you know, VCD, it's inversely proportional to size. It's inversely proportional to size. More the size, less the VCD. Less the VCD, more the stability. This is the order of stability of these negative charges. Yes. Perfectly done. Perfectly done. Perfectly done. Yes or no? Look at the more questions. More questions on the screen. Have a look. Nitrogen carrying negative, phosphorus negative, arsenic negative, antimony negative. Do these elements belong to same period or same group? Everyone. Same period or same group. They belong to same group. VCD plays a role. More the size, less the VCD. Lesser the VCD, more the stability. Right? This is the stability order of the negative charges. Right? Tell me here. Oxygen carrying negative, sulfur carrying negative. Oxygen, sulfur. Oxygen, sulfur. Same group. Same group. VCD. More size, less VCD, more stability. Is this the order? Quickly. Let me know here. Let me know here. If you look properly, this is single bonded carbon. This is double bonded carbon. This is triple bonded carbon. Where is the S character more? Where is the S character more? Single bonded, double bonded, or triple bonded? Where is S character more? Here the S character is more. So I would say electronegativity of this one is more. Right? But we know positive charge is more stable on less electronegative. Right? We know positive charge is more stable on less electronegative. This one is less electronegative. So this is the stability order. Done? Simple trick to remember. That's it. Okay, look at the next one. Carbon carrying negative, double bonded carbon carrying negative, triple bonded carbon carrying negative. Where is the S character more? Where is the S character more? S character is more here. Right? S character is more here. sp hybridized. If S character is more here, that means its electronegativity is more. And you know, negative charge is more stable on more electronegative. Negative charge is more stable on more electronegative. So is this going to be the stability order? Absolutely, this is going to be the stability order. Absolutely, this is going to be the stability order. These questions, tell me their answers. Tell me their answers, people. Negative charge on 3-membered ring. Negative charge on 4-membered ring. 5-membered, 6-membered. Which one has got maximum angle strain? Which one has got maximum angle strain? सर आप कश्मीरी लगते हो. हाँ बेटा मैं कश्मीर से हूँ, श्रीनगर से हूँ. चलिए. Have a look, people, here. Have a look here. Which one is under maximum angle strain? I'll say first one is under maximum angle strain. First one is under maximum angle strain. Right? More the angle strain, more the electronegativity. So electronegativity of this carbon will be more than that of this one. Right? And negative charge is more stable on more electronegative. This is the stability order. Positive charge is more stable on less electronegative. This is the stability order. Now tell me this particular scenario. Carbon carrying negative and nitrogen carrying negative. Where is the negative charge more stable? You need to answer this. You need to answer this, everyone. You need to answer this. You need to answer this, people, quickly. Quickly. Where is the negative charge more stable, on carbon or nitrogen? So normally, what should you think? Normally, you'll think like this. Carbon and nitrogen, they belong to same period. In the period, electronegativity dominates, right? And you know, negative charge is more stable on more electronegative. So this has to be the stability order. But if I ask you, is this the actual stability order? This is not the actual stability order. This is not the actual stability order. Remember this, people. Remember this. This is a special case. It is a special case. Here you have got sp hybridized carbon. The carbon which you have here, it's sp hybridized. Nitrogen, it is sp3 hybridized nitrogen. It is sp3 hybridized nitrogen. Do remember, electronegativity of sp hybridized carbon is more than that of electronegativity of sp3 hybridized nitrogen. If you want to remember the values, the value here is 3.25. Here the value is 3. Electronegativity values I'm giving, right? Now, which one is more electronegative? I would say this particular species is more electronegative. If it is more electronegative, then it's evident negative charge is more stable and more electronegative. So this is the order. This is the order. So this was the first type of question which we did here. Arrange the charges on the basis of their stability. Right? Right, people? Let me know, everyone in the chats with the fire symbol. If every single thing is clear, then I'll show you one more type of question which we can do from the same concept which I taught you. Tell me first of all in the chats. With the fire emojis, guys, I don't want the chats to be slow at all. I don't want the chats to be slow at all. I don't want the chats to be slow at all, people. I don't want the chats to be slow at all. Let me first of all see how many people are watching us and what is happening in the chats, because I'm unable to see your chats from there. Is it live? I think I need to refresh it once. Okay, this is the refresh screen, but I'm unable to see the chats again. Wow, nice, good. Okay, where are your live chats? Here are your live chats. Guys, I want the chats to run fast. What is this? What is happening? They're stagnant, right? The chats are stagnant. If every single thing is clear till here, I want the chats to light up with the fire emoji. Everyone. If every single thing is clear till here. And I believe I've taught in entire depth, guys. Yes? All clear? All clear? So we have got Zifan, we have got Lakshmi, we have got a lot of people. Well, I am unable to see now. We have got Suja, we have got Killer Science. Killer Science is a very old student, by the way. Since it's been almost 7 months we have started this channel, and I have seen this Killer Science guy from day one itself on this channel. Wonderful, good. Oh, we have got Yavar Manzoor sir as well in the chats. Right? We have got Yavar Manzoor sir in the chats as well. Wonderful. We have got Selva Kumar as well. Selva is also an old student. Laharika is an old student. Nice, nice, nice. Good, good, good. Good. We have got Nikki, we have got Namrata, we have got Priya. All are regular students here. Good job, guys. I want you to be regular till the end. By the way, tomorrow we have got one more amazing session, guys. In the evening at 7. I'll be revealing one more amazing surprise with you. Right? Tomorrow at 7 p.m. on this particular channel itself. Yeah? And I can see the likes are pretty much less. Why is it? Don't I deserve a single like from you? Right? Don't I deserve a single like, guys? Okay, so should we move on? So first step of the question is done and dusted. Let's move on now. Let's move on now to one more type of question. Acidic strength. Acidic strength. Try to understand what exactly I'm going to say. My dear students, for example, I'm going to take an acid over here. This is acid. HA aqueous. It is an acid. It is an acid, right? I've introduced the acid in water. I've introduced the acid in water. Now, what this acid is going to do in water? This acid in water, it's going to donate H positive. You know it, right? You know it. So this acid, when you introduce this acid in water, it's going to donate what? It's going to donate H positive. After donating H positive, it is going to get converted into A negative. After donating H positive, it's going to get converted into A negative. This is something which you were calling as acid. This is something which you were calling as acid. And after the liberation of H positive, this acid, it got converted into A negative, right? This A negative here, I will be calling as the conjugate base. This is the conjugate base of the acid which I've taken over here. Right? This is acid. Acid, after donating H positive, it is getting converted into A negative. This A negative I'll be calling as conjugate base here. This is something which I'll be calling as conjugate base here. Now do remember, strength of the acid, people, strength of the acid, do remember, it is directly proportional to Ka value. I believe you would have studied Ka somewhere. Ionization constant of the acid, which I'm going to teach you in the upcoming chapter, equilibrium, right? If you do not remember it yet, remember it from now onwards. Strength of acid is directly proportional to Ka, which is inversely proportional to P of Ka, So basically, there will be a set of questions which will be asked on strength of acid. There'll be a set of questions which will be asked on Ka. There'll be a set of questions which will be asked on pK. Now, do remember, strength of acid is directly proportional to the stability of the conjugate base. This is the only statement which I would want you guys to remember here. Strength of the acid, it is directly proportional to the stability of the conjugate base. Strength of this acid is directly proportional to the stability of its conjugate base. More stable the conjugate base, stronger the acid. More its Ka value, less its pK value. Simple as that. Right? Do remember this. Strength of acid is directly proportional to stability of conjugate base. Now, I'm going to do many questions on this particular one statement. Strength of the acid is directly proportional to stability of its conjugate base. Right? Just remember it and have a look. See how I'll be dealing with the questions. My dear students, among these two, you have to identify which acid is stronger, ROH or SH. Which one is stronger among the two? Which one is stronger among the two? The concept which I gave you right now, you are going to utilize that concept itself. ROH or SH. Which one is more acidic? Which one is more acidic? How exactly you're going to do it? Try to understand. First of all, if I talk about ROH, my dear students, after the liberation of H positive, the conjugate base which we get over here, that is RO negative. RO negative is the conjugate base of this acid. Similarly, we have got RSH. After the liberation of H positive, it gets converted into RS negative. So I made their conjugate bases. Now, look at the stability of these conjugate bases. Tell me, oxygen carrying negative, sulfur carrying negative. Oxygen carrying negative, sulfur carrying negative. Oxygen and sulfur, same group. VCD plays a role. VCD plays a role. More the size, less the VCD, more the stability. So I would say this conjugate base is more stable. And that acid which gives more stable conjugate base, strength of that acid will be more, right? So which acid is stronger? Our SH is stronger than ROH. Simple. Yes. Simple. The kind of concepts which I gave you, I'm utilizing those concepts only. I'm not telling you something new. Look here. Make their conjugate bases. Make their conjugate bases first of all. Take H positive out from here. You'll be getting a negative on carbon. Take H positive out from here. You'll be getting negative on nitrogen. Take H positive out from here. You'll be getting negative on oxygen. Take H positive out from here. Negative on fluorine. Negative on fluorine. Now you tell me, carbon with negative, nitrogen negative, oxygen negative, fluorine negative. All these elements, they belong to the same period. In the period, we talk in terms of electronegativity. Negative charge is more stable on, more electronegative. Negative charge is more stable on, more electronegative. So negative charge will be more stable on fluorine. So the conjugate base which you get from HF, that is more stable. If the conjugate base is more stable, I would say the acidic strength of these acids will follow the same order. Done and dusted? Absolutely. H2O, H2S. Take H positive out, there'll be a negative charge on oxygen. Take H positive out, negative charge on sulfur. Right? If on taking H positive out, negative charge on oxygen. On taking H positive out, negative charge on sulfur. Now look at oxygen and sulfur. Oxygen, sulfur, same group. In the group, VCD. More the size, less VCD, more stability. So the conjugate base which I get from H2S, that is more stable. If that is more stable, that means this has to be the strength of these acids. Right? Done. Look at the next one. Say, take H positive out from here, carbon will carry negative. Take H positive out from here, this carbon will carry negative. Take H positive out from here, this carbon will carry negative. So you have made the conjugate bases. Now see, single bonded carbon, double bonded carbon, triple bonded carbon. Triple bonded carbon has got more S character. More S character means more electronegativity. And you know, negative charge is more stable on, more electronegative. So the conjugate base which you generate from here, that is maximum stable. And more stable the conjugate base, better is the acid, more is the strength of the acid. So this is the acidic strength order. Yes? Okay. Tell me about this one. Quickly. This is H here. Tell me about this one. Among these two, which one is more acidic? You have to tell me the answer. Among these two, which one is more acidic? You have to tell me the answer. Dr. Strange, you need to watch the session from the beginning, then you'll get to know what is S character. Which one is more acidic? Guys, this concept also I've given you. This concept I've given you too. Which one is more acidic? You have to answer me this. And the answer has to be correct. It has to be appropriate. If you give the wrong answer here, it will be a heartbreak for me. It is actually going to be a heartbreak for me if you give the wrong answer here. I can see majority has given the correct answer. Wonderful, good job. Hey guys, what you'll be doing? Make their conjugate bases. Take H positive out from here. You'll be getting something like this. HC triple bond, carbon carrying negative. Take H positive out from here. It's going to be NH2 carrying negative, right? Now these are the conjugate bases. Look at their stability. This is sp hybridized carbon. This is sp3 hybridized nitrogen. Electronegativity of sp hybridized carbon is more. And you know, negative charge is more stable and more electronegative. So this is the stability order of these conjugate bases. And whatever is the stability order of the conjugate bases, same is the order of their acidic strengths. Done and dusted, right? Yes? Is it clear? I believe every single thing, whatever I have taught you till now, is clear. So, the basics which was required to learn the general organic chemistry, that is clear. And by learning the basics, you could solve two types of questions. First question on the basis of, first question was stability of charges on different species. Second question was the acidic strength. Remember, acidic strength is directly proportional to stability of conjugate base. Nothing else you have to remember. That's it. Is it clear? Are you ready for the inductive effect now? Are you ready for the inductive effect? I want the chats to move fast. They are pretty slow. I want the chats to run fast. They should run. They should not walk. They should run. They should run. Yes. Basic strength questions will be given too, but wait for it. We have to do certain concepts first. And the ones, again, who have not liked the session yet, like the session right now. I want the likes to be more than 1K quickly. I can see not everyone has done that. Guys, it does not, I mean, you need not to pay for the likes. It's free. Yeah, it is free. But when you enter into your medical college, then I'll make you pay, okay? Just remember that. When you enter into your medical college, I'll make you pay for whatever I've done on YouTube, whatever the team has done on YouTube. Yeah? And I believe at that time you should, and you will, and I'll make sure you do. Okay, perfect. Hello guys, let's move on to something called as inductive effect. This is again one important concept and simple at the same time. Simple at the same time. Have a look. How do you exactly define the inductive effect? Dear students, I'll be writing a simple statement over here. Then I'll make you understand what that statement exactly is all about. Inductive effect. Whenever an atom or a group is attached to a carbon chain. Whenever an atom or a group is attached to a carbon chain, the chain becomes partially polarized. The chain becomes partially polarized. Due to the transmission of sigma electrons. Due to the transmission of sigma electrons, or let me write, due to the transmission of sigma electron density. This effect is something which we call as inductive effect. This effect is something which you call as inductive effect. Now, what does it mean? How can we understand this? Have a look, people. For example, I'm taking a carbon chain over here. Let's assume you have got this particular carbon chain, right? This is the carbon chain which we have. Okay, this is the carbon chain which we have. And this particular carbon, imagine it is attached with hydrogen. Right? My dear students, in this particular chain, can I say there are only sigma bonds present? Yes, in this chain, there are only sigma bonds present, right? So can I say in this chain, there is only sigma electron density? Absolutely, in this chain, right now, there is only sigma electron density. Now, what exactly I'll be doing? I'll be replacing this hydrogen. I'm going to replace this hydrogen by an atom or a group of atoms. I'm going to replace this hydrogen by an atom or group of atoms. For example, these were 1, 2, 3, 4, 5. These were 5 carbon atoms in the chain. 1, 2, 3. This is 4 and this was 5. Right? Now, I'm replacing the hydrogen by an atom X. Right? By an atom X. And similarly, my dear students, I'm again going to replace this hydrogen by an atom Y. So these are your 1, 2, 3, 4, 5. 5 carbon atoms. This was your carbon chain. Now, instead of hydrogen, here I'm attaching what? Here I'm attaching an atom or group Y. So what I exactly did? I took a carbon chain, which includes only the sigma electron density. Now, instead of hydrogen, I placed X, and here I placed Y. My dear students, let's look at this particular scenario first of all. I'm assuming electronegativity of X is more than that of electronegativity of carbon. Now you tell me, if electronegativity of X is more than that of electronegativity of carbon, what's going to happen? Can I say this X will pull the sigma electrons towards itself? Absolutely. If X is more electronegative than carbon, that means X has got more tendency to attract the bonded pair towards itself. So this particular bonded pair, can I say it will shift towards X, due to which this X gets delta negative and this particular carbon gets delta positive. Now this particular carbon which got delta positive, can I say it is going to attract this bonded pair as well towards itself, right? It's going to attract this bonded pair towards itself as well, due to which this will also get delta positive. Now this will attract this will also get delta positive. Perfect. If you try to understand, when I attached an atom or a group to the carbon chain, can I say the carbon chain got partially polarized? Have a look on the charges. The carbon chain got partially polarized. And the carbon chain got partially polarized due to what? Due to the transmission of sigma electrons. Whenever you see this kind of the effect in which upon the introduction of an atom or a group, the carbon chain becomes partially polarized due to the transmission of sigma electrons. Due to the transmission of sigma electrons, you call this particular effect as the inductive effect. So I would say this group or atom, it is showing which effect right here? It is showing inductive effect. It is showing inductive effect. Point number one. Point number two. My dear students, imagine that electronegativity of carbon is greater than that of electronegativity of Y. If electronegativity of carbon is more than that of Y, that means carbon has got more tendency to attract this bonded pair towards itself, right? Carbon has got more tendency to attract this bonded pair towards itself, due to which this carbon gets delta negative and this Y gets delta positive, right? Now, my dear students, this carbon carrying delta negative, can I say it's going to repel this electron pair? If it repels the electron pair, I'll say this carbon will get delta negative. Now, similarly, due to repulsion, this carbon will get delta negative. So what happened over here? When you introduced an atom or a group, the chain got partially polarized due to the transmission of sigma electrons. So again, I would say this Y over here is showing which type of effect? It is showing inductive effect. Now, my dear students, try to understand one very simple thing. Tell me, what do you see exactly? Is this X increasing the electron density in the chain or decreasing? This X is pulling the sigma electrons towards itself. So this X, it is decreasing the sigma electron density. So can I call this X as electron donating or electron withdrawing? Here, I'll be calling it as electron withdrawing group. This X will be called as electron withdrawing group. Here, this Y, should I be calling this as electron donating or electron withdrawing? This Y is donating, right? It's donating. It is pushing sigma electron density in the chain, right? So I would call it as electron donating group. My dear students, that particular group which withdraws sigma electron density from the chain, that particular group which decreases the sigma electron density in the chain, we say that group shows minus I effect. So I would say the group or atom X which I've attached over here, it is showing minus inductive effect. From now onwards, remember, minus means withdrawing, plus means donating. Minus means withdrawing, plus means donating, right? Over here, this electron donating. If it is electron donating, I would say this particular group is going to show plus I. So do remember this particular statement as well. That atom or group which decreases the sigma electron density in the chain due to the transmission of sigma electrons, that group is electron withdrawing, and we say that group shows minus I effect. And here I would say the group is showing plus I effect. It's electron donating. Donating is plus, withdrawing is minus. Donating is plus, withdrawing is minus. That's all. Is this clear? I hope you got the idea of what this inductive effect is all about. And my dear students, this inductive effect, it's a weak effect. It's a weak effect. What is meant by this particular term? It's a weak effect. What is meant by this particular term? It's a weak effect. My dear students, let me tell you, we do not consider the inductive effect after 3 carbon atoms. If you would have analyzed this particular statement here, if you have analyzed this particular case over here, this carbon I showed positive, this positive, this positive. After that, I did not show any charge. This carbon I showed negative, this carbon I showed negative, this carbon I showed negative. After that, I did not show any charge. So inductive effect, we are only going to take up to 3 carbon atoms. The charges due to inductive effect, we are only going to take up to 3 carbon atoms. After that, inductive effect vanishes. After that, inductive effect vanishes. After that, inductive effect vanishes. I believe this is clear. Okay, I believe this is clear. These two statements I already told you. Look at these statements and understand whether these are clear to you or not. That atom or group which decreases the sigma electron density in the chain, we say that group shows minus I effect. That group or atom which increases the sigma electron density in the chain, we say that atom or group shows plus I effect. Right? This is understood now. This is understood now. This is understood now. Now, my dear students, there is one more term. Plus I and minus I, we say they are relative to each other. We say they are relative to each other. What does that mean? What does that mean? We say they are relative to each other. Try to understand one thing. Look at this particular molecule. Here you have got 3-membered ring. Here you have got 4-membered ring. I would say this particular carbon is more electronegative. This particular carbon is comparatively less electronegative. We know due to angle strains. This is more electronegative. So it will attract this bonded pair towards itself, due to which it gets delta negative. This gets delta positive. If you particularly look at this particular group, if you particularly look at this group, what do you think? Is this group pulling the electron density, pulling the sigma electron density towards itself? I would say yes, this group is pulling the sigma electron density towards itself. And that group which pulls the sigma electron density towards itself, we say that group shows minus I effect. Now people, look at this particular group. Look at this particular group. Is this group pulling the sigma electron density or pushing? It is pushing the sigma electron density towards the other one, right? So I'll say this particular group is showing plus I. So basically this plus I and minus I, they are relative to each other. I would say this group is showing minus I with respect to this one, and this is showing plus I with respect to this one, right? This group is showing minus I with respect to this, and this is showing plus I with respect to this. So plus I and minus I, they are going to be relative to each other. They are relative terms. They are relative terms. One is withdrawing with respect to another. Another is donating with respect to another. Yeah. Similarly, look at this particular case. Here the carbon is sp hybridized, right? Here the carbon is sp2 hybridized. Perfect, right? So this carbon will be more electronegative. If it is more electronegative, it will attract the sigma electron density towards itself. It will attract the bonded pair towards itself, due to which it gets delta negative. This gets delta positive. Now people, just try to understand one simple thing. Look at this particular group. Look at this particular group. This particular group, is it pushing the electron density or pulling the electron density? It is pulling the electron density. If it is pulling the electron density, that means it is going to show minus I. This particular group, is it pulling the electron density or pushing the electron density? It is pushing the electron density, right? So this group is showing plus I. This group is showing plus I. So I'll say this particular group is showing minus I with respect to this one, and this shows plus I with respect to this one. So again, I can categorically say this plus I and minus I, they are relative terms. They are relative terms, right? They are relative to each other. I believe this particular statement is also clear to you. Now guys, in order to do the questions on inductive effect, we have to remember certain things. In order to do the questions, we have to remember certain things. Point number 1, all the cationic groups, they show minus I effect. All the cationic groups, they show minus I effect, right? All the cationic groups means group carrying positive, group carrying positive, group carrying positive. Any group which carries the positive charge, remember, it's always going to show minus I. It's going to withdraw the sigma electron density. It's going to be electron withdrawing. It's going to be electron withdrawing. Point number 1. Point number 1. All the cationic groups, they show minus I effect. They are withdrawing in nature, right? Minus I power of cationic group, minus I power of cationic group will be always greater than that of minus I power of neutral group. Minus I power of cationic group will be always greater than that of minus I power of neutral. One more thing. Guys, I will have to use all these things in the questions. That's why I keep on telling you all the time to remember all these things. All the cationic groups, they show minus I power. Minus I power of cationic group will be greater than that of minus I power of neutral group. All your halogens, chlorine, bromine, iodine, all your halogens, they are withdrawing in nature. They show minus I effect. all your halogens, they are withdrawing in nature. They are electron withdrawing in nature. They show minus I effect, right? Groups like OH, NH2, NO2, CN, they are also minus I. They also show minus I. Now the point is why? Now the point is why? Understand. My dear students, if this OH is attached to a carbon chain, oxygen is more electronegative than carbon. So it will attract the bonded pair towards itself, right? It's behaving like electron withdrawing. If it is electron withdrawing, so minus I, right? Look at this one. If this nitrogen is attached to the carbon chain, look at the first atom, nitrogen. If this is attached to the carbon chain, nitrogen is more electronegative than carbon. It will attract the sigma electron density towards itself, right? Again minus I. Nitrogen, attach this with carbon chain, again minus I. This is CN. This is C, triple bond N. Attach this with carbon chain. Attach this with carbon chain. What you'll observe? Look at the hybridization of this particular carbon. It's sp. Look at the hybridization of this particular carbon. It's sp3. Right? This one is more electronegative. If this one is more electronegative, it will attract the sigma electrons towards itself. Right? Attracting. So it is behaving like electron withdrawing group. So this is going to show what? This is going to show minus I. So Cn also shows minus I. I'm showing you exactly how to identify whether the group is showing plus I or minus I. Right? I'm exactly showing you how to identify whether the group is showing plus I or minus I. People try to look at this particular case. This is C double bond O. Imagine this particular group is attached with a carbon chain. What you will observe? Carbon, oxygen. Which one is more electronegative? Oxygen. If oxygen is more electronegative, so this will carry delta negative, this will carry delta positive. Now this delta positive on carbon will attract these sigma electrons towards itself, right? Perfect. So is this group behaving like electron withdrawing or electron donating? This is electron withdrawing. So I'll say it will directly show minus I, right? It will directly show minus I. Look at this particular case. This will also show minus I because this minus delta, this is plus delta. This is minus delta, this is plus delta, this minus delta, this is plus delta. So all these groups, whatever are mentioned on the screen, they are going to show minus I effect. All these things are clear. Say yes or no once in the chats. I will have to utilize all these things in the questions, people. I'll have to utilize all these concepts in the questions. Everyone, quickly, everyone. So from this particular slide, what we have to remember, minus all the cationic groups, they show minus I. They are withdrawing, right? Minus I power of cationic group will be greater than minus I power of neutral group. Second thing. And third thing, all the halogens, they are electron withdrawing. They show minus I. And all these groups, whatever are mentioned on the screen, they show minus I, right? When attached to the carbon chain. Yes? Perfect, people? I believe this is clear. Now, similarly, what are plus I showing groups? My dear students, just opposite of what I told you. Plus I means electron donating. All the anionic groups, all those groups which carry the negative charge, all the anionic groups, they are electron donating. They show plus I. Number one. Number two, plus I power of anionic groups, will be greater than that of plus I power of neutral groups. So anionic groups, they are more electron donating than that of your neutral groups. All your alkyl groups, CH3, right? This is methyl, right? C2H5, this is ethyl. Perfect. All your alkyl groups, they always show plus I. That means they are electron donating or withdrawing. They are electron donating. Why they are electron donating? Have a look on this one as well. Imagine this is CH3. What imagine? This is CH3, right? This is CH3 here. It is attached to a carbon chain. Now, among carbon and hydrogen, which one is more electronegative? You tell me. Among carbon and hydrogen, carbon is more electronegative. So this carbon will be definitely getting delta negative, right? Because carbon is more electronegative. If carbon gets delta negative, there's a bond pair here. There will be repulsions. This negative charge will repel this bond pair and will push the sigma electron density in the chain. If it is pushing the sigma electron density in the chain, So I'll say this particular group, is it donating or withdrawing? This is donating. And your donating here are called as plus I. So all your alkyl groups, be it methyl, ethyl, propyl, butyl, whatever aryl, right? They're always going to be donating, right? As per plus I. Yes? Let me know in the chats quickly. Let me know in the chats quickly, people. Let me know in the chats quickly. Everyone. Everyone means everyone. Everyone means everyone. Quickly. I will tell you one more important statement. There are few things which I need to tell you about inductive effect. Then we'll see its application. We'll see the types of questions which are asked. My dear students, one more important thing. Plus I. Whenever you hear the term plus, plus means electron donating. And right now I'm talking about plus I power. Plus I power, it is directly proportional to number of branching at the free valent carbon. Plus I power, it is directly proportional to number of branching at free valent carbon. What does it mean? Imagine this is a group. Imagine this is a group. Imagine you are attaching this group with a carbon chain. Imagine you are attaching this group with a carbon chain. This is a carbon chain with which you have attached the group. That carbon of the group which is directly attached with the chain, you'll be calling that as free valent carbon. This is your free valent carbon. This is your free valent carbon. As per this particular statement, plus I power is directly proportional to number of branches. If I ask you how many branches this free valent carbon has, this is one of the branch which it has, this one more branch. So this free valent carbon, it has got two branches here. It has got two branches here, right? Look at the other case. If this is the group and you're attaching this with the carbon chain, you're attaching this with the carbon chain. This carbon is directly attached with the carbon chain. So this is your free valent carbon. This is your free valent carbon. And 1, 2, and 3. There are 3 branches which are associated with the free valent carbon. Do remember one thing. More branches means more plus I. More branches means more plus I. More branches means more plus I. Now you tell me one simple thing. You tell me one simple thing. If I talk about this particular group, this is group 1 and this is group 2. Which group is maximum branched at the free valent carbon? The second one, right? So its plus I power be more. So this group will have more plus I power. As simple as that, because branching is more. Yes? Simple? Simple? Now, if the branching is same, if the branching is same, then plus I power is directly proportional to number of carbon atoms. If the branching is same, then plus I power is directly proportional to what? Number of carbon atoms. What does that mean? Invite code for tomorrow's 11 AM extra problem session. This is, guys, it might ask you the code. Wassim10 is the code. Wassim10 is the code for tomorrow's 11 AM extra problem session of GOC. Okay? Perfect? All right. Look at this particular thing, guys. What I was talking about? If the branching is same. For example, this is the group which is attached to the carbon chain. This is the carbon chain, for example. This is the free valent carbon. If this is a free valent carbon, how many branches? Just one branch it has, right? One branch it has. Similarly, if this is the group, if it is attached with a carbon chain, this is a free valent carbon here. It's a free valent carbon. How many branches it has? It has 2 branches, right? This is the free valent carbon here. It also has got one branch only. Why am I writing 2 branches? It has 1 branch, right? This particular carbon, how many branches it has? It also has 1 branch. Perfect. So whatever free valent carbons we had in these 3 cases, all the free valent carbons are having one branch. Perfect. One branch. Now, if the branching is same, how do you relate plus I power? Plus I power is directly proportional to number of carbon atoms. Tell me, in which branch carbon atom is more? Carbon atoms are more here. So this particular group will be showing more plus I. This will be showing more plus I, followed by this particular one, followed by this particular one. So do remember, if the branching is different, more the branches, more the branches at free valent carbon, more the plus I. If the branching is same, then what do you have to do? Then you have to look at the number of carbon atoms in the branch. More carbon atoms in the branch means more plus I. I believe this is clear. Yeah? Perfect. Similarly, if you talk about hydrogen, Do you know how many isotopes of hydrogen do we have? How many isotopes hydrogen has? You should know it. How many isotopes hydrogen has? Quickly. 3. Protium, deuterium, tritium. Protium, deuterium, tritium. And all these isotopes of hydrogen, they show plus I power basically. They show plus I power. And do remember, plus I power of tritium is maximum, then that of deuterium, then that of what? Then that of protium. On this particular thing, again, there will be few questions that will be asked. Perfect. Are you ready to solve the questions now? Are you ready to solve the questions, people? Are you ready to solve the questions? Are you ready to solve the questions? Are you ready to solve the questions? You can only solve the questions if you remember all these things. This was the first thing which you have to remember. Some common minus I showing groups. Remember these particular points. Common plus I showing groups, right? Similarly, branching, right? How it affects. A particular set of questions I'm going to give you. You have to answer. You have to answer. A particular set of questions. There is a lot of application as per this inductive effect, right? A particular application. Arrange the following according to their minus I power. Arrange the following according to their minus I power. You tell me. Arrange the following as per their minus I power. Quickly. Quickly, guys. Chlorine, chlorine, bromine, iodine. Which one will be having more minus I? Which one will be having more minus I? You know it. Chlorine is more withdrawing, then chlorine, then bromine, then iodine, right? Chlorine attached with carbon chain, oxygen attached with chain, nitrogen attached with chain. Which one is more withdrawing? This will be more withdrawing. Simple. This is the cationic group, this is a neutral group. All the cationic groups, they have got more plus I, more minus I. So this is more withdrawing. This is more withdrawing. Look at the next one. Oxygen attached with the chain, nitrogen attached with the chain. Oxygen is more withdrawing. More minus I. More minus I. Right? More minus I. This is your sp hybridized carbon because it's forming 2 sigma bonds. This is your sp2. This is your sp3. This is your sp3. Where is the S character more? S character is more here. Electron negativity is more here. So it will be more withdrawing. This will be more withdrawing. This is how you arrange these groups on the base of their minus I power. Simple. Simple. This is how you are going to arrange them on the base of their minus I power. Now, tell me about these. Tell me about these. Among these three, 1, 2 or 3, which one will show more minus I power? All the concepts which I gave you, all those concepts only you have to utilize. All those concepts. I'll give you a break once inductive effect is completed. Inductive effect and its application part is completed. Then I'll give you a break. And after the break, we'll start the resonance. Quickly. It's very evident, guys. If this group is attached with a carbon chain, this group will carry delta positive because oxygen carries delta negative. Electronegativity difference, oxygen is more electronegative. So delta negative, delta positive. Even this, there is electronegativity difference here. So this delta positive, this delta negative. Right? Perfect. Now you tell me just one thing. Carbon-oxygen electronegativity difference is more than that of carbon-nitrogen. If the electronegativity difference here is more, that means the magnitude of positive charge here is more. Right? So magnitude of positive charge here is more than that of magnitude of positive charge here. Right? If the magnitude of positive charge here is more, can I say it will pull sigma electrons more towards itself? Right? So what has to be the electron withdrawing nature? Minus I power. This is the minus I power. Simple and basic. Right? NF3, NH3. Both are cationic groups. NF3, NH3. Here nitrogen is attached with fluorine. Here nitrogen is attached with what? It's attached with hydrogen. Fluorine is more electron. Fluorine is more electron negative than nitrogen. So fluorine will increase the intensity of positive charge on nitrogen. Fluorine will increase the intensity of positive charge on nitrogen, due to which it becomes more withdrawing. Right? NH3, PH3, ASH3. One simple thing. Nitrogen, phosphorus, arsenic, antimony. Do they belong to same period or same group? They belong to same group. In the group, VCD plays a role. In the group, VCD plays a role. Right? In the group, VCD plays a role. This one has got lesser size. Lesser size means more volume charge density. More volume charge density means more positive volume charge density. If over here you have got more positive volume charge density, so it's going to pull the sigma electrons more towards itself. So it will show more minus I. Simple and basic. OH2 positive, SH2 positive. Same reason. Oxygen carrying positive sulfur, SET. Oxygen, sulfur, SET. They belong to same group. Again VCD. Lesser size, more positive volume charge density. More positive charge volume density means more withdrawing. So this is more withdrawing. More minus I. Right? Now NR3 positive, NH3 positive. NR3 positive, NH3 positive. Can you let me know in the chats, what do you think? Which one will show more minus I? Quickly. Which one will show more minus I? I'm asking you. This is the question I'm asking you. Quickly. Which one will show more minus I? Quickly, guys. Everyone, quickly. Normally, it seems like this should have more minus I. It seems like, because nitrogen here is attached with hydrogen, right? Here nitrogen is attached with alkyl groups. Alkyl groups are donating. So normally a common man thinks that alkyl groups are donating. Alkyl groups are going to decrease the intensity of positive charge here. Alkyl groups are going to decrease the intensity of positive charge here. This has to be more minus I. Normal people think like that, but we are not going to think like that. We are not going to think like that. See, we have got NR3 positive. This is R, this is R, this is R. Nitrogen carrying positive. This is N, this is hydrogen, this is hydrogen, this is one more hydrogen carrying positive, right? Perfect. Let me first of all tell you, the first one has got more minus I. There are a lot of reasons for it. One reason is solvation reason, right? Or in simpler words, just to remember it, what you should remember exactly so that you can remember it. Have a look. RRR, alkyl. Are these bulky groups? You can remember it like this. Are these bulky groups? These are bulky groups. If they are bulky groups, will there be repulsion? Yes, there will be repulsion. If there is repulsion, bond angle increases or decreases? Bond angle increases. If bond angle increases, electronegativity automatically? Yes. Right? Perfect. Electronegativity automatically increases. So, which nitrogen do you see more electronegative here? The first one, right? If first one is more electronegative, it's going to withdraw more electron density from the carbon chain. So, it will show more minus I. There is one more logic, that is solvation. I'm not going into the details, right? I believe this particular statement is clear. I believe these sort of questions you can easily solve. Now, guys, this is the minus I series. Since I have showed you exactly how to check which one has got more minus I, which one has got more plus I, on the basis of all those points, this is the series which you have to remember, my dear. NF3 positive will show maximum minus I power, followed by NR3 positive, followed by NH3 positive. All these three are cationic groups. Then comes your neutral groups, right? Then comes these. You have to remember this particular series. You can create a mnemonic based on your own thing. Yes, yes, Danish, you can watch it. Perfect. This is the minus I series. Similarly, there's a plus I series as well. There's a plus I series as well. First of all, look at all these. These are anionic groups. And you know, all the anionic groups, they do what? All the anionic groups, they have more plus I power than the neutral groups. So that's why anionic groups are the first, then comes your neutral and all. You have to remember this particular series as well. You have to remember this particular series as well. One is for minus I series and another series is plus I series, guys. Okay, plus I series. One thing which I told you already, I believe you remember this. Both plus I and minus I are considered only up to 3 carbon atoms. Both plus I and minus I, they are considered only up to 3 carbon atoms. Because inductive effect, it's not a strong effect, it's a weak effect. Okay. So this was all the theory which was needed in the inductive effect. Now it is the time for questions. But before doing the questions, I need to tell you certain things which will help you in order to solve the questions. My dear students, the first point which I would want you guys to remember, that is stability of carbocations. Stability of carbocations as per inductive effect. Remember, stability of carbocation Carbocation is stabilized by electron donating groups. Carbocations are destabilized by electron withdrawing groups. Carbocations are stabilized by electron donating groups. They are destabilized by electron withdrawing groups. That means, in short, since till now we have studied only inductive effect, so I'm not going to take any other effect into consideration. I'm just going to solve the equations as per what? I'm just going to solve the equations as per inductive effect. Electron donating as per inductive means plus I. Electron withdrawing as per inductive means minus I. So the first type of question will be done from this particular equation which I gave you. Stability of carbocation, right? Electron donating group, it stabilizes carbocation. Electron withdrawing group, it destabilizes carbocation. Perfect. So stability of carbocation is directly proportional to plus I, inversely proportional to minus I. Point number one. Point number two. Stability of carbanion. Stability of carbanion. Stability of carbanion. Carbanion is stabilized. Carbanion, carbon carrying negative. Carbanion is stabilized by electron withdrawing. They are destabilized by electron donating groups. They are destabilized by electron donating groups. They are destabilized by electron donating groups. And my dear students, electron withdrawing as per inductive means minus I. Electron donating as per inductive means plus I. So this is one more question which we are going to do. This is one more question which we are going to do. Right? This is one more question which we are going to do. The third one. The third one. Acidic strength. Acidic strength. Strength of acid. As I told you already, strength of acid. Strength of acid is directly proportional to Ka, is inversely proportional to pKa, and let me tell you, strength of acid, it is directly proportional to what? You know it already. It is directly proportional to stability of conjugate base. Stability of conjugate base. And let me tell you, this conjugate base, it is stabilized. It is stabilized by electron withdrawing groups. Conjugate base is stabilized by electron withdrawing. It is destabilized by electron donating groups. If I only talk inductive effect, if I only talk in terms of inductive effect, electron withdrawing means minus I. Electron donating means plus I. So, few more questions you can get from this particular thing. Few more questions you can get from this particular statement. Few more questions you can get from this particular statement. Since I till now taught you only inductive effect, we are going to do the questions only based on inductive effect now. Yeah. Now, similarly, the fourth question, that is strength of a base. Strength of a base. Strength of a base. My dear students, if I ask you what a base is as per Lewis concept, how do we define a base? Does the base accept a pair of electron or lose the pair of electron? Tell me that. Does a base accept a pair of electron or lose a pair of electron? A base loses a pair of electron, donates a pair of electron. A base donates a pair of electron. Right? You know that? It donates a pair of electron. Correct? Does the base accept H positive or donate H positive? Tell me that. Does the base accept H positive or donate H positive? Does the base accept H positive or donate H positive? It accepts H positive. Base accepts H positive. Can I say H positive can attack on the base? H positive can easily attack on such a base where the electron density will be more. H positive will attack easily on such a base wherein the electron density at some site will be more. Agreed? Right? So tell me, strength of base. Base. For the H positive to attack easily, electron density has to be more or less? It has to be more. How electron density is going to be more? Can I say electron donating groups? Electron donating groups. Electron donating groups, if attached to a base, will increase the strength of the base. And electron withdrawing groups, if attached with a base, are going to decrease the strength of the base. Simple. Right? Now, electron donating means over here in terms of inductive effect, it's plus I. Electron withdrawing in terms of inductive effect, it's minus I. So can you solve all these questions? Can you solve all these questions by considering only inductive effect? Till now we have studied only inductive effect. Now anything can be asked from this particular slide. Anything. Anything means anything. Anything means anything. Now. Let's try to solve certain questions so that it will be absolutely clear to every one of you. Absolutely clear to every one of you. Okay? Just a second, people. Just a second. Just a second. The first and the basic question. You are going to answer me in the chats. Now I want the chats to move fast. Among these two, among these carbocations, which one is more stable? Among these two, which one is more stable? Quickly. Who is this model? Bro, please stop spamming. Please stop spamming. Let people study. You are writing east or west. Alak sir is the best. Of course, he is the best. We appreciate him, right? We love him. Every teacher in the country loves him because of the contribution which he has made, right? But don't write all these things. Let people study, right? Let people study, okay? Right? So, look at this one now. Look at this one. Tell me among these two, which is more stable? Quickly, guys, you are not supposed to take this much of time. You are not supposed to take this much of time. Quickly. One or two. One or two. One or two, quickly. Asha, wait. I'll do this at the end. Tell me among these three. Carbocation is stabilized by plus I. See, this is plus I showing. So 3 plus I showing. Since I've only taught you inductive effect yet, so I'm going to answer the questions only on the basis of inductive effect. So 3 plus I showing groups. How many? 2 plus I showing groups. How many? Only 1 plus I showing group. Right? So more plus I showing groups, more the stability. 1, 2, 3. Done. Question number one. Look at this one. All these are carbocations, right? Carbon carrying positive, carbon positive. Here you have got CH3 attached, CD3 attached, NO2 attached. Carbocations are stabilized by plus I. Carbocations are stabilized by electron donating groups. Now CH3 shows plus I, of course, right? CD3, it also shows plus I, right? NO2, it shows minus I, right? So minus I showing group, it destabilizes the carbocation. So stability of the C at the end, right? Now among 1 and 2, which one does show more plus I? Which one shows more plus I? Is it CH3 or CD3? I hope you remember. Tritium shows more, if you remember in that part. Tritium more, followed by D, followed by H. Similarly, CD3 will show more plus I than that of CH3, right? More plus I means more stability. So BAC is the order. Simple. Look at the next one. No group. Over here you have got NO2 attached. Over here you have got NO2 attached. NO2, is it withdrawing or donating? It's withdrawing, right? It's withdrawing. It shows minus I. Inductive effect, is it distance dependent? Yes, it's distance dependent. So can I say NO2 will be more withdrawing in the third case? NO2 will be more withdrawing in the third case. And if in the third case NO2 is more withdrawing, it will destabilize. It will destabilize this particular species to the maximum. So the stability of C is the least, right? A will be maximum, followed by B. Simple. ABC is the order. ABC is the order. Nothing to do. Tell me about answer of this particular question. A, B or C. Again, these are carbocations. CD3, electron donating plus I. CD3 plus I. CD3 plus I. Right? Now, inductive effect is distance dependent. Where is the distance less? Here the distance is less. So more prominating plus I nature. More prominating plus I nature. Right? So what has to be the stability order? Plus I increase the stability of carbocation. So C will be maximum stable, right? Followed by B, followed by A. Right? Look at the next one. Look at the next one. Look at the next one. This is your alkyl group plus I. This again your alkyl group plus I. This again your alkyl group plus I. Right? Now which alkyl group shows more plus I? Where the branching is more. Where is the branching more? B. B. So this will be maximum stable carbocation, followed by what? Followed by C, followed by A. So BCA is the order. Yes? Clear? Guys, the chat should run continuously. The chat should run continuously. You're supposed to answer all the questions. All the questions. Look at this one. A, B or C. Which one is more stable? All these are carbocations. Carbocations are stabilized by plus I. See, this is alkyl showing plus I. Right? NO2 showing minus I. Right? CN showing minus I. Plus I groups, they stabilize the carbocation. Plus I groups, they stabilize the carbocation. So A will be maximum stable. Right? Now, among B and C, which one is less electron withdrawing? CN is comparatively less electron withdrawing than NO2. So C will be more stable, followed by B. If you remember the series I gave you, right? NO2 is more shows more minus I than that of CN. Now, look at this one. Look at this one. Positive charge is here and positive charge is here, right? Look at this double bond. This is sp2. This is sp2. This is also sp2. But here all are sp3. sp2 means more withdrawing. Withdrawing, they destabilize the carbocation, right? So stability of B is more than that of A. Yes? Right? Moving ahead. Moving ahead. Look at this one. CD3, CH3, CT3. Plus I showing. Even this is plus I showing. Even this is plus I showing. Now, which one is more plus I showing? CT3 is more plus I showing. Then CD3, then CH3. And plus I showing group, they stabilize the carbocation. So, stability of C will be maximum, followed by what? Followed by A, followed by B. This is the stability order. Oh, yes. Welcome to the night mode. Welcome to the night mode. Welcome to the night mode. Okay. Look at the next one. Look at the next one, people. Look at the next one. Carbon carrying positive. Here carbon is carrying positive, carbon carrying positive, right? Over here, nitro group is attached. Here fluorine is attached. Here no such group, no withdrawing group is attached as such, right? Perfect. So this shows minus I. This shows minus I. And minus I groups, they destabilize the carbocation. Here you do not have any electron withdrawing group. So stability of A is maximum. Now, this is more withdrawing. If this is more withdrawing, it will destabilize the carbocation to the maximum. So B at the end, here it's going to be C. So ACB is the order. ACB is the order. Yes. ACB is the order. Look at the next one. Look at the next one. Look at the next one. I think this is the question which we already solved. C carrying positive, here positive. So 1 plus I showing group here. Over here 2 plus I showing groups. Here you have got 3 plus I showing groups, right? So stability order will be like this because plus I showing groups, they stabilize the carbocation, right? Now, since I did not teach you hyperconjugation or anything yet, I'm solving the equation directly on the basis of inductive effect. Now, this particular carbon carrying positive, it's getting electrons from one side. This particular carbon carrying positive, it's getting electrons from 3 sides. This particular, it's getting electrons from 2 sides, right? Perfect, right? So where will be the positive charge compensated the maximum? Positive charge is compensated the maximum here, right? If the positive charge intensity is decreased here, the maximum decrease in the intensity of positive charge is here, right? So it will be more stable. So 2 will be more stable than that of 3, and at the end it's going to be 1. Now CH3, CH2D, deuterium, CHD2, CD3 positive, right? More the D's, more is the stability, right? Nitro, CNF, nitro, CNF, all are electron withdrawing. So minus I. The one which shows lesser minus among the 3. The one which shows lesser minus I among the 3. Which one shows lesser minus I? So third shows lesser minus I. So its stability will be more, followed by 2, followed by 1. Right? Perfect. I believe you are able to solve these questions easily. Now, one more. Among these two species, which one is more stable? Can you let me know? Among these two species, which one is more stable? Carefully look. Sulfur carrying negative, oxygen carrying negative. Rest everything is same. This part is same, even this part is same. Sulfur carrying negative, oxygen carrying negative. You tell me the answer. Sulfur and oxygen, they belong to same group. Same group means VCD, volume charge density. Right? Volume charge density. Sulfur, more size, less VCD. Less VCD means more stability. So this is the stability order, right? Perfect. This question we already solved. This is your sp hybridized carbon carrying negative. This is your sp3 hybridized nitrogen. Right? This is your sp3 hybridized nitrogen. Perfect. Now you tell me, which one is more electronegative? Which one is more electronegative? sp hybridized carbon is more electronegative. Negative charge on an electronegative element is considered to be stable. So this is the stability order. Done? Perfect. Perfect. Tell me the order of these questions. I think, yeah. Okay, now these are not your carbocations. These are not your carbocations. These are your carbanions. Carbon carrying negative, carbon carrying negative, carbon carrying negative. Carbanions are stabilized by electron withdrawing, minus I showing. Carbanions are stabilized by minus I showing groups. Yeah? Now, CH3, it's plus I, CN, minus I, NO2, minus I. Minus I showing groups, they stabilize the carbanion. Now, which one shows more minus I? Nitro. Nitro shows more minus I. So C, then B, then A. This is the order. Right? Guys, keep on telling me the answers in the chats. I'm looking at your chats. Look at the next one. Look at the next one. All these are carbanions. This shows minus I. Right? Even this fluorine shows minus I. Perfect. CD3, it shows plus I. And since these are carbanions, carbanions are stabilized by electron withdrawing. So there is electron withdrawing, this electron withdrawing. Now, which one is more electron withdrawing? NF3 positive is more electron withdrawing. It shows more minus I, right? So A is more stable, followed by B, followed by C, right? Done and dusted? Done and dusted? Now, look at the other cases. Look at the other cases. Just a second. Just a second, people. Just a second. Just give me a second. Okay. Look at this particular case. Again, these are carbanions. Carbon carrying negative, negative, negative. Tell me, where is the stability maximum? Where the stability is maximum? I need the answer. I need the answer. Where is the stability maximum? Whatever concepts I gave you, use those concepts only, nothing else. I'm going to give you the break after this inductive effect is done. Quickly, quickly. What do you think? See, this is oxygen. It will be withdrawing electrons. Here the oxygen is comparatively close, right? Here there is no oxygen. Wherever oxygen is close, wherever withdrawing group is close, there only carbanion stability is maximum. So B will be maximum stable, followed by A, followed by C, right? This question, I believe you should easily be able to solve. Sulfur carrying negative, oxygen carrying negative, right? Sulfur carrying negative, oxygen carrying negative. Sulfur and oxygen, they belong to same group. VCD plays a role. This has got less VCD. Less VCD means more stability. So negative charge is more stable in this. So A is more stable than B. A is more stable than B. Now compare B and C. Compare B and C. A is more stable than B. Compare B and C now. Oxygen carrying negative, nitrogen carrying negative. Oxygen, nitrogen, they belong to same period. In same period, electronegativity plays a role. Negative charge is more stable and more electronegative. Negative charge is more stable and more electronegative because oxygen is more electronegative. So B is more stable than C. B is more stable than C. So order has to be A, B, and then C. When you compare these two, you took VCD into consideration. When you compared these two, you took electronegativity into consideration, right? Since they belong to same period, electronegativity plays a role. Negative charge is more electronegative and more, negative charge is more stable and more electronegative. And at the end, it will be carbon carrying negative, right? So this has to be the order ABCD. Right, guys? ABCD has to be the order. Perfect. Now, guys, look at this particular question. What do you think? What do you think? Quickly. Okay. Sorry. Quickly. What is the answer of this question? What is the answer of this question? That was my previous organization, by the way, where I used to work. Okay. Quickly tell me the answer of this particular question. Acidic strength. Acidic strength. Acidic strength. Acidic strength. If you remember, guys, if you remember, just a second. Acidic strength. I hope you remember that table which I gave you. I hope you remember the table which I gave you. Acidic strength. Acidic strength. Strength of acid is directly proportional to stability of conjugate base, and conjugate base is stabilized by minus I. So in short, I would say minus I groups, they increase the strength of acid. Minus I groups, they increase the strength of the acid, right? Plus I groups, they decrease the strength of the acid. Now you're going to give me the answer. Since you know it already, you are going to give me the answer now. Quickly, guys. Just a second. It was slide number 60. I believe this is slide number 60. Yes. Okay. So first of all, identify the site from where hydrogen is going to donate. Hydrogen is going to go away as H positive. This is the site from where hydrogen is going to leave as H positive. This is the site from where hydrogen is going to leave as H positive. This is the site from where hydrogen is going to leave as H positive. Here you have got electron withdrawing, right? Here you have got electron donating, electron withdrawing groups. They increase the strength of the acid. So I would say A strength will be maximum, followed by B, followed by C, right? Now, majority of the students will do a mistake, I believe, here in this question. Tell me, which one is more acidic? I think a lot of students will do a mistake here. Quickly, which one is more acidic here? Guys, after looking at this question, do not straight away C plus I minus I plus M minus I. Do not do that. Do not do that. Why? Because this is carboxylic acid. This is carboxylic acid. This is phenol. This is phenol. And generally, you know it, carboxylic acids are stronger acids than phenols. Carboxylic acids are stronger acids than phenols. So definitely A and B is going to be more acidic than C and D. Okay. A and B is going to be more acidic than C and D. Now, among A and B, this is minus I showing, this is plus I showing. Withdrawing, electron withdrawing group, it increases the strength of acid, right? So A will be maximum acidic, followed by B. Now, among C and D, this is withdrawing, there is no withdrawing group. So I'll say C, then D. I believe this particular question is done again, right? Agreed? Right, guys? Okay. What about this one? What about this one? First of all, look at the site from where hydrogen is going to go away as H positive. I identified the site, right? Over here, 1 fluorine, 2 withdrawing, 3 withdrawing. More the withdrawing groups, more the acidic strength. More the withdrawing groups, more the acidic strength. Done and dusted. Look at the next one. This is NF3 positive. Okay. Okay. First of all, this is your phenol basically. This is phenol, but this is carboxylic acid. Carboxylic acids are stronger acids than there are phenols. So C will be maximum acidic. Now among A and B, strength of acid is directly proportional to minus I. Right? Minus I. This shows more minus I. This is more withdrawing. This more withdrawing. So after C, I'll prioritize A. Then I'll prioritize B. Right? I believe this is also clear. I believe this is also clear. Okay. Okay. What about this particular question? 1 or 2? 1 or 2? See, from here, hydrogen is going to go away as H positive. From here, hydrogen is going to go away as H positive. Perfect. Now, 1, 2. At carbon number 2, there is withdrawing. 1, 2, 3. At carbon number 3, there is withdrawing. So, where will the fluorine show more prominent minus I? Where the distance is less. Where the distance is less. So, in the first case, more withdrawing. More withdrawing means more acidic strength. Right? Okay. Now, first of all, this is the site from where hydrogen is going to go away as H positive. Perfect. Now, you know, strength of acid is directly proportional to stability of conjugate base. Perfect. Stability of conjugate base. Right? Or directly tell me one thing. Which ring over here will be more withdrawing? Angle strain concept. Angle strain. 3-membered, 4-membered, 5-membered, 6-membered. 3-membered ring. More angle strain, more electronegativity, more withdrawing. More withdrawing. If it is more withdrawing, that means it will stabilize the conjugate base the maximum, right? So this is the stability order of the conjugate base as well as the stability as well as the order of the strength of the acids, right? Okay, here you might do a mistake. Here you might do a mistake. You might do a mistake. In 1 and 2, which one is more acidic? In 1 and 2, which one is more acidic? Tell me that. In 1 and 2, which one is more acidic? Tell me that. Among 1 and 2, which one is more acidic? Quickly. Are you sure? Are you sure? Among 1 and 2, which one is more acidic? Have a look, guys. First of all, make their conjugate bases. Take hydrogen out as H positive. This will be CF3 negative, right? Take hydrogen out as H positive. This will be CCl3 negative. These are the conjugate bases. See, these are your acids and these are their conjugate bases. Now check the stability of these conjugate bases. Check the stability of these conjugate bases. Have a look, guys. Try to understand. Carbon carrying negative, right? But this particular carbon is attached to 3 fluorine atoms, right? This is carbon and you have got 3 fluorine atoms. Perfect. Look at this particular carbon. It is attached to 3 chlorine atoms. 3 chlorine atoms. These are the conjugate bases basically which we have. Now tell me one thing. In the fluorine, do you have any vacant orbitals? In fluorine, are there any vacant orbitals? No, right? In chlorine, if you remember chlorine, in chlorine there are vacant d orbitals. Chlorine configuration is 3s2, 3p5, but there is 3d as well, 3d0, there are vacant d orbitals. So if there are vacant d orbitals in chlorine, can I say this? If there is a vacant d orbital in the chlorine, can I say it can show the back bonding? It can show the back bonding. If it shows back bonding stabilizes the carbanion. Or I would say back bonding, it stabilizes your conjugate base. So which conjugate base is more stable? This conjugate base is more stable. More stable the conjugate base, stronger the acid. More stable the conjugate base, stronger the acid. Look at the next one. Take hydrogen out as H positive, negative charge. Hydrogen out as H positive, negative charge, right? Perfect. Now, this is sulfur. Sulfur outermost configuration, 3s2, 3p4, and there is 3d as well, containing 0. Oxygen is simple, 2s2, 2p4, right? There is no d, there is no vacant orbital. Here you have got vacant orbital. If there is vacant orbital, there is a chance of back bonding, and back bonding stabilizes the conjugate base. So wherever the conjugate base is more stable, that acid is going to be stronger. I believe this is clear to everyone. Yes? All right, guys. So let's move on then. Let's have a look on what resonance exactly is all about. My dear students, before letting you know the exact meaning of resonance, we should know first of all which kind of molecules do exhibit this property. Which of the molecules can show resonance? Which of the molecules cannot show resonance? And after that, I'll let you know what this resonance exactly is. So my dear students, I'm going to write one simple statement over here. Try to understand. The statement is like this. Whenever a true structure of a molecule cannot be drawn, whenever true structure of a molecule cannot be drawn, or if any structure cannot explain all its properties, we say the molecule exhibits resonance. We say a molecule exhibits resonance. This is one very, very, very important point. My dear students, whenever you will be unable to draw true structure of the molecule, whenever you'll be unable to draw the actual structure of the molecule, or if any structure of the molecule will not be able to explain all its properties, if any structure of the molecule will not be able to explain all its properties, at that point of time, we say that the molecule exhibits resonance. Now, what is meant by it? Let's try to understand this a bit more in detail. Try to understand, guys. First of all, I'm sure every one of you would have come across the term benzene, right? Benzene, every one of you would be knowing. Now, my dear students, experimentally it has been observed. Experimentally it has been observed that in benzene, all the bond lengths are equal. Experimentally it has been observed in case of benzene, all the CC bond lengths are equal. All the carbon-carbon bond lengths are equal. This has been observed experimentally, point number one. And at the same time, it has been observed that benzene, it does not behave like a normal alkene. It has been observed that, it has been checked, my dear students, that in case of benzene, all the carbon-carbon bond lengths are equal. Experimentally, it has been observed. And apart from that, it has been observed that in case of benzene, benzene does not behave like a normal alkene. Correct? If I ask you guys, what is the structure of benzene? Some of you will come up with this particular structure. Some of you will come up with this particular structure, right? And some of you will come up with this particular structure. Some of you will come up with this particular structure. If I ask you what is the structure of benzene, some of you will say this is the structure of benzene, and some of you will say this is the structure of benzene. Now, my dear students, let me call this as carbon number 1. Let me call this as carbon number 2. This is 3. This is 4. This is 5. This is 6, right? Do you know one thing? That bond order is directly proportional to bond strength, right? Which is inversely proportional to bond length. I believe every one of you will be knowing this. Bond order is directly proportional to bond strength, which is inversely proportional to bond length, right? Now, guys, try to understand. If you look at this particular structure, this is the structure which you gave me about benzene, right? Some of you said this is the structure of benzene, and some of you said this is the structure of benzene. If you look at the first structure, in the first structure, there is a double bond between this carbon and this carbon. There is a double bond between this carbon and this carbon. So, between carbon number 1 and carbon number 2, there is a double bond as per this particular structure, right? Between carbon number 2 and carbon number 3, there is a single bond. Between carbon number 2 and carbon number 3, there is a single bond. Now, if I ask you, as per this particular structure, there is a double bond between these two. There is a single bond between these two. As per this structure, will this particular bond length and this particular bond length, will these bond lengths be same or different as per this structure? I'll say C1, C2. C1, C2 bond length won't be equal to C2, C3 bond length. Correct? Very simple. See, if you look at this particular structure, as per this structure, there is a double bond between 1 and 2. There is a single bond between 2 and 3. If there is a double bond and a single bond, definitely their bond lengths won't be equal, right? But my dear students, already we know something about benzene. We know in case of benzene, all the CC bond lengths are equal. But as per this structure, CC bond lengths are not coming out to be equal. This bond length as per the structure will be less, and this bond length as per this structure will be more, right? So as per this structure, the CC bond lengths are not equal. So if I ask you, is this structure able to explain all the properties of benzene? You'll directly say no. This structure is not able to explain all the properties of benzene, because we know in case of benzene, all the CC bond lengths are equal. But as per this structure, CC bond lengths are coming out to be different, because somewhere there is a double bond, somewhere there is a single bond, right? Similarly, if you look at this particular structure, If you look at this particular structure, let me call this as 1, let me call this as 2, this is 3, this is 4, this is 5, this is 6. As per this structure, between 1 and 2, there is a single bond, right? And between 2 and 3, there is a double bond. Perfect. So if I ask you, as per this particular structure of benzene, will C1C2 bond length, be same as that of C2C3? You will say no, right? They won't be equal. As per this particular structure, they won't be equal. Perfect. Because as per this structure, there is a single bond here, there is a double bond here. Perfect. Right? So if I ask you, are these two structures able to explain all the properties of benzene? These structures are not able to explain all the properties of benzene. This particular structure is not unable to explain all the properties. Even this particular structure is unable to explain all the properties of benzene. Whenever you cannot draw the true structure of the molecule, or if any structure will be unable to explain all the properties of the molecule, at that point of time, we say the molecule exhibits resonance. So can I say benzene will be exhibiting resonance? Absolutely, benzene will be exhibiting resonance. Absolutely, benzene will be exhibiting resonance. Right? Because none of the structures of benzene are able to explain all its properties. And any such molecule whose structure cannot explain all its properties, we say that molecule exhibits resonance. Okay? Clear, guys? So benzene is the molecule which exhibits resonance. Perfect. Now, what this resonance exactly is all about? Before talking about resonance, there are few points which you need to know. Before understanding what this resonance is, there are few things which you need to know, my dear students. Have a look exactly what those things exactly are. Have a look exactly what those things exactly are. Have a look, people. Just a second. Let me create a space over here. Let me create a space over here. Okay. My dear students, in order to understand the term resonance, you should know first of all what is a localized electron pair. You should know first of all what is a localized electron pair. And how do we define the localized electron pair? When an electron pair is shared only between two atoms. If an electron pair is just shared between two atoms, we call that particular electron pair as a localized electron pair. For example, this electron pair, it is just shared between A and B. This particular electron pair, it is just shared between A and B, right? Any such electron pair which will be just shared between two atoms, you call that particular electron pair as the localized electron pair. You'll be calling that as the localized electron pair. When the electron pair is shared by just two atoms, you'll be calling that as the localized electron pair. Now, what will be the meaning of delocalized electron pair then? What will be the meaning of delocalized electron pair? My dear students, any electron pair which will be shared, between more than two atoms. Any electron pair which will be shared between more than two atoms, that is what you will be calling as delocalized electron pair. For example, have a look. Let's say I've got a molecule. This is the molecule. Let's say this is one more electron pair which I'm keeping between A and B. This is one molecule, right? This is one electron pair which I've kept between A and B, correct? Now, my dear students, for example, if I draw the structure of this molecule again, and by chance, if the same electron pair which was earlier between A and B, now if the same electron pair is between B and C. Earlier, this electron pair which I'm representing by cross, it was between A and B. Now, in one more structure of the same molecule, the same electron pair is between B and C. So the first structure is telling you that this particular electron pair is shared between A and B. The second structure is telling you that the same electron pair is shared between B and C. Now tell me whether this electron pair is shared by two atoms or three atoms. I'll say this particular electron pair is shared among three atoms. Any such electron pair which will be shared by more than two atoms, you call that particular electron pair as delocalized electron pair. So this particular electron pair which we have, it is not shared only between two atoms, it is shared between three atoms, and any such electron pair which will be shared by more than two atoms, you call that electron pair as the delocalized electron pair. Correct? Right? Now, my dear students, the point is, which electron pair will be called as delocalized electron pair? The point is, which electron pair will be called as delocalized electron pair? A simple and basic statement. A high energy electron pair can be considered as delocalized like your pi electrons. Now, what is meant by this statement? Since I told you, delocalized electron pair is that electron pair which is shared between more than two atoms. Now, which electron pair can be delocalized? My dear students, over here it's mentioned, high energy electron pair can be delocalized. Now, what is high energy electron pair? You must be thinking, what is high energy electron pair? Let me tell you first of all, what is high energy electron pair? Try to understand exactly what is high energy electron pair. Have a look. For example, imagine this is an s orbital of one atom. Imagine this is s orbital of one more atom. Right? Now, my dear students, when these atomic orbitals will approach each other, what will happen? Will there be axial overlapping? Will there be head-on overlapping? Absolutely, there will be head-on overlapping. Absolutely, there will be head-on overlapping, right? And due to head-on overlapping, which bond is formed? It is the sigma bond which gets formed due to head-on overlapping. So this particular bond which got formed here by the axial overlapping, this particular bond I'm calling as sigma bond. Correct? That's something which I call a sigma bond. Now you tell me one thing. The sigma bond which gets formed over here, right? This particular common electron density, can I say this particular common electron density, it is under the influence of both these nuclei directly? This particular electron density is under the influence of both these nuclei directly, right? Now, try to understand one more thing. Let's say this is your p orbital. This is one more p orbital. I'm keeping their axes parallel. If I keep their axes parallel, tell me, will there be axial overlapping or parallel overlapping? There will be parallel overlapping. And due to parallel overlapping, which bond gets formed? Pi bond gets formed. So what will happen? These lobes, they'll bend towards each other and there'll be parallel overlapping, right? So this is your p orbital and this is your one more p orbital. And this particular electron density, right? This common electron density, it results in the formation of what? It results in the formation of pi bond. Perfect. Now, how do I make it at the end? Try to understand. This is the nucleus. Even here you have got the nucleus. Perfect. So, let me make it like this. Let me make it like this. This is the common electron density at the top. This is the electron density here, right? This is the nucleus, this is the nucleus. So, in between, I would say, over here there'll be a plane. Over here there'll be a plane on which electron density won't exist. And you call this particular plane as nodal plane. I hope you know that. Right? Now, my dear students, just tell me, just compare these two. Just compare these two. This is a plane on which no electron density lies. Electron density lies on the top and below the plane. Electron density lies above the plane and below the plane. Correct? Now tell me whether this electron density, which you call as pi electron density, right? Whether this electron density is under the direct influence of nucleus. Here the electron density is not under the direct influence of the nucleus. Here the electron density was under the direct influence of the nucleus. Now tell me, which electron density among these two, sigma electron density or pi electron density, which electron density will be experiencing more force of attraction by the nuclei? Can I say this electron density will be experiencing more force of attraction? Can I say this particular electron density will be experiencing more force of attraction by the nuclei because it is under the direct influence of these nuclei, right? Can I say this electron density, this pi electron density, it is under less force of attraction? It is subjugated to less force of attraction. That electron density which is subjugated to less force of attraction, that electron density is something which you call as high, right? That electrons, those electrons which are under less force of attraction by the nucleus, which are subjected to less force of attraction by the nuclei, that is something which you call as high energy electron density. That is something which you call as high energy electron density. So what is the high energy electron density? Why did I tell you all this? Because the point was very simple. Initially, I told you, first of all, what is a delocalized pair? Delocalized electron pair is that electron pair which is shared by more than two atoms. Now, the point was which electron pair can be delocalized? I told you high energy electron pair can be delocalized, like your pi electrons, right? Like your pi electrons. Is this clear? High energy electron pair, that electron pair which will be subjugated to less force of attraction by the nuclei, that is something which you call as high energy electron pair. And that high energy electron pair, can be delocalized. Yes? Is this point clear? Is this point clear? Guys, try to understand carefully what I'm saying. First, I made you clear what is delocalized electron pair. It is that electron pair which is shared by more than two atoms. Now the point was which electron pair can be delocalized? It is the high energy electron pair like your pi electron pair which can be delocalized. And delocalization of high energy electron pairs. Delocalization of high energy electron pairs is something which is what you call as resonance. Did you get the idea of what this resonance is all about? Did you get the idea of what resonance is all about? So resonance is just defined as the delocalization of high energy electron pairs like your pi electron. Right? Let me know once in the chats if it is clear. Let me know once in the chats if it is clear. The delocalization of high energy electron pairs like your pi electrons. Right? That is something which is what you call as resonance. Perfect. Now guys, before making you understand, before showing you how do we draw the resonating structures, etc., etc., there is one approach which you need to learn. Right? There is one approach which you need to learn. That is something which you call as orbital approach of resonance. But again, before making you understand the orbital approach of resonance, there is one more thing which I want to let you know. Your pi electrons, which are your high energy electrons, right? They can be delocalized. These pi electrons are exactly of two types. One you call as the real pi electrons, another one you call as differential pi electrons. If I talk about your pi electrons are of two types basically, right? Pi electrons are the ones which are subjugated to less force of attraction by the nuclei, right? These are high energy electron pairs, right? And these high energy electron pairs get delocalized basically. Now, these pi electron, these are of two types. One is real pi, one is differential pi. What are real pi electrons? Real pi electrons are the ones which are present either in double bond or triple bond. Real pi electrons are the ones which are present in either double bond or triple bond. Whereas your differential pi, lone pair you call as differential pi, or negative charge with an unshared pair of electrons. Lone pair and negative charge with unshared pair of electrons. These are what you call as differential pi electrons. These are what you call as differential pi electrons. These are what you call as differential pi electrons. And my dear students, there is a particular energy order of these real pi and differential pi electrons which you need to remember. There is one energy order which you need to remember regarding these real pi electrons and differential pi electrons. And what is that energy order? See, negative charge with unshared pair of electrons. This will be always having more energy, followed by the lone pair, followed by the pi electron pair of this double bond, followed by these two pi electron pairs of these triple bonds. Just remember this directly. First of all, what are these electron pairs? What are these electron pairs? What this real pi is all about, what this differential pi is all about. These are the types of pi electrons. Pi electrons are high energy electrons, and only high energy electrons, they get delocalized. I mean, your high energy electrons, they get delocalized. They show delocalization, right? They show delocalization. Now people, now let me make you understand the actual concept of resonance. Now let me make you understand the actual concept of resonance. Try to understand. First of all, if I ask you, what is the structure of benzene? Some of you will come up with this structure. Some of you will come up with this structure, right? Okay. Now, if you exactly have a look on how this structure is formed actually, how the structure is formed actually. If you have a look on how this particular structure is formed, can you do that? Can you make the orbital diagram of this particular benzene? Can you make the orbital diagram of this particular benzene? Or I'll do one thing. I'll make it comparatively simple. Let me make it like this. Let me make it like this. Right? I asked you what is the structure of benzene. Some of you told me this is the structure of benzene. Now I'm going to explain how this structure was formed basically. How this structure was formed. First of all, my dear students, if you look at this particular carbon, can you let me know its hybridization? This particular carbon, its hybridization. See, 1 sigma, 2 sigma, and 1 more sigma with hydrogen, 3 sigma. So it's sp2 hybridized. Even this is sp2, this is sp2, this is sp2. Every carbon here is sp2. Now, my dear students, what is the outermost configuration of carbon? It is 2s2, 2p2. You know that, right? This is your 2s orbital, and this is your 2p. These are your 3 2p orbitals. Now, every carbon is sp2 hybridized. Every carbon is sp2 hybridized. So, can I say every carbon will contain one pure p orbital as well? Absolutely, every carbon will contain one pure p orbital as well. So, basically, the hybridization involved here is sp2, right? The hybridization involved here is sp2, and I would say there will be one pure p orbital present at every carbon. And my dear students, let me tell you, in case of sp2, hybridization, what is the geometry as per sp2 hybridization? It's trigonal planar. It is trigonal planar, right? You must be knowing this. This is trigonal planar. What is meant by trigonal planar geometry? What is meant by trigonal planar geometry? See, if I talk about this particular carbon, it is attached with hydrogen as well on this side, right? First of all, the carbon has undergone sp2 hybridization, right? Which leads to the formation of 3 hybrid orbitals. So there'll be 3 sp2 hybrid orbitals, and apart from that, there'll be 1 pure p orbital as well. Perfect. Now, my dear students, these sp2 hybrid orbitals, what they have done? One of the sp2 hybrid orbital has done the overlap, formed the sigma bond. One more has formed one more sigma bond. One more has formed one more sigma bond. Correct? Right? Perfect. And this particular carbon, it has got p orbital as well. It has got p orbital as well. And that p orbital will be perpendicular to the plane containing these bonds. See, first of all, this bond, this bond, this bond, they're present on the same plane. They're present on board. Now, perpendicular to the board, there'll be a p orbital. Perpendicular to the board, there'll be a p orbital. So, this is a p orbital here. Even this has got its p orbital. 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 Even this has got its p orbital. You know it now. Right? Right, guys? So, if I talk about benzene, all the carbon atoms are sp2 hybridized, and every carbon has got one pure p orbital as well. Perfect. Now, guys, try to understand. Try to understand. If I exactly want to make the orbital diagram, how exactly I'm going to make it? Try to understand it carefully. Try to understand it carefully. Let me make a structure like this. Let me make a structure like this. I told you every carbon has got a pure p orbital. Every carbon has got a pure p orbital. Right? Every carbon has got a pure p orbital. As per this structure, there's a pi bond between these two carbon atoms. There's a pi bond between these two carbon atoms. How a pi bond gets formed? Pi bond gets formed by the parallel overlapping, right? Can I say as per this particular structure, these two orbitals have parallelly overlapped. They have parallelly overlapped and formed a pi bond here. Similarly, p orbital of this and p orbital of this, they have parallelly overlapped and formed a pi bond, right? Similarly, these two have parallelly overlapped and formed a pi bond, right? As per this structure, there's a pi bond here. There's a pi bond here. That means the p orbital of these two carbon atoms would have parallelly overlapped and formed a pi bond. Here a pi bond, here a pi bond. Correct? Now, my dear students, one more thing. If I ask you what is the structure of benzene, a lot of you told me this is the structure of benzene, but there will be few students who will tell me that this is not the structure of benzene. This one is the structure of benzene. A lot among you will tell me this is the structure of benzene. Now, can you tell me how this structure would have got formed? If you look at its orbital approach, see, every carbon is sp2 hybridized, right? And there is a pure p orbital with every carbon here, right? So if you make its structure, or let me make its structure over here. Let me make its structure over here. Let me make its orbital diagram over here. Every carbon has got a pure p orbital. Every carbon has got a pure p orbital. Now, people, look at this particular structure. There's a pi bond between these two. What does that mean? That means the p orbital of this and p orbital of this, they would have parallelly overlapped and formed a pi bond. So I would say, as per this particular structure, this orbital and this orbital, they have parallelly overlapped, right? Similarly, p orbital of these two, they would have parallelly overlapped. That means these two would have parallelly overlapped, right? Similarly, these two would have parallelly overlapped. Perfect. These two would have parallelly overlapped. Correct? So I gave you two structures of benzene. One structure of benzene is this, one structure of benzene is this, right? This particular structure of benzene is formed when these orbitals overlap. And this particular structure of benzene is formed when these orbitals overlap, right? Perfect. But is this structure able to explain all the properties of benzene? No. Is this particular structure able to explain all the properties of benzene? No. But I would say, some of the properties of benzene, this structure will be explaining. That means this structure will be explaining. And some of the properties of benzene, this particular structure will be explaining. Right? Some of the properties of benzene, this structure will be explaining. And some of the properties of benzene, this particular structure will be explaining. So basically, related to benzene, some of the information you are getting from this particular structure and some of the information you are getting from this particular structure. If you combine the information, what do you get? See, guys, this particular structure is telling you that these two orbitals have parallelly overlapped. But this particular structure is telling you these two have not overlapped. These two have overlapped. Right? So in the actual structure of benzene, what would have happened? In the actual structure of benzene, what would have happened? I told you guys, some of the information this is giving us. We have to compile both the informations. Right? We have to compile both the informations. Now try to understand. As per this particular structure, overlap is between these two. But as per this structure, overlap is between this and this. Right? As per this structure, overlap is between this and this. But as per this structure, overlap is between this and this. Right? As per this particular structure, overlap is between this and this. Parallel overlap. As per this particular structure, overlap is between this and this. So we compiled all the informations from these two structures. These are the proposed structures of benzene. Which we gave. And after giving the proposed structures of benzene, we compiled all the information. We are merging the information and we got something like this. Right? We got something like this. So this particular structure, try to understand. In this particular type of structure, if you see this particular structure, this particular structure is telling you that in case of benzene, there is the simultaneous overlap. There is a simultaneous parallel overlap of these p orbitals. right? This particular structure is telling you there is a simultaneous parallel overlap. There is a simultaneous parallel overlap of p orbitals. Perfect. And my dear students, let me tell you one simple thing. Let me tell you one simple thing. The overlap of orbitals, the parallel overlap of orbitals can be P or D, is something which is called as resonance basically. The parallel overlap of your, as in case of benzene, the parallel overlap of your p orbitals, right? In such a way that the electron density is uniform throughout. That the electron density is uniform throughout is something which you call as benzene. Sorry, which is something which you call as a resonance. Perfect. So did you get the idea of what I said? Did you actually get the idea of what I said? Did you actually get the idea of what I said? Now we will try to understand. This is the structure which we propose about benzene. This is the structure which we propose about benzene. We compiled the information. We got the actual structure of benzene. In the actual structure of benzene, these p orbitals are simultaneously and partially overlapping. These are simultaneously and partially overlapping. Perfect. Now, let me tell you this particular structure. How you are going to denote it. 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 If I ask you, will you be able to do that? Will you be able to do that? Tell me one thing. As per this structure, there should be double bond between these two atoms. As per this structure, there should be single bond between these two atoms. So merge the information. Merge the information. Merge the information. This structure is telling you there should be a double bond between these two. This structure is telling there should be a single bond between these two. But in the actual structure, it will be neither pure single bond nor it will be pure double bond. It will be partial double bond here. It will be a partial double bond here. Similarly, in the actual structure, it will be partial double bond here. In the actual structure, it will be partial double bond everywhere. It will be partial double bond everywhere. That is the reason why in benzene, all the bond lengths are equal. That is the reason why in benzene, all the bond lengths are equal. Got it? My dear students, this particular structure is what you call as the actual structure of benzene, or you can call it as the resonance hybrid as well. This actual structure of benzene is something which you call as a resonance hybrid. Resonance hybrid. And these particular structures, these are the proposed structures which we gave about benzene, right? This is something which we call as canonical structures. This is one of the canonical structure of benzene, or you can call it as the heretical structure, or you can call it as the resonating structure. Perfect. Similarly, this one. This either you will be calling as canonical structure or resonating structure or theoretical structure. Now you tell me one thing which is very important here. One thing which is very important here. My dear students, in this canonical form, if I ask you whether the bonding is localized or delocalized, here in this particular structure, you can categorically say there is a pi bond between these two. You can say there is a pi bond between these two. There is a pi bond between these two. Right? But if I ask you, where is the pi bond here? It can be here, it can be here, it can be here, it can be here. So where is the delocalization actually present? Is the delocalization present in the canonical form, or is the delocalization present in the hybrid? Delocalization is present in the hybrid. Right? Delocalization is present in the hybrid. Got it? Delocalization is present in hybrid. Here you cannot say with 100% probability that your pi electron pair is here or here or here or here. It is delocalized. It is delocalized. But here in this proposed structure, in this canonical form, you can categorically say your pi bond is here, pi bond is here, pi bond is here. Similarly here, pi bond is here, pi bond is here, pi bond is here. So those proposed structures which give you the idea about the localized bonding, those proposed structures are what we call as canonical structures. But this particular structure, what does it contain? It contains delocalization of pi electrons. And this is something which we call as resonance hybrid. Is this clear? Is this clear, people? Say yes or no in the chats if you got to know this. So from now onwards, if I ask you, is delocalization present in the hybrid? Or delocalization is present in the canonical structure? Or delocalization is present in both? What do you think? I would say delocalization is present in the hybrid. Delocalization is not present in the canonical form. Right? So my dear students, the partial overlap of these p orbitals, is something which we call as resonance. Now, what happens due to resonance, if I ask you? What happens? What is the consequence of resonance? My dear students, due to resonance, what is the resonance? Delocalization. Due to delocalization, will the pi electron density be subjugated to only 2 nuclei or more than 2 nuclei? I'll say due to delocalization, pi electron density, it will be subjected under the influence of more than 2 nuclei. If the pi electron density is subjected to more than 2 nuclei, what will happen? Force of attraction on the electron density will increase. If force of attraction increases, what will happen? Will stability increase or decrease? Force of attraction increases means energy decreases. Energy decreases means stability increases. Do remember this. Yeah? Perfect, guys? So, in short, what happens due to delocalization? Due to delocalization of these high energy electrons, due to delocalization of these pi electrons, due to the delocalization of this pi electron density, I would say this pi electron density, it comes under the influence of more than 2 nuclei, due to which force of attraction increases. If force of attraction increases, energy decreases and stability increases. Right? Perfect. That is the reason if delocalization is in this particular hybrid, if delocalization is here, that means its energy will be the least and its stability will be the maximum. Right? So do remember, energy of the resonance hybrid is the least and its stability will be maximum, because over here resonance is present, over here delocalization is present. Among these two, resonance is not present, delocalization is not present. I hope this is clear. So guys, in nutshell, have a look. That structure which contains localized bonding, wherein you can clearly say that pi electron is between these two carbons. So that structure which contains localized bonding, but cannot explain all the properties of the molecule. That's what you call as theoretical structure or resonating structure or canonical form. Okay? Or canonical form. Perfect? Right? Okay, one more thing. Look at this particular statement. None of the canonical structures is the true structure of the molecule. You saw it. None of the canonical structure is the actual structure of the molecule. Perfect? It is just from the canonical structures we get some information. We compile that information and make the actual structure of the molecule, which is something we call as a resonance hybrid. And in that resonance hybrid, basically, your delocalization is present, your resonance is present. And due to delocalization, as I told you, due to delocalization, what happens? The high energy electrons, they come under the influence of more than 2 nuclei, due to which force of attraction increases, energy decreases, stability increases. As simple as that. Right? So the structure which contains delocalized bonding but can explain, the properties of the molecule is something which you call as a resonance hybrid. So this is basically your resonance hybrid of benzene. This is the hybrid of benzene. I believe this is clear to everyone. Right? Perfect. And due to delocalization, what happens? Can I say partial pi bonds are formed? Due to delocalization, what did you see? Due to delocalization, what happened? Partial pi bonds are formed, right? You saw that. You saw that. Okay? Partial pi bonds are formed. Now, my dear students, this is something which all of you must be knowing. See, over here, there's a single bond. It's a pure single bond. It is a pure double bond, and it's a partial double bond. It's a partial double bond. I'll say bond order here will be 1. I'll say bond order here will be 2, and bond order here will be greater than 1 and less than 2. Correct? Yes. And you know, your bond order, it is inversely proportional to bond length, right? Perfect. So bond length, in case of single bond, will be maximum, followed by partial double bond, followed by pure double bond. Correct? Yes. And you know, your bond order, it is directly proportional to bond strength. Wherever is the bond order maximum, bond order is maximum here, 2, pure 2. Its bond strength will be maximum, followed by partial double bond, followed by pure single bond. Right? All these things will be utilized. All these things will be used in the questions. But before doing the questions, there are few more things which I need to tell you related to resonance. If you ask me what are the conditions, what are the conditions for resonance? What are the conditions for resonance? This is again one more important point. What are the conditions for resonance? My dear students, for resonance, there should be presence of parallel p orbitals with high energy electrons coplanar to each other. Coplanar to each other. Coplanar to each other. For example, this is CH2, this is double bond, this is CH, this is a double single bond, this is CH2, and this is positive. Okay? This is the molecule which I made over here. My dear students, try to understand. If you ask me, what is the hybridization of this particular carbon? This carbon, it's forming how many sigma bonds? 2 with hydrogen, 1 with carbon. 2 with hydrogen, 1 with carbon. 3 sigma bonds. So it is sp2 hybridized. If it is sp2 hybridized, there will be a p orbital. There will be a p orbital. This one, it is also forming 3 sigma bonds, this carbon. Again, there will be p orbital. Right? Perfect. Now look at this particular carbon. It's again forming what? It's again forming 3 sigma bonds. There'll be a p orbital here. There'll be a p orbital here. And as per this particular structure, which 2 parallel p orbitals have overlapped? These 2 parallel p orbitals have overlapped and they have formed a pi bond. They have formed a pi bond. Right? Can you draw its one more structure? See, this is one of the canonical forms. It's one more canonical form. How will it look like? In one more canonical form, I would say these 2 p orbitals would have overlapped. So the pi bond would have been shifted over here. Pi bond would have shifted over here. Correct? Over here, as per this particular canonical form, these 2 orbitals have parallelly overlapped. But in one more canonical form, there would have been one more possibility that these 2 would have overlapped. These 2 would have overlapped. Correct? So what is the condition basically? Condition is there should be presence of parallel p orbitals with high energy electrons. Condition is there should be presence of what? There should be presence of parallel p orbitals with high energy electrons. Like you saw here, these 2 orbitals have parallelly overlapped and formed a pi bond. In one more canonical form, I would say these two would have, this is CH2, this is CH, and this is your CH2. For example, try to understand what I'm going to say. These are the pure p orbitals. So in one more canonical form, these 2 would have overlapped parallelly, right? These 2 would have overlapped parallelly. Perfect. And your pi bond should have been here as per this particular canonical form. Perfect. Now, if I ask you, is this the true structure? Is this the hybrid? This is not the true structure. This is not the actual structure of the molecule. Even this is not the actual structure of the molecule. This is giving me some of the information. This is giving me some of the information. If I compile the information, I'll get the actual structure of the molecule. Now, how the actual structure of the molecule will look like? Try to understand. Actual structure will be like this. This particle CH2, I'll put a single bond everywhere first of all. I'll put a single bond everywhere. Now, as per this structure, there is a double bond between these 2. But as per this structure, there is a single bond. But in the actual structure, there will be neither pure single nor pure double. So it will be a partial double. It will be a partial double here. As per this structure, there is a single bond. As per this structure, there is a double bond. But in the actual structure, neither pure single nor pure double. It will be partial. This structure is telling me that this carbon carries positive. right? Perfect. But this structure is telling me this carbon does not carry any positive. So let me write it as delta positive here. Now, this particular structure is telling me this carbon is carrying positive. This is telling me no, this carbon is not carrying positive. So I'll be writing it as delta positive. So this is something which I'll be calling as resonance hybrid. This is your hybrid actually. This is your hybrid. Now you tell me, is resonance, is delocalization present in first case, second case, or third case? Everyone in the chats. Is delocalization present in first case, second case, or the third case? Is delocalization present in the first case, second case, or third case? I want everyone to answer. Delocalization, first, second, or third? Delocalization is present in third. It is present in hybrid. Due to delocalization, your high energy electron pair, right? Due to delocalization, your pi electron pair, it would have come across more force of attraction, due to which its energy would decrease, stability would increase, right? Absolutely, guys. Wonderful. So do remember this particular case. There should be the presence of parallel p orbitals with high energy electrons, which must be coplanar to each other. And this is something which I already told you. Due to delocalization of pi electrons, the pair of electrons are subjugated to more force of attraction, due to which potential energy decreases, stability increases. Therefore, we say that resonance increases the stability. Therefore, we say that resonance increases the stability, right? Now, guys, there are a few more points related to resonance. Then we'll do a lot of questions based on these, okay? The first point, resonance hybrid. Resonance hybrid is always more stable, right? Because in the hybrid itself, delocalization is present. In the canonical forms, delocalization is not present. In the hybrid, delocalization is present. In the canonical forms, delocalization is not present. And wherever delocalization is present, wherever resonance is present, there only I would say stability is more, right? So do remember, resonance hybrid is always more stable because resonance is present in the hybrid, not in the canonical form, right? Told you already. Told you already. Okay. Second important point, all the canonical forms should have almost same energy. For example, you have got the molecule. You have got the molecule N. It's one of the canonical form is C1. It's one of the canonical form is C2. It's one more canonical form is C3. It has got 3 canonical forms, for example. It has got 3 canonical forms. Now, I will be calling them canonical forms of this M only if their energy is almost same. These 3 I'll be calling the canonical forms of this molecule only if the energy is almost same. For example, what are canonical forms first of all? These are proposed structures by us. So I can give one more canonical form, C4. For example, its energy is far, far, far greater than this. If energy of this canonical form is far, far, far greater than these 3, then I won't be considering this as the canonical form. All the canonical forms, first of all, canonical forms are proposed by us, right? And all the canonical forms, they should have what? They should have similar energy, almost same energy, right? They should have almost same energy. Okay? Almost same energy. Now, my dear students, one more thing. Out of all the canonical forms, that structure which is the most stable gives the better representation of the true molecule. So basically, if you have got the molecule, and you are proposing its structures, canonical forms, C1, C2, C3. These are the canonical forms of this molecule M. Perfect. That canonical form, which will be most stable among all these 3. That canonical form, which will be most stable among all these 3. Your true molecule will look more like that. Your true molecule will look more like that. I hope you're getting what I'm trying to say. You have got the molecule. You have got the molecule. You are proposing its canonical forms. Now, let's say among these 3, C1 is the most stable canonical form. If C1 is the most stable canonical form, that means your actual molecule will look more like C1. It will look more like C1. That means C1 will give more information about the actual molecule, about the true structure of the molecule. C1 will give more information about it. Your actual molecule will resemble more like what? Will resemble more like C1. Yeah? Is this point clear? Is this point clear, guys? So that canonical form which will be the most stable. Your actual molecule will look more like that canonical form, which is highest stable. Let me know once in the chats if this point is also clear. If this point is also clear. All right, have a look on this particular thing. As I told you, look at this particular point. All the canonical forms should have same, this is one more important point. All the canonical forms, they should have same total number of shared and unshared electron pairs. For example, say, if you need to identify whether these two are canonical forms or not, so there's a condition, both these canonical forms should have same number of shared plus unshared electron pairs. Now see how many do we have? This one electron pair, 2, 3, 4 and 5. So in total, it has got 5 electron pairs. Now this should also have 5 electron pairs, then only I would call them as the canonical forms. 1, 2, 3, 4, 5. This also has 5 electron pairs in total. So all the canonical forms, do remember they should have same number of electron pairs. Shared plus unshared. Shared plus unshared. Right? This was one more important thing. Now guys, we are actually going to, I hope you got the exact definition of resonance. Let me quickly summarize it. Guys, in order to understand resonance, resonance is considered as the most difficult topic if it is taught actually, right? Okay, if it is taught in a real sense basically. Otherwise, it's easy. You know, the conjugation, do this, that, shift the bonds, that is easy. But the actual meaning of resonance is basically, right, it is difficult to understand. And I hope it is clear to everybody now. Yeah? Can you quickly let me know if it is clear? So quickly summarize it. Whenever a true structure of the molecule cannot be formed, or if any structure of the molecule cannot explain all the properties of it, you will say that the molecule will exhibit resonance. Right? You'll say that the molecule will exhibit resonance. Perfect. What are the conditions? What is the meaning of, first of all, localized and delocalized electron pair? Localized electron pair is that electron pair which is shared between two atoms. Delocalized, shared by more than two atoms. Right? Now, which electron pairs can be delocalized? High energy electron pairs can be delocalized, like your pi electrons, which are subjugated to less force of attraction. They can be delocalized. And the delocalization of high energy electrons, like pi electrons, is something which you call as resonance. If you look at the orbital approach, as per orbital approach, what is the resonance? It is the partial overlap of p or d orbitals, which are parallel and coplanar to each other. Right? Perfect. Now, one more thing. How do you define the canonical structures? Canonical structures are the ones in which bonding is localized. Delocalization is not present in the canonical form. Delocalization is present in the hybrid. If delocalization is present in the hybrid, that is the reason why in the hybrid your pi electron density comes under the influence of more than two nuclei, due to which force of attraction increases, right? Potential energy decreases, stability increases. That's the reason why your hybrid is more stable. That is the reason why the hybrid is more stable. Yeah? That is the reason why hybrid is more stable. Perfect? And at the same time, condition for resonance, there should be the presence of parallel p orbitals, which should be coplanar to each other. Perfect? Right? Your true structure will look more like that canonical form, which is highest stable among all the canonical forms. This is one more important point, which we have discussed. Okay? In all the canonical forms, the total number of electron pairs should be equal. One more important point. Right? One more important point. Perfect. And all the canonical forms should have similar energy. All the canonical forms should have similar energy. Now we are going to move into conjugation. Now you will easily do the resonance, etc., etc. Now this is the easy part, right? Now this is the easy part. See guys, basically wherever there is conjugation, resonance will be there. Conjugation can be of many types. Pi sigma vacant orbital conjugation, something which we have to discuss in detail. pi sigma free radical conjugation, pi sigma negative charge with unshared pair of electron, right? Pi sigma pi conjugation. Wherever you see pi sigma, I mean these sort of conjugations, do remember in that molecule resonance will be there. In that molecule resonance will be there, right? In that molecule resonance will be there. For example, this is CH2, this is double bond, this is CH, this is single bond, this is CH2 positive. For example, just an example. First of all, sp2, this is also sp2, this is also sp2, everywhere. Or let me just make it like, this. See guys, over here there's a pi bond. As you can see, it is pi. And after pi, you have got sigma. After pi, you have got sigma. After pi, you have got sigma. So first you have pi, then you have sigma. If you look at this particular carbon, if you look particularly at this carbon, what about the outermost configuration of carbon? It's 2s2, 2p2, right? 2s2, 2p2, correct? 2s2, 2p2. So this is 2s containing 2 electrons, 2p containing 2 electrons. Perfect. Now after excitation is done, 2s will be containing 1 electron and 2p will be containing 3 electrons. 2p will be containing 3 electrons. Now there is a positive charge here. Positive charge here means take 1 electron out. Positive charge means take 1 electron out. Let's say 1 electron is here. Let's say that 1 electron is taken out from here. Now this particular carbon, how many sigma it's forming? 3 sigma. 3 sigma means sp2 hybridization. This sp2. And there is one vacant orbital, one vacant p orbital. So this carbon, it has got a vacant p orbital over here, right? So in this molecule, do you see pi, sigma and vacant orbital present? Absolutely. Here we have pi, sigma and vacant orbital. Wherever in a molecule you see pi, sigma, vacant orbital, understand resonance will happen in that molecule. Similarly, pi, sigma free radical, resonance will happen. Pi, sigma negative charge with unshared pair of electron, resonance will happen. Pi, sigma, pi conjugation, resonance will happen. Okay? Perfect. Now people, one by one, we are going to discuss this conjugation. So first type of conjugation is your pi, sigma, vacant orbital conjugation. Your pi, sigma, vacant orbital conjugation. Now guys, firstly, I'll make you understand this particular thing. After that, I'll show you how to draw the structures exactly. See, first of all, this is your sp2. Okay. If you look at this structure, this is one of the canonical forms which is given to me. Now, after looking at this canonical form, I will have to make more canonical forms. After looking at this particular canonical form, I will have to make more canonical forms. But before that, have a look exactly whether any type of conjugation is present here or not. See, I can see this is a pi bond. I can see here you have got sigma. Now, it has to be pi, sigma, vacant orbital. Then only I'll say there is conjugation, and then only I'll say that this molecule will undergo resonance. Now, how do you check whether you have got a vacant orbital here or not? The same approach which I showed you a few minutes back. Right? Tell me, outermost configuration of carbon is 2s2, 2p2. Right? This is 2s containing 2 electrons and 2p containing 2 electrons. One here, one here. After the excitation is done, 1 electron will be here and 3 electrons will be here. 1, 2 and 3. Now there is a positive charge here. So take one of the electron out. If you take one of the electron out, this is the structure now. Okay. Now what is the hybridization of this carbon? It is forming 3 sigma. Right? So it's sp2 hybridization. 3 sigma means sp2. So this is sp2 hybridization. Perfect. And there is a presence of a vacant p orbital here. So this particular carbon, it has the vacant p orbital. Even this is sp2. This is sp2. Right? If you exactly have a look on the orbital approach, if this is sp2, this is sp2. That means it will be having 1 p orbital and here 1 p orbital. And this structure is telling you that these 2 p orbitals have overlapped parallelly. Now other structure will tell you that these two can also overlap parallelly. Right? Perfect. Now I'm not going into the details of that. Since over here I got to know that we have got the pi sigma. We have got the pi sigma vacant orbital conjugation. So I'll directly say that resonance will happen here. And how do we make its other structures? In this structure, these 2 p orbitals have overlapped. In the other structure, these two will overlap. So what does that mean? In short, shift shift this pi bond here. When you shift this pi bond here, it will become CH2 positive. It will become CH2 positive. There was a double bond here. There was a double bond here. Now there will be a single bond. This CH you are writing as such. Initially there was a single bond here. Now it's going to be a double bond. Now it's going to be a double bond. Initially this was CH2 positive, but due to the double bond, it is not that positive will be compensated, nullified. This will be CH2 now. So this is one more resonating structure, one more canonical form. And this canonical form is telling you, the p orbital of this and the p orbital of this, they have overlapped. Now, some information about the actual molecule this is given. Some information about the actual molecule this is given. And if you compile the information, you'll get the resonance hybrid. You'll get the resonance hybrid. So make the hybrid, guys. Make the hybrid. Make the hybrid here. Make the hybrid here. Try to understand. The hybrid looks like this. First of all, I'll write CH2. I'll put single bond everywhere. I'll put single bond everywhere. Correct? Now, as per this structure, there should be double bond between these two. But this structure is saying single bond. So in the actual molecule, it's neither going to be pure single nor pure double. It will be partial double. Similarly, this is single. This is saying double. So in the actual one, it is partial double. Right? This structure is telling you that this carbon should have positive. So make delta positive over here. This structure is telling you, no, this carbon has to be positive. So keep delta positive over here. So this is something which I'll be calling as the hybrid. This is the resonance hybrid, people. I hope you got to know how to make it. Right? I hope you got to know how to make it. Perfect. I hope you got to know how to make it. Now, look at this one. Look at this one. Look at this one. Again, you can see this is pi. This is pi, sigma. And over here, you will find a vacant orbital. You will find a vacant orbital. This is sp2 hybridized. This sp2 hybridized. Even this is sp2 hybridized. Right? Every carbon here is sp2 hybridized. So every carbon will be having a p orbital, and those p orbitals will be parallel to each other. Right? And the partial overlap of the parallel p orbitals is something which you call as resonance. Right? Now guys, try to understand. This is pi, this is sigma, and here you have got the vacant orbital. Here you have got the vacant orbital. So there's a conjugation. If there is a conjugation, so you'll be making its resonant structures. So shift this pi bond here first. Right? When you shift this pi bond here, this was CH2 positive in the beginning. Now it's going to be CH2, positive charge compensated. Now there'll be a double bond here. Right? There'll be a double bond here. Since you have shifted this pi bond towards this, right? So I would say this particular carbon will be getting positive, right? It will be getting positive. Rest, everything is same. Now, again, if you see, this is pi sigma vacant orbital, pi sigma positive, pi sigma vacant orbital. So again, resonance. So this pi bond will shift here. When this pi bond shifts here, the other resonating structure will be like this. Guys, see exactly how do we make the resonating structures. See, there was a positive here. Now pi bond is shifting, right? From which carbon pi bond is shifting? In this structure. In this structure, your pi bond was between these two. In this structure, your pi bond is between these two. So basically, this is the carbon at which pi bond is present. But pi bond is shifting from this carbon. That carbon from which pi bond is shifting, that will get the positive charge. Rest, everything is same. Again, if you see pi sigma positive, that means shifted in this direction. When you shift it in this direction, so what is one more conjugating structure which you will get? This is CH2. And others, this is this, right? And this will get the positive. Now again, pi sigma positive means shift this in this direction. So what do we get at the end? This is CH2. This is double bond. Sorry, not the double bond. This is CH2. This is a single bond. And rest, have a look. There'll be a double bond here. There'll be a double bond here. There'll be a double bond here. Perfect. Right, guys? Now, if you categorically look at one more important thing here. Guys, look at the first canonical form and the last canonical form. If I ask you, are these same or different canonical forms? Are these same or different? First one and last one. Are these same or different? Are these same or different? Are these same or different? Quickly. First and the last, are these same canonical forms or different? See, canonical forms, they contain localized bonding. This canonical form is telling you there's a pi bond between these two. But the last one is telling you there is a single bond between these two, right? So these two canonical forms, they are different, right? No doubt they are different, but, first and last, no doubt they are different canonical forms. But let me tell you, their energy and stability will be the same. Look at both of them. Look at both of them. Sorry, there's a charge here. Look at both of them, right? So they are basically different canonical forms, but their energy and stability will be the same. Okay, so first and last, let me write it here. First and then last. They are actually different canonical forms. They are actually different canonical forms, but their energy and stability is same. But their energy and stability is the same. Right? So finally, if I want you guys to make the hybrid, you can easily make the hybrid. Let's make the hybrid, people. Let's make the hybrid. See, every bond here is getting the partial double bond character. This is getting partial double bond. Why? Because here it was supposed to be single, but here it is double. So it will be partial double, right? Every bond, there will be partial double bond character. There will be partial double bond character. Number one, as per the first structure, this should have positive. As per this structure, this should have positive. As per this structure, this should have positive. And as per this structure, this should have positive. Perfect. So this is something which you will be calling as the hybrid, right? This is something which is what you'll be calling as the hybrid. Perfect. Is it clear, people? Is it people? Is it clear, people? Quickly. Have a look. You have got again pi, sigma, and here you have got positive. Pi, sigma, vacant orbital basically, right? Pi, sigma, vacant orbital. If you see every carbon here is sp2 hybridized. Every carbon here is sp2 hybridized. So it's again pi, sigma, vacant orbital. If it is pi, sigma, vacant orbital, right? Draw its structures. So it's one of the structure will be like this. So pi bond got shifted and now this gets the positive, right? Now again you got pi sigma positive. Pi sigma positive. Let me shift it here. When you shift it here, there'll be a structure like this. Now there's a pi bond here and this particular carbon will be getting the positive. Perfect. Now do you see first one and last one? First one and last one, are they same or different? They are different, but their energy and stability will be same. Actually, tell me one thing. How do we make the hybrid here? How do we make the hybrid? Every bond is getting partial double bond, right? Every bond is getting partial double bond. As per the first structure, delta positive here. As per the second structure, delta positive here. As per the third structure, delta positive here. So this is what you'll be calling as hybrid. And hybrid will be maximum stable as per all these structures here. Okay, so this was your pi sigma vacant orbital conjugation, right? Now tell me one thing. Will the molecule show resonance or not? What do you think? Will the molecule show resonance or not? Will there be resonance in this molecule? You are going to tell me. Will there be resonance in this molecule? What do you think? What do you think? I'm asking you. It's a simple question. Yes or no? See what you're saying here. You're saying pi sigma positive, pi sigma vacant orbital, right? So there is conjugation, right? So majority is saying there is conjugation. Nice, good. If there is conjugation, that means it should undergo resonance. But people just try to understand, if it undergoes resonance, this bond will shift here, right? If this bond shifts here, what do we get? We got RC. This is oxygen. Since a bond is getting shifted from oxygen, so oxygen carries positive now. And there'll be a double bond here. This will be CH2. If resonance happens here, this has to be its canonical form. But if you look at this form, oxygen was not carrying any charge. Here, oxygen is carrying positive charge. If you remember, positive charge on an electronegative element makes it highly unstable. Positive charge on an electronegative element makes it highly unstable. So I would say, if this is I'm calling as canonical form 1, this I'm calling as canonical form 2, I would say energy of canonical form 2 will be higher than that of canonical form 1. But we know, as per the property of canonical forms is concerned, canonical forms, they should have same energy, similar energy. But its energy is very, very, very high. So this cannot be its canonical form. So this molecule won't undergo resonance. Understood? Understood? Tell me that. Is this point clear? Guys, all these are very, very, very important points. I'm not sure whether you would have studied all this before or not. Tell me in the chats quickly. Quickly. Yes? I want everyone to say it in the chat quickly. Perfect. Perfect, guys. See, normally, if you look at these two molecules, what you will quickly say, you will say there's a conjugation. Pi sigma positive, pi sigma positive. You will directly say these two will undergo resonance. Right? If the concept of resonance is not clear, if you would have superficially discussed resonance, you'll clearly say there's a conjugation pi sigma positive, so it will undergo resonance. But I'll say this will not undergo resonance. Why? What is the reason? What is the reason? My dear students, conjugation is basically like this. This is pi, then there should be sigma, then there should be a vacant orbital, right? But look at this particular nitrogen. How many bonds it's forming? It's forming 4 bonds. If it is forming four bonds, its octet is complete, right? Its octet is complete. If its octet is complete, will there be any vacant p orbital? Will there be any vacant p orbital with this nitrogen? It is forming 4 bonds. This nitrogen is forming 4 bonds. So its octet is complete. So will there be? See guys, its octet is complete here. If its octet is complete, that means now its configuration is going to be 2s2, 2p6. Right? So do you see any vacant orbital with nitrogen? Do you see any vacant orbital with nitrogen? Nitrogen does not have the vacant p orbital here, right? Because all its p orbitals are carrying the electrons now. So it is not going to show resonance. Look at this one. Pi sigma, vacant orbital should be present here. It is forming 3 sigma bonds. 3 sigma bonds. So 3 2s are 6 and 2 electrons here. 6 plus 2, 8. Its octet is also complete. If its octet is complete, it is not going to have any vacant p orbital. If there is no vacant p orbital, if there is no vacant p orbital, it's not going to show any resonance here. Got this point? So these two are not going to show any resonance because there is no vacant p orbital here, there is no vacant p orbital here. The octet of this nitrogen and oxygen is complete. If the octet of nitrogen and oxygen is complete, there will be no vacant p orbital with them. Yeah? All right, tell me. Tell me whether this molecule will show resonance or not. This is pi sigma positive, whether they'll show resonance or not. See, phosphorus is forming 3 plus 1, 4 bonds. So 4 to its octet is complete, right? Sulfur, its octet is complete. Nitrogen, its octet is complete, right? Will this show resonance? This will show resonance. This will show resonance. In phosphorus, see, nitrogen, phosphorus. Nitrogen, phosphorus. Nitrogen does not have any d orbital, but phosphorus has vacant d orbital. Phosphorus has vacant d orbitals, right? Phosphorus has vacant d orbitals. So I would say phosphorus over here, it has vacant d orbital. It has vacant d orbital. So the conjugation will be pi sigma vacant orbital. Pi sigma vacant orbital, right? I had categorically mentioned in the first case, it has to be pi sigma vacant orbital. That vacant orbital can be p or d. That vacant orbital can be p or d, right? No doubt. It looks like it's forming 4 bonds. Its octet should be complete, but it has got vacant d orbital, guys, right? If there is a vacant d orbital, that means it will show resonance. Look at this one, sulfur. Sulfur, 4 bonds it's forming. Octet complete. Now tell me, sulfur, does it have vacant d orbitals? Sulfur has d orbitals, right? There is the vacant d orbital of sulfur. What is the electronic configuration of sulfur outermost? It is 3s2. It is 3p4. There is 3d as well, which contains 0 electrons. So it has vacant d orbitals. If it has vacant d orbital, it will show resonance. But nitrogen, if you look at the configuration of nitrogen, 2s2, 2p3, is there any d? There is no d in nitrogen. There is no d in nitrogen, right? There is no d in nitrogen. If there is no d in nitrogen, this will not show resonance. Is it clear? Is it clear? Is it clear, guys? I hope you can analyze from now onwards which one can show resonance, which one cannot. Okay, among these three, quickly, among these three, is the first one going to show resonance? Yes or no? Everyone. Is the first one going to show resonance? This is pi sigma, and it will have, this phosphorus will have vacant d orbital. It will show resonance, right? What about the second one? Pi sigma. Look at this boron. It's forming how many bonds? 3 bonds. It's forming 3 bonds, right? It's forming 3 bonds. Quickly tell me, is this particular molecule going to show resonance or not? Quickly tell me, is it going to show resonance or not? If you look at boron, guys, what is the outermost configuration of boron? It is 2s2, 2p1. Correct? This is 2s carrying 2 electrons and 2p carrying 1 electron. 2p carrying 1 electron. Now, after the excitation is done, 1 electron here, 1 electron here, right? Okay. How many bonds it's forming? It's forming 3 sigma bonds. 3 sigma bonds means sp2. This sp2, is there the vacant p orbital? Yes, this boron has vacant p orbital. So pi sigma vacant p orbital. Absolutely, it will show resonance. Right? Look at this one. Look at this one. Is it going to show resonance? Pi sigma. Again, the similar scenario. This will show resonance. So all these 3 will show resonance. Right? All these 3 will show resonance. I hope this is again clear to everyone. Now there is one more conjugation. So till now I showed you one conjugation. What is that? What is that? That is your pi sigma vacant orbital conjugation. The second one is pi sigma free radical conjugation. Pi sigma free radical conjugation, right? Have a look. Pi sigma radical. Pi sigma radical. Conjugation is there, so it will undergo resonance, right? So shift the pi bond on this side. When you shift the pi bond on this side, this CH2 will get a radical, right? And this was a double bond here. Now it's going to be a single bond. This is CH now. Now it's going to be a double bond. So it's going to be CH2 like this. So this is one more canonical form of it. Now, if you want to make it hybrid, so make it simple. CH2, everywhere keep a single bond first. CH, this is CH2, right? Now, there was a double bond here, but this structure is telling single bond. So neither single nor double, partial double. Single, but this is saying double. Neither single nor double, partial double. Now look at this particular resonance hybrid. See, as per this particular structure is concerned, this having a radical. So have a radical here. As per this structure, this having a radical. So have a radical here, delta radical, right? So this is the hybrid. This is the hybrid, people. Clear? This is the hybrid. Make its resonating structures. How will you make its resonating structures? See, pi sigma radical. So shift this pi bond in this direction. When you shift the pi bond in the direction, this is CH2. Now it's going to be a double bond, right? That carbon from which the bond has been shifted. From this carbon bond has been shifted. I'll put a radical here. Rest everything is same. Now it's again pi sigma radical. If it's pi sigma radical, shift in this direction. When you shift in this direction, what do we get? Try to understand what do we get exactly. This is your pi. Here you will be getting the radical, and here's a double bond. Perfect. Now again, this is pi sigma radical, right? So shift in this particular direction. So what do we get again? This is CH2. This is double bond, and rest. I believe everything is similar only, right? Now this particular carbon gets the radical, because the bond has been shifted from this particular carbon. Now have a look. This pi sigma radical. Pi sigma radical, shift this bond here. When you shift the bond, it is going to be at the end CH2 radical. It is a single bond. Rest. All the things. This is like this. Now tell me one thing. First and the last, are these same or different resonating structures? First and last. Same or different? Same or different? Quickly. First and last. Same or different? First and last, same or different? They are different resonating structures, but their stability and energy, that's equal. Yeah? So, I hope this particular conjugation is also clear. Now, guys, there is one more conjugation. What is that? First one was pi sigma vacant orbital. Second one is pi sigma free radical. Third one is pi sigma negative charge with unshared pair of electron. Negative charge with unshared pair of electron. Have a look. This is your pi. This is sigma. This is negative charge with unshared pair of electron. So shift it, just shift it. After shifting, what do we get? This will be your CH2 negative. This will be your CH2 negative. There'll be a single bond here. This is CH, right? There'll be a double bond here. And this will be your CH2. Perfect. Simple. Now make the hybrid. How will you make the hybrid? First, put a single bond everywhere. First, put a single bond everywhere. After putting the single bond everywhere. Now, this is double here. This is single. So hybrid will contain partial double. Single, this is double. Hybrid will contain partial double. Now, as per this particular structure, this one carries negative charge, right? So this is delta negative. As per this one, the other carbon carries the negative charge, so delta negative. So this is your hybrid. This is your hybrid. I believe this is also clear. I believe this is also clear, right? Now, similarly, guys, there is one more conjugation. There is pi sigma lone pair conjugation. Okay, one more example we have here. One more example we have here. Right? One more example we have here. Have a look, guys. Look at this one. This is pi, this is sigma, this is negative, right? With an unshared pair of electron. So again, conjugation, shift it, right? When you shift it, what do we get at the end? This is CH2. There is a single bond here. This is CH. There is a double bond here, and this is O. Now, this will carry the negative because this bond has been shifted. Now, if I ask you what is the hybrid, how the hybrid looks like, this is CH2, single bond CH, right? This is O. Perfect. Now, as per this particular structure, there's a double bond here. As per this structure, there is a single bond. So, in the hybrid, it will be partial double. In the hybrid, it will be partial double, right? This is going to be delta negative, and this is also going to be delta negative. So, this is your hybrid over here. Yes? I hope you can easily do all these sort of things, right? I hope you can easily do all these sort of things. Okay. Can you make the resonating structures of these two? You should be in a position to make the resonating structures of these two. Have a look. This is pi sigma negative charge with an unshared pair, right? Pi sigma negative charge with unshared pair. What will happen? Shift this negative charge here, shift this pi bond here. So what do we get? This is O. So what do we get? This is O. Now there is a double bond here. Perfect. Now see what all shifting would have happened. Now, since this is a double bond, right? This pi bond has shifted in this direction. So now this carries the negative charge, rest everything, keep it as such. Now this is pi sigma negative. So shift it here, shift this one here. What do I get? This is oxygen, this is double bond, and all the things, rest. This is double, this is negative, perfect, in this particular direction. Now again, this pi sigma negative, shift this in this direction, shift it in this direction. What do I get? I get oxygen, this is double bond, right? And see all the things, this is now negative, right? There is a double bond here, there is a double bond here, perfect. Now again, this pi sigma negative, shift it and shift it. So what do I get at the end? I got something like this. Perfect. So these are all the resonating structures which we have here. Now people, tell me, first and last, are they same or different? They are different, but their energy stability both is same. Yeah? Perfect. Now I think this one you can easily do on your own. This one you can easily do on your own. Now here is a check for you. This is your checkmate. Will the following molecules show resonance or not? I've got 4 molecules here. Among these 4 molecules, which one will show resonance? Which one will show resonance among these 4? Among these 4. Which one will show resonance among these 4? Will first one show resonance? This is pi sigma negative, but it has to be pi sigma negative with unshared pair. This has to be the actual scenario. I'm just mentioning pi sigma negative, but it has to be pi sigma negative with unshared. Negative with unshared. So is this going to show resonance? No way. Look at the second option. Look at the second option. Look at the second option. Tell me one thing. What is resonance? The partial overlap of p orbitals, right? The partial overlap of orbitals which can be p or d. Correct? Now guys, try to understand. Try to understand. If you look at this particular carbon, what is the, if you talk about carbon, it is 2s2, 2p2, right? So this is s, and these are 3p orbitals of carbon. Okay? First of all, there's a pi bond here. If there's a pi bond, that means p orbital of this and p orbital of this, they have parallelly overlapped. So one of the p orbital is consumed. It is consumed, right? One of the p, this p orbital and this p orbital, they are partially overlapped, right? So this p orbital is gone. Now, how many orbitals are left? S and 2p. So this will undergo sp2 hybridization. sp2 hybridization means how many hybrid orbitals? 3 hybrid orbitals. One of the hybrid orbital would have formed this sigma bond. One of the hybrid orbital would have formed this sigma bond. And one hybrid orbital will be carrying this positive charge. One hybrid orbital will be carrying this positive charge, right? Now for resonance, now you tell me, will this molecule show resonance or not? Will it show resonance? What is the resonance? Will it show resonance? Yes or no? Quickly. Quickly. So that positive charge is basically present in what? sp2 orbital. It should have been in it should have been pure p orbital. Right? So it is not going to show resonance. Look at this one. Again here, it is present in sp2. This radical is also present in sp2. So none of the molecule will show resonance among these four. None of the molecule will show resonance among these four. Okay? None of the molecules will show resonance among these four. These are some typical cases, guys, which I'm showing you. Okay. This is one important statement. Lone pair has to be present in the pure p orbital. When you talk about pi sigma lone pair conjugation, the lone pair has to be present in pure p orbital. There is one important thing which I'm going to tell you now. First of all, have a look. Have a look, guys. This is pi, this is sigma, this is a lone pair. Is this lone pair over here conjugated? Yes, this is conjugated. So basically, oxygen has two lone pairs. Oxygen has two lone pairs. Out of the two lone pairs, one lone pair will participate in the resonance. That lone pair which is participated in the resonance, that is not considered while calculating the hybridization. That lone pair which participates in the resonance, that is not considered for hybridization. So one of the lone pair, you don't have to consider for hybridization. Now if I ask you, what is the hybridization of this oxygen? Quickly. See, it's forming 1 sigma, 2 sigma. So 2 sigma and 1 lone pair you have to consider. You don't have to consider 2, you have to consider 1. So 2 sigma 1 lone pair, steric number 3. If steric number is 3, so it is sp2. It is sp2. It is sp2. That means this lone pair, it is present in pure p orbital. That's what I mentioned over here. Lone pair has to be present in the pure p orbital. Lone pair has to be present in the pure p orbital. Perfect? Right? So make its resonating structures. So shift this lone pair in this direction, shift this bond in this direction. What do you get? You get CH2 negative. You get CH2 negative. There is a single bond. This is CH. This is double bond. This is OH carrying only one lone pair, and there will be a positive charge here. Perfect. So this is its one more canonical form. Look at this particular nitrogen. This nitrogen, it's forming 3 sigma bonds. It's forming 3 sigma bonds. And this lone pair is conjugated. This is pi sigma lone pair. It is conjugated. Perfect. Now this nitrogen, if I ask you its hybridization, it's sp2. If it is sp2, there will be a p orbital, and that p orbital will be carrying this lone pair, right? So shift it. When you shift it, it's going to be CH2 negative. CH2 negative, there is a single bond. This is CH, there's a double bond. This is going to be your NH2 positive here. Perfect. So this is going to be its canonical form. Similarly, can you make the canonical forms for this one? Can you make canonical forms for this one? This pi sigma lone pair. Pi sigma lone pair. This oxygen, it has got 2 lone pairs basically. It has got 2 lone pairs basically. But out of the 2 lone pairs, 1 lone pair will participate in resonance. So you do not have to count that lone pair for hybridization. Now, tell me the hybridization of this oxygen. It's forming 2 sigma and 1 lone pair. 2 sigma, 1 lone pair. That means steric number 3. So it's sp2. That means this particular lone pair, it is present in pure p orbital. And that is the criteria. Lone pair has to be present in the pure p orbital. Correct? Now you can do all the wonders, right? Shift it in this direction. Shift it here. There'll be a negative charge. When there is a negative charge here, shift it in this direction. This will shift in this direction. There'll be a negative charge. Then shift this in this direction and shift it here. I mean, you can easily make these structures. You can easily make these resonating structures now. Okay? Is that clear? Now, my dear students, once you are familiar with how to draw the resonating structures, now it is the time to compare. It is the time to compare the stability of the resonating structures. It is the time to compare the stability of resonating structures. This is a question which is frequently asked. How do you check the stability of the resonating structures? These are the 3 resonating structures which are given to us. We need to compare their stabilities. My dear students, the first and the most important point. If you need to compare the stability of these resonating structures, what you should do? First of all? Try to calculate the number of covalent bonds. See, first of all, this is CH3 here, CH3 here, CH3 here, right? This is NH, this NH here, this NH here. This is CH3 here, this is CH3, this is CH3. So all these things are same everywhere. So what I'll be doing, I won't be counting the exterior bonds. I'll be counting the interior bonds. I'll be counting the interior covalent bonds. Tell me how many interior covalent bonds do we have here? 1, 2, 3, 4, 5, and 6. 6 interior covalent bonds, right? Look at this one. 1, 2, 3, 4, 5, 6. 6 interior covalent bonds here. Absolutely. How many here? 1, 2, 3, 4, 5, 6. 6 interior covalent bonds here. My dear students, whenever you need to compare the stability of the resonating structures, the first point is you have to count the covalent bonds, interior covalent bonds. That structure wherein covalent bonds are maximum, that will be maximum stable. This is the first point which you'll be checking all the time. Calculate the maximum, calculate the interior covalent bonds. That resonating structure which will be containing maximum interior covalent bonds will be maximum stable. But here in these 3, the interior covalent bonds are same. So you cannot decide on the basis of interior covalent bonds. Right? But your priority is always covalent bonds. Number two. Look at that resonating structure. Find that resonating structure in which atoms do not contain any charge. Is there any resonating structure like that in which atoms do not contain any charge? Is there any resonating structure like that in which atoms do not contain any charge? I can directly say first one, right? I can say first one. That resonating structure in which atoms do not contain any charge. That is going to be stable. First, you are going to check what? First, you are going to check number of bonds. Then, you are going to see that resonating structure in which the atoms do not contain any charge. This is the structure in which atoms do not contain any charge. So, first one is maximum stable. Now, among 2 and 3. Have a look properly what exactly we are going to say. Have a look. My dear students, what do you think? 1, 2, 3, 4, 5, 6. Okay. What do you think among 2 and 3? Which one? Among 2 and 3, which one? Quickly. Among 2 and 3, which one? Which one is more stable? What do you think? See, if you look at these two structures carefully, this is oxygen carrying negative, same, right? Same. Perfect. Look at this particular oxygen. Oxygen is carrying positive here. Oxygen is carrying positive. Positive charge on an electronegative element makes it highly unstable, right? So among 2 and 3, which one is more stable? I'll say 3 is more stable, followed by 2. So is this the order? This is going to be the order here, right? Let's have a look on one more question. Have a look on one more question. Check the order of the stability of these resonating structures. Check the order of the stability of these resonating structures. Have a look, guys. First of all, calculate the total number of internal covalent bonds. 1, 2, 3, 4, 5, 6, 7, 8. 8 covalent bonds. 1, 2, 3, 4, 5, 6, 7. 7 covalent bonds. 1, 2, 3, 4, 5, 6, 7, 8. 8 covalent bonds. Wherever bonds are minimum, that is least stable. So 1, 2, 3. 2 is least stable. 2 is least stable. Now among 1 and 3, this is the resonating structure in which atoms do not contain any charge. So 1 is maximum stable, followed by 3, followed by 2. All of you got this order? 1, 3, 2. All of you got this order? 1, 3, 2. Perfectly done? Perfectly done? Wonderful. Okay. Tell me the answer of this question. Among these two, which one is more stable? First, calculate the bonds. 1, 2, 3, 4. 1, 2, 3, 4. Bonds are same. Bonds are same. Now, this one does not carry any charge on atoms. So this one will be more stable. 1, 2, 3. Calculate the bonds. Calculate the bonds. 1. These are 6 plus 1, 7. 8, 9, 10. 10 internal bonds. 2. 2 plus 6 is 8. 8 plus 2 is 10. 10. 2. 2 plus 6 is 8. 8 plus 2 is 10. So bonds are same. Bonds are same. So I'm not going to talk in terms of bonds. Now, what is the next thing? This particular resonating structure, its atoms do not contain any charge. It's maximum stable. Now, among 2 and 3. Among 2 and 3. See, oxygen carrying positive. Here also oxygen is carrying positive. Carbon carrying negative. Here also carbon is carrying negative. So these are the two resonating structures wherein same atoms carry similar charge. Oxygen positive, carbon negative, carbon negative. And when same atoms carry similar charge, at that point of time, what do we say? At that point of time, how do we distinguish more stable, less stable? These are like charges or unlike charges. These are unlike charges. Positive, negative, unlike. Positive, negative, unlike. More the distance between positive and negative. Can I say more will be the potential energy of the system? As the distance increases between unlike charges, potential energy of the system increases. And if potential energy of the system increases, stability decreases. So which molecule will have more potential energy? This resonating structure will have more potential energy, so less stability. So 3 is least stable. And here is 2. I was talking about unlike charges, right? More the distance between unlike charges, more is the potential energy of the system, lesser is the stability, right? So 1, 2, 3 is the order of the stability here. All right. Among this and this, okay, these are 3 basically given in the beginning. 2, 4, 4 sigma bonds. 4 covalent bonds, 4 covalent bonds, 3 covalent bonds. So third one is least stable. Leave that. Third one is least stable. Now among 1 and 2, check it out. See, this is the nitrogen carrying positive, nitrogen carrying positive. Perfect. This nitrogen is carrying negative, and here carbon is carrying negative. Nitrogen carrying negative, carbon carrying negative. Nitrogen, carbon, they belong to same period. Same period, electronegativity plays a role. Negative charge is more stable and more electronegative. So this particular first one will be maximum stable, followed by 2, followed by 3. Do you agree with all this? Yes? 1, 2, 3 is the order. Okay, tell me the next one. I'm giving you 1 minute of time. 1 minute of time I'm giving you. Tell me this is calling this as resonating structure 1, calling this as 2, calling this as 3, and calling this as 4. What will be the stability order of these resonating structures? I'm asking you. You should be in a position to answer this quickly. Quickly, guys. Quickly, everyone. You should be in a position to answer this particular question as well. So one of the option I got from Senthil Kumar, 4321. 4321. This is one of the option. I'll be taking 4 options from you. Sweetie is saying the same thing. 4321. Everyone is, I think, saying 4312. I got one more option, 4312. Okay. 3412. 3412. Now, any other? Are you doing some permutation combination here? Okay, let's have a look. Let's see what is going to be the actual answer. First of all, count the total number of internal covalent bonds. 2, 3, 4, 5. Right? 5. 1, 2, 3, 4, 5, 6. This is 6. Right? 1, 2, 3, 4, 5. 5. Perfect. 1, 2, 3, 4, 5, 6. This is 6. Right? So you calculated. What did you calculate? You calculated the total number of internal covalent bonds. Now you tell me. More the bonds, more the stability. So it is evident that 3 and 4 will be more stable than 1 and 2. It is evident that 3 and 4 will be more stable than 1 and 2. Now among 3 and 4, which one is more stable? Among 3 and 4, which one is more stable? See, carbon carrying negative here. Here also carbon is carrying negative. Nitrogen carrying positive, nitrogen carrying positive. So in these two resonating structures, I'll say same atoms carry similar charge. Same atoms carry similar charge, right? Same atoms in these two resonating structures carry similar charge. Are the charges like or unlike? They're unlike. They're unlike. More the distance between unlike charges, more the potential energy of the system, less the stability. So among 3 and 4, which one is more stable? 4, then 3. Now in 2 and 1. 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 What do you say in 2 and 1? What do you think in 2 and 1? In 2 and 1. What do you say? Negative 1 carbon, positive 1 carbon. Right? Negative 1 carbon, positive 1 carbon. Perfect. Now here will you use the distance rule between unlike? No. After this carbon, there is nitrogen. Nitrogen has got the lone pair. Right? After this carbon, there is a nitrogen. Nitrogen has got a lone pair. So lone pair and negative, they'll ripple. Ripple means more will be the energy of the system, less is the stability. So 2 will be more stable than that of 1. Did you get this? Guys, you should be able to solve these questions. I'm giving you the typical questions. These are not easy ones. I'm giving you the typical ones wherein you can do a mistake. Wherein you can do a mistake. Tell me, among these two, which one will be more stable? This easily you can. This easily you can. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Right? 2 is more stable 1. Yeah? Directly count the bonds. From the bonds itself, you got to know everything. Right? From the bonds itself, you got to know everything. Every possible thing. I hope this is clear to everyone. Now let's move on to one more topic, that is cross and extended conjugation. Have you ever come across this particular topic, cross and extended conjugation? Have you ever come across this particular term, cross and extended conjugation? Guys, I think the Josh is over. Is the Josh over? Do you want me to cancel the class from here? Do you want me to cancel the class from here? Is Josh over? Is the Josh over? Is that it? Is that it? Are you done? You done? I want everyone to say it. Is the Josh still high? Is the Josh still high? No, right now I'm not giving any break. We'll complete this topic, then maybe. We'll see. Is fire still left or it's over? Is fire still left or it's over? Are you all active? Guys, don't do this. Don't do this. Okay, don't sleep before me. I'm not going to be the one who's going to write the exam. Okay? And I'm not sure whether you would have solved these sort of questions before or not. I don't think. These are typical examples which I'm giving you. Typical examples which I'm giving you. Hmm. Okay. Yes, sharp magnet, JE aspirant can also watch it. Chalo, let's have a look on one more topic. This is again important. Cross and extended conjugation. Right? Cross and extended conjugation. Now, what is cross and extended conjugation all about? See, guys. See, guys. Just a second. Look at this particular slide once. From this particular slide, I'll make you understand what is cross and extended conjugation all about. If you read the first point, whenever, the first point says, whenever a particular electron pair competes for delocalization, whenever a particular electron pair competes for delocalization with two pi electron pairs, which are not conjugated, it is termed as cross conjugation. It is termed as cross conjugation. What is meant by this? You will get the idea in some time. If the pi electron pair gets delocalized in the same direction, it's called as extended conjugation. Try to understand what it means. My dear students, if you look at this particular molecule, carefully. Carefully look at this particular molecule. Here you have got a pi bond, right? Here you have got a pi bond. Here you have got a pi bond. Look at this. Pi, sigma, pi. Pi, sigma, pi. There is conjugation over this particular side. Pi, sigma, pi. Right? Similarly, pi, sigma, pi. Again, there is conjugation. Again, there is conjugation. On both the sides, there is conjugation. Correct? Can I say this particular pi electron pair, this particular pi bond, it is simultaneously in conjugation with this one as well as this one? This particular electron pair, this particular pi electron pair, it is simultaneously in conjugation with this pi bond as well as this pi bond. Whereas, if I consider these two pi bonds, are these two pi bonds conjugated? This is pi, sigma, sigma, pi. They are not conjugated with each other. They are not conjugated. I'll say this particular pi bond is in conjugation with this one as well as this one. Whenever you see this kind of this scenario in which a particular electron pair simultaneously will be in conjugation with two electron pairs, will be in conjugation with two pi electron pairs, this is something which I call as cross conjugation. Whenever a particular electron pair, whenever a particular high energy electron pair is simultaneously in conjugation with two other high energy electron pairs, but those two high energy electron pairs are not conjugated, this particular system is what you call as cross conjugation. Whereas if you look here, this is pi, sigma, pi, sigma, pi. The conjugation is in a single direction, right? Whenever the conjugation is in single direction, this is something which we'll be calling as extended conjugation. You can call it as linear conjugation. Let me tell you people, extent of resonance in cross conjugation is always less than that of extent of resonance in extended conjugation. Extent of resonance in cross conjugation is always less than that of extent of resonance in extended conjugation. And do remember, extent of resonance decides the stability. Extent of resonance decides the stability. More the extent of resonance, more the stability. More the extent of resonance, more the stability. More the extent of resonance, more the stability, right? So, tell me one thing. Over here, a pi electron pair is simultaneously in conjugation with these two electron pairs. But these two electron pairs themselves, they are not conjugated. This kind of the system is something which we call as cross conjugation. But here, there is a conjugation in one direction. You call it as linear conjugation or extended conjugation. Extent of resonance in cross conjugation is less than that of extent of resonance in extended conjugation, right? Wherever extent of resonance is more, stability is more. Just if you remember two things, you are done. If you just remember these two things, you are done. Tell me the answer. Which one among these two is more stable? Which one among these two is more stable? First or second? More stable. First of all, my dear students, if you have a look, this is pi, sigma, lone pair. So conjugation is throughout, right? Over here, this is pi, sigma, lone pair, correct? This is pi, sigma, lone pair. Even this is pi, sigma, lone pair. So can I say this lone pair is in conjugation in this direction as well as this direction? So can I call this as the example of cross conjugation? It is the example of cross conjugation. Extent of resonance in cross is less. If the extent of resonance in cross is less, stability is less. So which one is more stable? I'll say first one is more stable, right? And my dear students, this concept you are going to use at the time when both these molecules will have same pi electrons. Have a look. 2, 4, 6. 2, 4, 6. So same number of high energy electrons are there. Both these molecules are having same number of high energy electrons. So whenever same number of high energy electrons are there, you at that point of time you are going to use the concept of cross and extend conjugation. Otherwise not. Tell me in this case. See, this is pi, sigma, pi. So conjugation. Now pi, sigma, pi. Conjugation. So I'll say this high energy electron pair. This high energy electron pair is simultaneously in conjugation with this one as well as this one. So this is the example of cross. Look at this one. Pi, sigma, pi. So conjugation is throughout. Right? So this is cross conjugation. Extent of resonance in cross is less. Extent of resonance in cross conjugation is less. So stability is less. Right? Look at this one. This negative. Pi, sigma, negative. So this high energy electron pair is conjugate on this side as well as this side. Right? Okay. But have a look on this one. This is pi, sigma, negative. Here conjugation is throughout basically. Right? This is your cross. This is your extended. Right? Extent of resonance in cross is less. If extent of resonance in cross is less, stability is less. So this is the stability order. Is it clear? Is it clear, people? Quickly. Is it clear? I believe this is clear. All right. Tell me one more example. Just a second. Okay. One more thing from which question comes. That is negative charge holding capacity. Negative charge holding capacity of an atom. My dear students, as I told you in the starting of the lecture, the negative charge holding capacity of one oxygen atom. It is greater than the negative charge holding capacity of 10 carbon atoms. The negative charge holding capacity of one oxygen atom is even greater than the negative charge holding capacity of 10 carbon atoms. For example, oxygen is carrying negative, carbon is carrying negative, right? Oxygen, carbon, they belong to same period electronegativity. Negative charge is more stable on more electronegative, right? So negative charge, of course, will be stable on oxygen. It will be more stable on oxygen. But if you want to see how much stable this negative charge on oxygen will be, you will directly say negative charge holding capacity of oxygen is greater than the negative charge holding capacity of almost 10 carbon atoms. From that, you'll get the idea how stable negative charge will be on oxygen as that of carbon. Now you tell me one thing. Look at these two molecules. This is OH negative. Oxygen carrying negative. But over here, is there any oxygen? There is no oxygen. But I would say resonance will be there. This will come here, this will go here, and there'll be a negative here. Then negative comes here, this will go on this side, negative comes on here. Then this will shift here, and this will shift here. Negative comes here. Perfect. That's something which will happen. So in this particular molecule, where all negative charge is getting generated? It was here. Now the negative charge is getting generated at this position, at this position, at this position. Perfect. No doubt there is dispersion of negative charge. There is dispersion of negative charge here. Negative charge is coming on 1, 2, 3, 4 carbon atoms. But here, the negative charge is on oxygen. So can you compare the stability of negative charge? No doubt here negative charge is getting dispersed on 4 oxygen atoms. But in this case, in the first case, negative charge is on oxygen. So tell me, where is the negative charge more stable? Where is the negative charge more stable? I'm asking you. First or second? First or second, quickly. Where is the negative charge more stable? First or second? Guys, you have to tell me the answers in the chats quickly. Look at this statement. I told you negative charge holding capacity of oxygen is greater than negative charge holding capacity of 10 carbon atoms. Here, negative charge is spread on 4 carbons. Here, negative charge is alone on oxygen. But you know, negative charge carrying capacity of oxygen is greater than the negative charge carrying capacity of 10 carbon atoms, right? So where is the negative charge more stable? In the first case. In the first case, right? Okay. Tell me among these two. Among these two, which one is more stable? Among these two, which one is more stable? Which one is more stable? Where is the negative charge more stable? So first of all, no more electronegative element, or everywhere there is carbon-carbon, right? So resonance can happen. And due to resonance, this negative charge can come here. Similarly, due to resonance, this negative charge can first come here. Then the same negative charge will come here. Then the same negative charge will come here, right? So where is the dispersal of negative charge more? In the second case, right? In this, since everywhere there is carbon, again everywhere there is carbon, no electronegative element, nothing, right? So here you'll be simply seeing the dispersal of charge. Wherever dispersal of charge is more, stability is more, right? So where is the negative charge more stable? Okay, look at this one. Look at this one. Here you have got oxygen. No oxygen here. No oxygen here. It's evident. If this undergoes resonance, negative charge will automatically come on oxygen. If this undergoes resonance, negative charge can come here. Then it can go downwards. Then it can come this side, right? Negative charge is spread on 1, 2, 3, 4 carbon atoms. But here, one oxygen atom alone is enough, right? One oxygen atom alone is enough. Yeah? One oxygen atom alone is enough to sustain the negative charge, right? Correct, people? Correct. Okay, few more examples. Tell me among these two, which one is, where is the negative charge more stable? Where is the negative charge more stable? Quickly, you have to answer this question. Where is the negative charge more stable among these two? I'm asking you. First or second? Quickly. See, this can undergo resonance and this bond will shift in this direction, due to which oxygen will get negative. So negative charge is on 1 carbon and 1 oxygen. But here, already the negative charge is on oxygen. Now, when it undergoes resonance, this negative charge can come here, or the same negative charge can come here, or the same negative charge can come here. Here, the negative charge was on oxygen. Apart from that, due to resonance, it is coming on 3 carbon atoms. So leave. You cannot decide on the basis of oxygen. Oxygen. In both the cases, you have got 1 oxygen atom. But here the dispersal is more. More the dispersal, more is going to be what? More is going to be stability. So second is more stable. Yes. Second is more stable. You can check it like this as well. Over here, you can find 2 resonating structures. Here, you can find more than 2 resonating structures. If the negative charge bearing capacity is same, more the resonating structures, more the stability. In short, more the resonating structures, more the stability. In short, because more the resonating structures means more the dispersal of charge. More the dispersal of charge means more is the stability. Look at the next one. First or second? Quickly. First or second? I'm asking you. Quickly, guys. See, if there is resonance, this negative charge can come on this oxygen as well. So negative charge here is coming on 2 oxygen atoms. Here, negative charge is on 1 oxygen, and due to resonance, it can maximum come on these carbons. It can come on these carbons, right? But here the negative charge due to resonance is coming on 2 oxygen atoms. And you know, negative charge carrying capacity of 1 oxygen is greater than that of 10 carbons. Over here you have got 2. So which one is, where is the negative charge more stable? Of course 1. Of course 1. Right? One is saying still, you're saying 2. Why 2? No. Here, negative charge is coming on 2 oxygen atoms due to resonance. Here you have got only 1 oxygen atom, and apart from that, there are carbon atoms. Right? 2 oxygen atoms carrying, negative charge is spread between 2 oxygen atoms. See how stable it is going to be. Yeah? I hope this is clear. Okay, if this is clear, tell me the answer of this question. Tell me the answer of this question. Stability order among these 3. Where is the negative charge more stable? First, second, or third? Arrange the following on the basis of stability order. Quickly. Quickly. Now, this question, everyone has to answer properly. Everyone has to answer properly. People are saying ACB, matlab 1, 3, 2. People are saying 1, 3, and 2. Are you sure? Are you 100% sure? See, this will come here, this will come here. So the negative will come here. So negative is coming on 2 oxygen atoms, right? Here there is no oxygen, so nothing to do with that. 1 oxygen is already there. And apart from that, negative charge can come here, it can come here, it can come here. Perfect. So 2 oxygens will be playing a greater role. So A, then followed by C, followed by B. Absolutely, you all are right. Good job. That means you are getting things. Wonderful. Wonderful. Okay. Tell me the answer of this question. A, B, C, D, E, F. Arrange them on the basis of stability. Arrange them on the basis of stability. Till then I can have some water. Arrange them on the basis of stability. Arrange them on the basis of stability. Arrange them on the basis of stability. Let me see who is going to answer this question correctly. Guys, these are 6 molecules. These are not only 4. There is EF also in the bottom. There is EF in the bottom as well. People are saying DEBCFA. Is that? Is it DEBCFA? Let's have a look. First of all, look at all these structures and see where do we have maximum oxygen atoms. No oxygen. 1. Here you have got nitrogen as electronegative. 1 oxygen, 1 oxygen. Okay, here you have got 2 oxygen atoms. If here you have got 2 oxygen atoms, that means due to resonance, this negative charge can come here as well. So negative charge is spread between 2 oxygen atoms, right? So D is going to be maximum stable. Leave D aside. Done and dusted, right? Now, look at those molecules wherein there is 1 oxygen atom. Here you have got 1, here you have got 1. But apart from that, no doubt, this will undergo resonance and oxygen will get the negative. So among these 2, there is 1 oxygen. But at the same time, this will carry more resonating structures, more charge dispersal, more stability. So E will be more stable than that of B. So these 2 are gone. Okay. Now, A, C, and F. A, C, and F. In A and F, there is no electronegative element. But here you have got electronegative element nitrogen. So it will undergo resonance. Negative charge will come on nitrogen. Negative charge on electronegative element makes it highly stable. So C will be more stable. So leave C aside. Now among A and F, there is no oxygen, no electronegative element. So decide directly on the basis of resonating structures. There are 2 resonating structures. Here will be many resonating structures, right? Here you'll get many resonating structures, right? Here you will get many resonating structures. More the resonating structures, more the charge dispersal. More the charge dispersal means more the stability. So this is the stability order. How many of you gave this order? How many of you gave this order? DEBCFA. DEBCFA. Someone is saying 4, 5. Guys, I'm unable to relate. What is 4, 5, 3, 2, 6, 1? Is it same as that of DEBCFA? So honestly, the ones who gave the correct answer, just say yes in the chat. Honestly, who gave the correct answer, just say yes in the chat. Quickly. Just say yes in the chats once. Yeah? Perfect. Okay, if this is perfect, then, just a second. Tell me, where is the negative charge more stable among these two? Where is the negative charge more stable? Now it is simple. Okay, this is your sp hybridized carbon. This is your sp2 hybridized carbon. S character more the S character, more the electronegativity. Negative charge is more stable on more electronegative, right? These sort of questions are pretty much simple. Now guys, there is one more important thing. Okay, before talking about that important thing, tell me the stability order here. 1 or 2? 1 or 2, quickly. 1 or 2. See, this is your sp2 hybridized. Even this is your sp2 hybridized. If hybridization is same, now see whether resonance is happening in anyone. Here you can see it can undergo resonance, right? But this cannot undergo resonance, right? This cannot undergo resonance. So resonance is possible in A. So wherever there is resonance, more stable. So A is greater than B. Yeah? Okay. So first one, see, hybridization in both the cases same. So I did not decide on the basis. Everywhere, whenever these sort of question comes, first point is you will have to decide on the basis of hybridization. If you're unable to decide on the basis of hybridization, then go for resonance. Okay, then go for resonance. I hope this is clear. Now guys, what is resonance basically? The partial overlap of pp orbitals. The partial overlap of orbitals, right? If you remember, how did we define resonance? It is the partial overlap of parallel p orbitals. Correct? Overlap. If it is the overlap, can I say 2p overlap? Extent of overlap in 2p is more than that of 2p 3p, is more than that of 2p 4p. Okay? So again, I'm making you understand one simple thing. See, how did we define resonance? The partial overlap of parallel p orbitals, right? So resonance is basically overlap. Resonance is basically overlap. So extent of resonance depends on the strength of overlap. Extent of resonance depends on the strength of overlap, and strength of overlap in 2p is maximum, followed by 2p 3p, followed by 2p 4p, right? And do remember, extent of resonance is basically directly proportional to what? It is basically directly proportional to stability, right? And extent of overlap, it is directly proportional to strength of overlap as well. From this particular statement also questions are asked. Now the point is what kind of questions? Are asked from this particular statement. See guys, understand one thing. Can you let me know where will be the extent of overlap more? Extent of overlap. Where will be the resonance more? Where will be the extent of resonance more? Where will be extent of resonance more? Where will be stability more? Tell me that. Quickly. My dear students, if you look at this particular carbon, it's sp2 hybridized, right? It is sp2 hybridized. So this is the vacant 2p orbital. Here, this particular lone pair, this oxygen has got two lone pairs, among which, if I talk about one lone pair is in 2p orbital as well. So here it will be 2p overlap. But here it's going to be 2p 3p overlap, right? Now, which overlap is effective? 2p overlap is effective. If 2p overlap is effective, extent of resonance in the first one will be more. Stability of the first one will be more. Simple. Right? Is this clear? Or if you want to have a look on the first case again, just have a look. Just have a look properly. First of all, this carbon, it has got 2s, 2p2, right? This is 2s carrying one orbital, 2p carrying three orbitals. Now this particular carbon, it is forming how many sigma bonds? It is forming 3 sigma bonds, right? One here, one with hydrogen, 3 sigma bonds. Perfect. It's forming 3 sigma bonds. Perfect. Its hybridization is sp2. And there will be one pure p orbital. So this is sp2 hybridized, and there is one pure p orbital. Similarly, there is one pure p orbital here, and these two orbitals have overlapped parallelly and formed a pi bond. This is understood? This is understood? Now, if you look at this particular oxygen, it carries two lone pairs. Out of these two lone pairs, is any lone pair conjugated? Pi sigma lone pair. One of the lone pair is conjugated. Let's assume this lone pair is conjugated. That lone pair which is conjugated is not considered for hybridization. Now tell me, how many sigma bonds? 1, 2. 2 sigma bonds and 1 lone pair. So 2 sigma bonds, 1 lone pair. 2 plus 1, 3. 2 plus 1, 3 means this sp2. If this is sp2, that means this lone pair, it is present in this lone pair. It is present in pure p orbital. One of the lone pair is present in pure p orbital. Right? It's present in pure p orbital. Now, which orbital of oxygen? Which orbital of oxygen? It is 2p orbital of oxygen. So the overlap here is going to be 2p, 2p overlap. But here it's going to be 2p, 3p. And you know, strength of overlap. 2p, 2p overlap is more effective than 2p, 3p. So wherever overlap is more, you will say extent of resonance is more. Correct? Even guys, if you remember, I had told you, in the beginning I had told you, the order of high energy electrons. I had told you the order of energy of high energy electrons, basically. I had told you negative charge with unshared pair, its energy is more, if you remember, right? Then comes your lone pair. Then comes your this particular electron pair of pi bond. Then comes the electron pair in the triple bond, the pi bonds in triple bond. This particular stuff I've told you already, if you remember. This particular stuff I've told you already. This particular stuff I've told you already. I hope you remember. I gave you the energy order. I gave you the energy order, right? I gave you the energy order already. What is resonance? If I ask you what is resonance, it is the delocalization of high energy electron pairs. Resonance is the delocalization of high energy electron pairs. Now that electron pair which will be having highest energy, that will get delocalized the maximum. The one which gets delocalized the maximum, there only I will say extent of resonance will be more. Right? Are you trying to get all these things, whatever I'm saying? Is it clear? What is resonance? Resonance is the delocalization of high energy electron pairs. Now that electron pair which will be having highest energy will be delocalized the maximum. And wherever delocalization is maximum, I'll say extent of resonance is maximum. And wherever extent of resonance is maximum, I'll say stability is maximum. I'll say stability is maximum. Right? So this is the energy order. This is the energy order. Why am I giving you this energy order? There's a logic behind that. Now, tell me among these two. Okay, answer is already written. Among these two, where is the extent of resonance more? Look at this. This is negative with unshared pair of electron. This is the lone pair here, right? Pi sigma lone pair, resonance. Pi sigma negative charge with unshared pair of electron. Now, which is this electron? I mean, are these electrons or these electrons? Among these two, which electron pair is high energy? This is the higher energy electron pair. The one which is high energy electron pair will do more delocalization. More delocalization means extent of resonance will be more. Extent of resonance will be more means stability will be more. Yes? Right? Okay. What about this one? Order of extent of resonance. My God, answer is already given here. What is this? What is this? Anyways, this is pi, this is sigma, vacant orbital. Pi, sigma, vacant orbital, right? This is pi, this is sigma, and this vacant orbital. Correct? Where is the extent of resonance more? Where is the extent of resonance more? Which concept you guys are going to use here? What is resonance? You'll simply remember the definition of resonance. Delocalization of high energy electrons. Right? Higher the energy of the electron pairs, more is the delocalization. More delocalization means more resonance. The answer is done. Now, you tell me the answer of this question. This is the pi bond of the double bond. This is the pi electron pair of the double bond. This is the pi electron pair of the triple bond. Which one is having more energy? Pi electron pair of double bond has got more energy than that of pi electron pair of triple bond. So, I would say in the first one, extent of resonance will be more. Simple. Right? Clear? Clear, guys? All right. Can you answer this question? 1, 2, 3. Which one is where? Which resonating structure is more stable? Give the order. Give the order. Over here, 1, 2, 3, 3 bonds. 1, 2, 3, 3 bonds. 1, 2, 2 bonds. Right? I think we can easily do this. We have done these sort of resonating structure questions. I'm not going to waste my time on this. Now let's move on to steric inhibition of resonance. Steric inhibition of resonance. This is something, guys, which will eat your brain. This topic will eat your brain. But before discussing this topic, I need a break for 10-15 minutes. You also take a break for 10-15 minutes. But be back. This is something from which you'll be getting the toughest questions. This is something very, very, very important. You are not going to understand this on your own. No way. And the questions which I've come up with this, right? In this particular topic, the questions which I've come up with. By solving those questions, I mean, nothing is left. You can easily solve all the types of questions asked. Okay? So should we take a break? So what time you guys will be back? I think 11:10. So is it a promise you'll be back at 11:10? Is it a promise that you guys will be back at 11:10? 11:10. Okay. Guys, be back, okay? Be back, be back. Or if after coming back, if the students would be less, maybe I will have to cancel the session then. Yeah. So I'll expect all of you, all the students who are watching me right now, I'll expect you guys to be back at 11:10 so that we can start the steric inhibitions of resonance, right? See you. See you in some time. What's up? What's up, guys? All back with the new energy? Yeah? Let me know in the chats. Is everyone back? Is everyone back? Okay, so let me know quickly if all the things are clear till here. Yes or no in the chats with the fire emojis. I don't want you guys to sleep. So keep on typing in the chats. Let me know quickly. Are all the things perfectly clear till here? Are all the things perfectly clear till here? Now, guys, we have to discuss something really, really important. I want some fire emojis in the chats first. I want some fire emojis in the chats. Quickly. Everyone. Everyone. I want some fire emojis in the chats, then I'm going to start. I need some fire emojis in the chats, then I'm going to start, people. Quickly. Okay, so let me know once in the chats, have you studied this particular topic before? Steric inhibition of resonance, SIR. Have you studied this particular topic before? Let me know with yes or no in the chats. Let me know with yes or no in the chats. So majority is saying no. Then let's get going. Let's get started and let's see what this steric inhibition of resonance is all about. My dear students, try to understand. Try to understand very carefully because this is something which might confuse you a bit. Okay? This might confuse you a bit. All right. So let's try to understand what this SIR, steric inhibition of resonance, is all about. My dear students, for example, over here I'm taking one benzene ring. Right? This is one benzene ring. At the top of the benzene ring, I'm attaching a group. Let's say this is nitrogen, this is R, and this is R. This R is the alkyl group. Okay? First of all, if I ask you, how many electrons are in the valence shell of nitrogen? You'll say 5. Out of 5 electrons, nitrogen have used how many electrons for bonding? 1, 2, 3. So can I say there'll be a lone pair on this nitrogen? Yes, there is a lone pair on nitrogen. Absolutely, there's a lone pair on nitrogen. Okay, number 1. Similarly, over here, what exactly am I going to do? I'm going to take one more benzene ring. This is a benzene ring, for example. At the top of it, I'm attaching, this is N, this is R, right? And there is a lone pair on nitrogen. And apart from that, I'm attaching one more group R over here. Perfect. These are the 2 molecules which I've taken into consideration. Now, first of all, do you see this lone pair in conjugation with this ring? Pi sigma lone pair. Absolutely, it's in conjugation, right? Similarly, pi sigma lone pair. Conjugation is there. Perfect. Conjugation is there. My dear students, can I say this lone pair will participate in resonance? Absolutely, this lone pair will participate in resonance. So basically, this lone pair will shift here, due to which right here you will get a double bond. So this lone pair is going to participate in the resonance. Similarly, here also the lone pair is going to participate in the resonance. What is resonance? Resonance is partial overlap of p orbitals. So basically, if you look at this particular nitrogen, it is forming 3 sigma bonds. 3 sigma bonds. Since this lone pair, it is participating in resonance, so I'm not going to count this for hybridization. So if I ask you what is the hybridization of nitrogen here, leave this lone pair aside. 1, 2, 3. So it is sp2. This sp2 hybridized, right? If I talk about this particular carbon, even this sp2 hybridized. Perfect. Correct. Now, my dear students, this nitrogen is sp2 hybridized, right? Nitrogen's outermost configuration, 2s2, 2p3, right? This is 2s, and these are 3p orbitals of nitrogen. Perfect. Nitrogen has undergone sp2 hybridization. sp2 hybridization. That means there is a p orbital which is carrying this lone pair, right? So can I say on this nitrogen, since it's sp2 hybridized, perfect. sp2 hybridized means trigonal planar. Trigonal planar means all these bonds, this bond, this bond, this bond, they are lying on the same plane. Imagine these 3 bonds, they are lying on the board. Yes, they are lying on the board. In the similar way, this carbon is also sp2 hybridized, trigonal planar. So this bond, this bond, this bond, like all these bonds are basically lying on the board, Perfect. Since this nitrogen is sp2, so it will be having one pure p orbital which will be perpendicular to the plane, for example like this. Similarly, this carbon, it is also sp2, so it will be also having one p orbital. So if I show it to you like this, all these bonds, they are present on the board, and this nitrogen has got the p orbital, this carbon has got the p orbital, so these p orbitals can overlap, right? What is resonance? Partial overlap, right? So these p orbitals can overlap. These are 2 parallel p orbitals which can overlap, right? Now, my dear students, try to understand one simple thing. Due to the partial overlap, can I say a double bond character gets generated over here between nitrogen and carbon? So between nitrogen and carbon, I would say between nitrogen and carbon, due to resonance, a partial double bond character gets developed. Due to nitrogen and this carbon, partial double bond character gets developed. Look at this particular scenario. This nitrogen has got the p orbital. Even this has got the p orbital. Now, my dear students, you have attached a bulky group over here. This is a bulky group. This is a bulky group. Over here, this is a bulky group. Can I say between 2 bulky groups, there will be repulsions? Steric hindrance, there will be repulsions. Due to repulsions, these p orbitals which were supposed to be parallel, due to repulsions, the orientation of this particular group will change. What does that mean? That means the p orbitals which were supposed to be parallel like this, right? Parallel coplanar. Orientation of this particular group, for example, will change like this. It was supposed to be like this, it will change like this. If the orientation of this particular group changes, that means this p orbital, which was at the top, its orientation will change. It will go like this. It will go like this. Due to the change in the orientation of p orbital, will there be now effective overlap or ineffective overlap between these two? You tell me in the chats. Will there be effective overlap or ineffective overlap? Quickly. Will there be effective or ineffective overlap now? Effective or ineffective? Quickly. There will be ineffective overlap, right? Yes. So these 2 p orbitals, they were supposed to be parallel and coplanar. Now, due to the repulsions, the orientation of the above group has changed, and this particular white colored p orbital, right? It will change. Its orientation will change. If its orientation changes, what will happen? Extent of overlap. Will it increase or decrease? Can you let me know where is the extent of overlap more? Among these two, where is the extent of overlap more? I'll say extent of overlap will be more here. So basically, when you attached a bulky group here, extent of overlap decreased here. Or I would say extent of resonance that decreased drastically. Right? I'll say upon the introduction of the bulky group, understand it carefully. Upon the introduction of the bulky group, what happened? I'll say extent of resonance decreased drastically. So due to SIR, due to steric, this effect is what you call a steric inhibition of resonance, right? Due to SIR, the extent of resonance that drastically decreases. No doubt, resonance will be there. Resonance will be there. But the extent of resonance will be less. Extent of resonance will be less. And due to resonance, there will be partial double bond character here, right? Absolutely, there will be partial double bond character. There will be partial double bond character here also between nitrogen and carbon. But, you know, upon the introduction of this bulky group, extent of resonance has decreased. Now, you tell me one thing. Due to resonance, this bond, it was a pure single bond first. It was a single bond, right? It was a single bond. And due to resonance, can I say a double bond character got established here? Yes, the double bond character got established. Similarly, here also, it was a single bond, but due to resonance, I would say double bond character got established here. Double bond character got established here, right? Now, you tell me one thing. Where is the extent of resonance more? In the first one, extent of resonance is more. If the extent of resonance is more in the first one, can I say this particular bond would have got more double bond character? Comparatively, this particular bond would have got lesser double bond character. Can I say something like that? Just to make you understand, for example, now the bond order of this particular bond is, let's say, 1.5. Imaginary numbers. Here it will be, bond order will be 1.3. Correct? Yes. Yes, people, is this clear? These are just imaginary numbers which I'm giving you just to make you understand. So basically what I'm trying to convey over here, due to steric inhibition of resonance, extent of resonance decreases, right? Due to resonance, this particular single bond was getting double bond character. Even this got the double bond character. But wherever extent of resonance will be more, there only double bond character will be more. So double bond character in this particular case, double bond character in the first case will be more, and double bond character in the second case will be comparatively less, right? Now, you know, bond order is directly proportional to bond strength, and which is inversely proportional to bond length. So if I have to compare this particular bond length, let me call this bond length as 1. Let me call this as bond length as 2. Can you give me the order of bond lengths? Can you give me the order of bond lengths? Here the double bond character is more. Double bond character more means less bond length. So 1 will be less than 2. 1 will be less than 2. Is this clear? Is this clear, people? Is this clear, people? See, due to resonance, double bond character got established. Due to resonance, double bond character got established. But where is the extent of resonance more? Here the extent of resonance is more, right? If the extent of resonance is more, that means here double bond character will be more in this particular bond. If double bond character is more here, that means this particular bond length will be comparatively less, and this particular bond length will be comparatively more. I believe it's clear. I believe it's clear now. Right? Why all this happened? Because this group and this group, they showed some repulsions, due to which orientation of this group changed, right? Its p orbital slightly got tilted, due to which ineffective overlap happened. Extent of resonance decreased drastically, right? Extent of resonance decreased drastically. I hope this particular point is clear. I hope this particular point is clear. So do remember one thing. Steric inhibition of resonance, SIR. It is directly proportional to repulsions, basically. More repulsions means more SIR. More SIR means less extent of resonance. Right? So can I say something like this? SIR, it's directly proportional to what? It's directly proportional to repulsions between these bulky groups, right? And if repulsions are more, extent of resonance will be. If repulsions are more, this p orbital will go more away from it, extent of resonance will be less, right? So SIR is inversely proportional to what? It is inversely proportional to extent of resonance. And repulsions are directly proportional to what? Size of these groups. So it is directly proportional to size as well. Perfect, right? I hope this is clear. If this is clear, just remember one thing. Just remember one thing, then I'll make you understand some beautiful questions I'm giving you. Just remember, first of all, this particular slide. These are the groups which basically show SIR. Right? R, CHO, COOH, CONH2, NO2, COR, COCl. All these groups, they contribute towards what? They contribute towards SIR. They show SIR. You have to remember that. You have to remember that. Now, where do I use this particular concept? Guys, please and please have your eyes properly on the screen now. Have your eyes properly on the screen now. See, where do I use all this SIR concept? See what kind of questions are asked in SIR. Try to understand. First of all, this particular bond length is represented by X. This particular bond length is represented by Y. I have to compare these bond lengths. I have to show which bond length is more, which bond length is less. First of all, you know, bond order is directly proportional to bond strength, and bond strength is inversely proportional to bond length. Right? This is something which you all know. This is something which you all know. My dear students, do you see any sort of conjugation here? Do you see any sort of conjugation here? Quickly. What do you think? Do you see any sort of conjugation here? Yes, you can see. This is chlorine. Chlorine, it has got 3 lone pairs, right? Because in its outermost shell, there are 7 electrons. So 2, 4, 6, 1, 7. Right? If you look at this particular, this is pi, this is sigma, this is lone pair. This lone pair can come here. This can go here. Perfect. So can I say this bond, which was supposed to be pure single, due to resonance, this bond is getting partial double bond character? This bond got the partial double bond character. But over here, do you see any conjugation? There is no conjugation. It's a pure single bond. It's a pure single bond here. Here, you have got partial double bond character. Here, it is pure single bond. Where is the bond order more? Bond order is more here. More the bond order, lesser the bond length, right? So X will be less than Y. Agreed? Is that clear? Say yes or no in the chats if it's clear. Everyone. Say yes or no in the chats if this point is clear. This was a basic question. This was a basic question. Yeah? Guys, everyone in the chat, say yes or no in the chats quickly. Don't take this much of time. Okay, if this is clear, let's move on to one more. Let's move on to one more. Okay. Now, I'm going to use all the concepts which we have discussed till now properly. See, guys, this carbon-carbon bond length is represented by X. This is represented by Y. This is represented by Z. I have to arrange these bond lengths. Okay? Try to understand. There is no conjugation. It's a pure double bond. It is a pure double bond. It's a pure double bond. Here, if you look at nitrogen, nitrogen has got the lone pair. It can show resonance. It can show resonance. Now try to understand. Try to understand. This bond, it was double. It was a double bond. Now due to resonance, this double bond, it is getting partial single bond character. It was double in the beginning, right? Due to resonance, it became partial double. Here it was mentioned as purely double. But due to resonance, we know it's going to be partially double. Yes, it's going to be partially double. Look at this particular case. Look at this particular case. Oxygen carries a lone pair here. Perfect. So one of the lone pair will participate in the conjugation. This double, it will also get partial single bond character. Right? Perfect. So this is purely double. This is partial double. This is partial double. Now try to understand one thing. Try to understand one thing. Nitrogen and oxygen, compare their electronegativity. Can I say oxygen is more electronegative than nitrogen? Yes. Oxygen is more electronegative than oxygen. Sorry. Oxygen is more electronegative than nitrogen. If oxygen is more electronegative than nitrogen, can I say this oxygen will be holding its electron pair firmly? Can I say this oxygen will be holding its electron pair firmly as compared to this nitrogen? If this oxygen is holding its electron pair firmly, tell me whether the extent of resonance in this particular case be more or less than that of second one. Among 2 and 3, where will be the extent of resonance more? Here, comparatively, this lone pair is easily available. This is not easily available. right? Wherever lone pair is easily available, I can say there only extent of resonance will be more, right? Extent of resonance will be more. Right? Extent of resonance will be more. So extent of resonance is more here. Extent of resonance is more here. You got to know extent of resonance is more here. Now understand one thing. This was a double bond. Due to resonance, it's getting single bond character. Due to resonance, its bond order is decreasing. Understand it like this. Its bond order is decreasing, for example, due to resonance. If extent of resonance is more here, can I say bond order will be decreased more? Can I say bond order will be decreased more here? Bond order will be decreased more here as compared to this one, right? Bond order will be decreased more. So here you will be having lesser bond order, less bond order as compared to this one. Less bond order means more bond length. Less bond order means more bond length, right? Less bond order means more bond length. So among these two, I'll say Y bond length will be greater than Z, will be greater than Z. And since it's a pure double bond, its bond length will be least. Did you get this concept? Did you get this concept? Say yes or no in the chat. Did you get this concept? See guys, here it's a pure double bond. So bond length least, pure double bond length least. Now, due to resonance, bond order is decreasing. Here it was pure double bond. Now it's partial double, pure double, partial double, right? Okay. This double bond is getting single bond character due to resonance. This double bond is also getting a single bond character here, right? Now extent of resonance is more here. Wherever extent of resonance is more, the bond order is decreasing. Technically bond order is decreasing. Technically here also bond order is decreasing. Now where extent of resonance is more, bond order would have decreased more. So bond order would have decreased more here. Lesser the bond order, more the bond length. So Y greater than Z greater than X. Yes? Yes? Let me take few more examples. Let me take few more examples so that it will be properly clear. See, first of all, this is a pure double bond. Pure double bond. Here you have got oxygen, right? It has got the lone pair. So it will participate in the resonance. It will participate in the resonance. Due to resonance, this won't be pure double. It will be partial double. So this double is getting single bond character basically, right? This double is getting single bond character. Now here, as you can see, this again oxygen, right? This will go in this way. Perfect. Right? Or I can write it like this. I can write this molecule like this. Have a look. Have a look properly. This is O. Then you have got methyl. This is your CH. This is double bond. This is CH. This is N. This is double bond. And this is O. This is the structure basically. Correct? Now what is going to happen? This oxygen carries the lone pair. Perfect. It has got the lone pair. This will come this way. Right? Perfect. This will shift in this way. And this will go here, for example. So this particular double bond, due to resonance, it is getting partial double bond character. I mean, this double bond is getting single bond character due to resonance. Due to resonance, it's getting single bond character. Now you tell me one thing. It's a pure double bond here. Pure double bond. This is partial double bond. This is partial double bond. Pure double bond will have least bond length. Correct? Will have least bond length. Now among these two, double bond is getting converted. Double bond is getting single bond character. Double bond is getting single bond character. That means bond order is decreasing here also. Bond order is decreasing here also. Now, if I ask you among these two, where is the extent of resonance more? My dear students, have a look. It is starting from here. It is ending here. See, over here, extent of resonance is starting here. Resonance starting here, ending here. Right? So where among these two, where is the extent of resonance more? I'll say extent of resonance is more here. Right? It is extended conjugation. Extent of resonance is more here. More the extent of resonance, due to resonance, this double bond, its bond order is decreasing. More the resonance, more the decrease in bond order. So this bond order will be less So this bond length will be more, right? So Z will be more than Y, Y will be more than X. Can you understand this? Can you understand this quickly? So it's 3 to 1. Is it clear? Is it clear now? Is it clear, people? Right? I hope you got it. So that's why I'm telling you, be attentive here, be attentive here, be attentive now. Compare these bond lengths. Here it's a pure single bond, pure single bond, pure single bond, pure double bond. Over here, nitrogen has got lone pair, pi sigma lone pair, resonance. Right? Pi sigma lone pair, resonance. So this will get partial double bond, this will get partial double bond. This is pure single bond, this is pure double bond. Pure single bond has got maximum bond length and pure double bond has got minimum bond length. These two we already knew. I'm telling you the bond length order, right? We just have to compare these two. We just have to compare these two. Understand carefully. Due to resonance, it was a single bond. This single bond is getting double bond character. This single bond, due to resonance, is getting double bond character. Now, where is the extent of resonance more? This pi sigma lone pair. This pi sigma lone pair. Extent of resonance is more here. More the extent of resonance. Due to resonance, it was single. It is getting partial double. So its bond order is increasing. Here also, bond order is increasing. It was single. Now due to resonance, it is getting partial double bond character. So bond order is increasing basically, right? So wherever extent of resonance is more, bond order will increase more there only. So here, bond order will be more. This particular bond order will be more comparatively. Bond order more means less bond length. Bond order more means less bond length, means less bond length. So 4 will have less bond length than that of 3. Did you get this? Did you get this? Did you get this? Yes, Manjula, you're right. Did you get this concept? I hope you got it. Okay, one more. One more. One more, have a look. This particular bond length and this particular bond length, 1 or 2. Give me the relation between 1 and 2. See guys, understand. This is pi sigma lone pair, right? This is pi sigma lone pair. It was a single bond. Here also single bond. Now due to resonance, it will get double bond character. Due to resonance, this bond will get double bond character. This NC bond. This will also get double bond character. So due to resonance, bond order in both the cases is increasing. Due to resonance, bond order is increasing in both the cases. Now people, what kind of resonance it will show? This will go here, right? This will go here, this will come here, and this will go here. Perfect. So negative charge at the end on this particular carbon. This will go here. Perfect. This will go here, and this will go here. Negative charge on oxygen. Where is negative charge more stable? Negative charge on carbon, negative charge on oxygen. Oxygen has got more negative charge carrying capacity. So where is the extent of resonance more? First or second? Extent of resonance is more in second. More the extent of resonance. See, due to resonance, bond order is increasing. More resonance, more increase in bond order. So this bond order will be more. More bond order, lesser bond length. So 2 will be less than 1. Right? Yes? Perfect. I hope this is clear. Now. Compare the bond length. Compare the bond length. This particular bond length is represented by 1. This is represented by 2. Okay. Now, first of all, what will happen? Due to resonance, you'll get a double bond character here. Due to resonance, you'll get a double bond character here. Right? So single bond is getting converted into partial double bond. This single bond, due to resonance, is getting converted into partial double bond. So in both the cases, bond order is increasing. Bond order is increasing. From single to partial double, single to partial double. Bond order is increasing in both the cases. Now try to understand. This is NO2. On the side of it, you have got Br. And I say this Br is going to show SIR on this side. And I say it will experience SIR on this side. Right? Similarly, you have got NO2 on this side as well. I mean, you have got Br on this side as well. So on this side also, can I say SIR will operate? So NO2. From two sides, SIR is operating. From two sides, SIR is operating. Here, only one side, SIR is operating. Only one side, SIR is operating. Due to SIR, extent of resonance will be less. Extent of resonance will be less due to SIR. Where is the SIR more? Here, SIR is more. Extent of resonance will be less here. Right? And due to resonance, what was happening? Bond order was increasing. Bond order was increasing. But extent of resonance is less here. That means extent of resonance is more here. More extent of resonance means more increase in bond order. More increase in bond order. Right? So bond order here will be more. More bond order means lesser bond length. Right? 1 less than 2. Be careful, guys. Be careful. Yes? Either you can say 1 less than 2 or you can say 2 greater than 1. Perfect? I believe this is clear. Okay, one more. One more. One more. Have a look. Have a look. This bond length I'm calling 1. This bond length I'm calling 2. Compare the bond lengths quickly. Compare the bond lengths quickly. Try to understand carefully. Due to resonance, first of all, this was a single bond. Due to resonance, it will get partial double bond character. Due to resonance, this will get partial double bond character. Right? It will get partial double bond character. Right? So basically, it was single. Now it is getting partial double bond. So its bond order is increasing or decreasing? Its bond order is increasing basically. Similarly, due to resonance, its bond order is also increasing. It's getting partial double bond character. Its bond order is increasing. But here we have got SIR. Here we have got SIR, repulsions. SIR. Due to SIR, extent of resonance decreases. Here, extent of resonance will be less. Here, extent of resonance will be more. More the extent of resonance. Due to resonance, bond order is increasing here. If extent of resonance is more, bond order will increase more here. If bond order here is more, that means this bond length will be less. So 2 will be less than 1. Or 1 will be greater than 2. You can say like that. Yeah? You're killing it. Nice. Good. Right? Perfect. One more question. One more question. Compare the bond lengths. This is 1, this is 3, and this is 2. This is single. Due to resonance, it will get partial double bond character. It was single. Due to resonance, it will get partial double bond character. 1 is getting partial double bond character. This 2 also is getting partial double bond character due to resonance. 3 is also getting partial double bond character due to resonance. But if you look carefully, this will operate SIR from here. This will operate SIR from here. Right? Over here, there won't be any SIR. Due to SIR, extent of resonance is less. So among all these three, where will the extent of resonance more? Extent of resonance is more here. Right? Due to resonance, bond order is increasing. This was 1 initially. Now it's partial double bond. Right? Due to resonance, bond order is increasing. So extent of resonance will be more here. More the extent of resonance, more will be the increase in bond order. More will be the increase in bond order. So bond order here will be maximum. So bond length will be minimum. 3 minimum. Right? Now 1 and 2, they'll be equal. 1 and 2, they'll be equal. Right? 1 and 2 will be equal. Yes, 1 and 2 will be equal. Because here on one side SIR, here also on one side you're getting SIR. Perfect. I believe this is also clear. Perfect. And you should be able to solve these sort of questions now, guys. You should be able to solve. Okay, one more, which might confuse you a bit. One more, which might confuse you a bit. Sorry. Guys, don't look at time. Try to understand things. Try to learn things. Don't look at time. It's going to take still a long time. It will take a lot of time. It will take 3-4 hours more. So do not look at time. Look at the slides. Try to understand it. Try to understand it properly. Okay? Chalo, tell me about this one. See, due to resonance, this will get double bond character, this will get double bond character, this will get double bond character. Right? Initially, it was a single bond. It was a single bond everywhere. Everywhere it was a single bond. Now they're getting double bond character. So all the 3 bonds are getting double bond character. Right? All the 3 bonds are getting double bond character. So bond order of all these 3 bonds is increasing due to resonance. Due to resonance, bond order of all these 3 bonds are increasing. Now, SIR from this side, SIR from this side, SIR from this side, right? This will operate SIR from this side. Perfect. Now guys, 3 and 2. In 3 and 2, SIR is operating only on one side. But here, SIR is operating on two sides, right? SIR is operating on two sides. If SIR is operating on two sides, extent of resonance will be least here. Extent of resonance will be least here means, what does that mean? Extent of resonance is least here. That means extent of resonance in these two will be comparatively more. If extent of resonance in these two is more, that means bond order would have increased more in these two, right? Bond order more means bond length less. So 2 equal to 3, which will be less than 1. Did you give this answer? 2 equal to 3 less than 1. Right? I believe it's clear. Okay, one more type of question. One more type of question. Compare the acidic strength of hydrogen. Which hydrogen is more acidic, which hydrogen is less acidic? Try to understand. Compare the acidic strengths of hydrogen. These are the hydrogens which I have given, right? You have to compare their acidic strengths. How do you compare their acidic strength? My dear students, if you take this hydrogen out as H positive, there will be negative charge on this oxygen. If you take this hydrogen out as H positive, negative charge here. Take it out, negative charge here. Take it out, negative charge here. Perfect. Now that hydrogen, which after leaving gives more stable conjugate base, that hydrogen which after leaving gives more stable conjugate base, that hydrogen is going to be more acidic. That hydrogen is going to give, that hydrogen will be more acidic, which will give more stable conjugate base. Now we have taken H positive out, oxygen carrying negative. Now it can participate in resonance. If it participates in resonance, can I say negative charge is shared by 2 oxygen atoms due to resonance? It is on 2 oxygen atoms. And you know how stable negative charge is on oxygen? Perfect. Here negative charge on sulfur. Here negative charge on 1 oxygen. Perfect. So I'll say this conjugate, when hydrogen leaves as H positive, whatever is left here, that is first of all resonance stabilized and negative charge comes on 2 oxygen atoms. So this particular hydrogen will be maximum acidic. Now look at, let's compare this and this. Oxygen carrying negative, sulfur carrying negative. Oxygen and sulfur, do they belong to same period or same group? Same group. Same group. Volume charge density plays a role. More size, less volume charge density. More size, less volume charge density, more stability. So S negative is more stable than O negative, right? So third will be stronger than second. Now compare second and first. Compare second and first. Oxygen carrying negative, nitrogen carrying negative. They belong to same period. Electronegativity. Negative charge is more stable and more electronegative. So I would say 2 will be more acidic than 1. So this is the order of it, which you were supposed to check. Is this clear? Say yes or no in the chats if it is clear. Yes. Say yes or no in the chats if it is clear. If it is clear. If it is clear. This hydrogen or this hydrogen, which one is more acidic? You need to tell me. First or second, which hydrogen is more acidic? Do not go directly. Do not jump directly into resonance. First, check with the help of hybridization. Check with the help of hybridization. Take this H positive out, negative here. Take this H positive out, negative here. This negative is at sp2 carbon. This negative is at sp carbon. Negative charge is more stable on more electronegative. This is more electronegative, right? Negative charge is more stable. So I'll say acidic strength of second hydrogen will be greater than that of first. So first you have to see hybridization, then go for resonance. Look at this one. Look at this one. Look at this one. When you take H positive out, this is negative. When you take H positive out, this is negative. Perfect, right? This sp2, this sp2. Both are sp2. You are unable to decide as per hybridization. Now what is left? Resonance is left now. Now check. This negative, I mean this getting resonance stabilized. If this hydrogen leaves as H positive, if this hydrogen leaves as H positive, the conjugate base which we get, that's resonance stabilized. So I'll say 1 will be more acidic than 2 here. Right? 1 will be more acidic than 2. I hope you can easily solve these sort of questions from now onwards, right? Now guys, we are going to jump into something called as mesomeric effect. we are going to jump into something called as mesomeric effect. This is again one very important thing. First of all, let me know in the chats if every single thing is clear till here or not. Everyone in the chats. Everyone in the chats. After mesomeric effect, we have to do aromaticity, then hyperconjugation. Okay? So, 3.5 hours more. That's it. But before that, tell me in the chats if every single thing is clear till here or not. Mesomeric effect. Mesomeric effect. Mesomeric effect. Perfect, guys. So what is mesomeric effect? Let's have a look at its definition. Then I'll make you understand what it exactly means. Look at its definition once. Whenever any group creates a charge separation between itself and the conjugated system through resonance. Whenever any group creates a charge separation between itself and the conjugated system through resonance, we say the group is showing mesomeric effect. Now, what it means exactly? Try to understand this, guys. For example, over here, I'm taking a perfectly conjugated system. This is a conjugated system which I have, right? This is a conjugated system which I have. First of all, tell me, is this a conjugated system? Pi, sigma, pi, sigma, pi, sigma. It is one conjugated system. It is a conjugated system here. I've taken a conjugated system. Now, my dear students, towards this conjugated system, let's say I'm attaching a group. I'm attaching a group. Why is it not writing? I'm attaching a group, for example, X. Right? Let's assume that on X there is a lone pair. Let's assume that on X there is a lone pair. So I have taken a conjugated system. And towards this conjugated system, I have attached a group. This group carries a lone pair. First of all, do you see one thing? Can I say this group is in conjugation with this conjugated system? Have a look. Pi, sigma, lone pair. Yes. Pi, sigma, lone pair. The group is also in conjugation with this particular conjugated system. Can I say between this group and this system, there will be resonance? Absolutely, there will be resonance. So, I would say this negative will come here. This will go here. This will go here, right? And so on. Right? Can I say something like this? Can I say something like this? So, this group will show resonance with this system, right? This lone pair will come here, right? And my dear students, when the lone pair comes here, I say this X will get delta positive, right? And this conjugated system will get delta negative. In short, this conjugated system will get delta negative. So do you see charge separation getting created between conjugated system and the group? Between the group and the conjugated system, charge separation got created. And this charge separation got created due to resonance between the group and the conjugated system. Whenever you attach a group towards a conjugated system, that creates the charge separation between the group and the system through resonance, we say that group shows mesomeric effect. So this particular group over here is showing what? Is showing what? It's showing mesomeric effect. It is showing mesomeric effect. Now you tell me one thing. You tell me one thing. Is this group increasing the electron density in the conjugated system or decreasing the electron density in the conjugated system through resonance? It got delta negative. So it is increasing the electron density in the conjugated system through resonance. That group which increases the electron density in the conjugated system through resonance, we say that group shows plus M effect, plus mesomeric effect. Plus mesomeric effect, right? Similarly, my dear students, one more example, understand. This is C, double bond C, single bond C, double bond C, right? This is example of a conjugated system. Now, towards this conjugated system, I'm attaching a group. The group is like this, X, double bond Y. And I'm assuming electronegativity of Y is greater than that of X. I'm assuming electronegativity of Y is greater than that of X. Towards this conjugated system, this is the example of perfectly conjugated system which I've taken. And towards this conjugated system, I've attached a group X double bond Y. Y is more electronegative than X. What is going to happen? Can I say this group is in conjugation with this system? Have a look. Pi, sigma, pi. This group is in conjugation with this system. What will happen? Resonance will happen between the group and the conjugated system. Resonance will happen between these two. And if resonance happens between the two, what will happen? I'll directly say this bond will shift in this direction, this will shift in this direction, this will shift in this direction, and so on. Right? So due to which Y gets delta negative, and this side it gets, this conjugated system gets delta positive. So tell me again one simple thing. When I attached a group towards a conjugated system, charge separation got created between the group and the conjugated system through resonance. Can I say this particular group is operating mesomeric effect here? Yes, it is showing mesomeric effect. Now, is this group increasing the electron density in the system or decreasing? Delta positive. It is decreasing the electron density in the system. And my dear students, that group which decreases the electron density in the conjugated system through resonance, we say that group shows minus M effect. Minus M effect. This is increasing electron density. This is decreasing. If this is increasing electron density, so I'll be calling this as electron donating group through mesomeric effect. This I'll be calling as electron withdrawing group through mesomeric effect. I believe these two terms are clear. These 2 points are clear. Right? As I told you in the beginning, minus always means withdrawing. Plus always means donating. Minus always means withdrawing. Plus always means donating. That's all. That's all. I hope this is clear. And if this is clear, let's have a look on few more things. I believe this is something which I told you already. When the group increases the electron density in the conjugated system, the group exhibits plus M, otherwise minus M. Okay? Otherwise minus M. Let's take few examples. Let's take few examples. For example, I'm taking phenol into consideration. Guys, try to understand carefully what I'm going to say. Let's say this is benzene. Towards benzene, I'm attaching OH. Oxygen, there are 2 lone pairs. Let me show just one. Okay? So, is benzene the example of a conjugated system? Yes, the benzene is the example of conjugated system. And towards this benzene, what I've attached? I've attached a group. Now tell me, oxygen carries a lone pair. Pi sigma lone pair. Can I say this group is in conjugation with this system? Yes, the group is in conjugation with this system. Due to which, what's going to happen? Resonance is going to happen between the two. And if resonance happens, I'll say this particular electron pair will come here. This pi bond will break in this direction. So what do I get? I got something like this. There is a point which I have to mention over here. There is a point which I have to tell you over here. This becomes OH positive, right? It becomes a double bond, right? Here comes a negative charge. Rest everything is same. Now, pi sigma negative. This negative will come here. This bond will break in this direction. So what do I get? Have a look. What do I exactly got? What did I exactly get? Try to understand. Try to understand. This is double, right? This is a negative. This is a negative. This bond is same. And this is same OH positive. Perfect. Now, this is pi sigma negative. This negative will come here. This bond will break in this direction. What do I get here? What do I get here? This is your pi. This is your pi. And this is negative. And on the top, we have got OH positive. Perfect. Again, this is pi sigma negative, right? This will come here. This will go here. So what do I get at the end? What do I get at the end? This is the final thing. This is OH. Okay. This is OH. Now, guys, try to understand one simple thing. Can I say, just tell me one thing. Just tell me one thing. When you attached OH towards a conjugate system, is the Is the electron density in the conjugated system increasing or decreasing through resonance? Just tell me that. Is the electron density increasing or decreasing in the conjugated system due to resonance? Have a look. Negative, negative, negative. So in the conjugate system, electron density is increasing through resonance. Through resonance. Right? So can I say this OH group, which group it is? Is it going to be plus M or minus M? It is showing plus M. It is showing plus M. Number one. Number one. Number two. Do you see electron density getting increased, negative charge coming only at ortho and para positions? Do you see this negative charge is only coming at ortho and para positions? Over here you checked exactly. This negative charge, when you attached plus M showing group towards a conjugate system, you saw the negative charge getting developed only on ortho and para positions. Perfect. Do remember this particular point as well. When you attach a plus M showing group towards a conjugate system, like benzene, the negative charge will be developed on ortho and para position. What does that mean? That means this position is called as meta. That means mesomeric effect. Mesomeric effect. Can I say it does not operate at meta position? It does not operate at meta position. Right? What does that mean? That means the charges are not getting generated, established on the meta positions. Yes? So is this OH ortho para directing here? I hope this is clear. So remember, mesomeric effect will be operated only at ortho and para. It won't be operated at meta. Right? This is one important thing. Perfect? Similarly, guys, one more example I'm giving you. One more example I'm giving you. One more example I'm giving you. This is your conjugated system, your benzene. If this is benzene, I'm attaching C double bond OH here, CHO group, CHO group. Now people, you tell me one thing. I've attached a group towards this perfectly conjugated system. Okay, let's see what happens. This is, if you look carefully, look at this group. This is X double bond Y. X double bond Y. Where Y is electronegative than X. Where Y is more electronegative than X. Already a few minutes back only I showed you. X double bond Y. Y more electronegative than X. It's going to show minus I. Sorry, minus M. It's going to show minus M. So this is, first of all, we got to know categorically, this is minus M. This group shows minus M. If this group shows minus M, what is going to happen? This pi bond, it will shift in this direction, and this pi bond will shift in this direction. What do we get at the end? What do we get? Try to understand. This is your C. Now the oxygen carries a negative. This is hydrogen attached with oxygen. There is a double bond here, right? And from this particular carbon, double bond got shifted. So this becomes positive. This is, rest everything is same. Now look here. Pi sigma positive, pi sigma positive, pi sigma vacant orbital. Resonance will happen, conjugation, right? This will shift here. And when it shifts here, what do I get? This is your CH, this is your O with negative, right? This is your double bond. And my dear students, look at this carefully. Look at this carefully. This is your double bond. And over here, you got the positive, right? Again, pi sigma positive. Pi sigma positive means this will shift here. And when it shifts here, what do I get? This is negative. This is your H. Check the other things. Check the other things. This double bond will remain as such. This will remain as such. And your positive got developed here. Right? Now, pi sigma positive. Pi sigma vacant orbital. Right? So, this will shift here. And this will shift here. What do I get at the end? This is CH. This is double bond O. This is single bond here now. It's a single bond here. Rest, everything is going to remain like this, right? Now guys, just try to understand one simple thing. When you attach this particular group towards a perfectly conjugated system, can I say charge separation got created? This is positive, negative, positive, negative, positive, negative. Charge separation got created between the conjugated system and the group. So I'll say this group is operating. It is showing mesomeric effect. Now, is this group increasing the electron density or decreasing? I will say this group is decreasing the electron density in the system. See, positive got developed, positive got developed, positive got developed, right? This group when attached to the conjugate system, it is decreasing the electron density through resonance in the conjugate system. Right? So I'll be saying this group is showing its electron withdrawal, it is showing minus M. It is showing minus M. Number one. Number two, where at what position the positive charge is getting generated? Ortho, para, ortho. Is the positive charge getting generated at meta? No. That is something which I already told you, right? Through mesomeric effect, positive as well as negative charges in the benzene ring, they are generated only at ortho and para positions. So in short, I'll again say plus M as well as minus M. It does not operate at meta positions. Right? Positive as well as negative through either plus M or minus M, they get only generated at ortho and para positions. Okay? Clear? Now guys, there are some things which you have to remember. What are plus M showing groups? What are plus M showing groups? Whenever you see a conjugate system, right? And if the group is attached to a conjugate system, if the first atom of the group carries a lone pair, this group will show plus M. If the first atom of the group carries a lone pair, it will show plus M. If the first atom of the group carries negative charge with a lone pair, it will show plus M. It will increase the electron density in the conjugate system. So do you remember this particular statement? Plus M showing groups. If the first atom of the group carries the lone pair, or the first atom of the group carries a negative charge with an unshared pair, right? It is going to show plus M. It is going to increase the electron density in the conjugate system through resonance. Perfect? Number one. Minus M showing groups. If the first atom of the group, if it contains vacant orbital, this vacant orbital can be either P or D. What will happen? See, this is basically your, if you look at it carefully, this is basically your sp2 hybridized carbon. So there is a p orbital, right? So what is resonance? Resonance is going to happen between them. Resonance is basically the partial overlap of these p orbitals, right? So partial overlap will happen. So resonance will happen basically. Perfect. And what is exactly going to happen? I'll say this will shift in this direction, this will shift in this direction, and so on. So if this atom, it carries a vacant orbital. Perfect. If it carries the vacant orbital. See, now it is not necessary that this atom should have positive charge. It can be without positive charge as well. Look at this BH2. Look at boron. Boron is forming how many bonds? 3 bonds. Boron's configuration is 2s2, 2p1. Right? This is 2s carrying 2 electrons. This is 2p carrying 1 electron. Now after excitation, what is going to happen? This is 1. And this is 1. Perfect. Now it is forming 3 bonds. So sp2 hybridized. This is sp2. There will be a pure p orbital here, which is vacant. Right? So this atom, it can have positive charge or it cannot have positive charge. Condition is there should be a vacant orbital present. Right? There should be a vacant orbital present. And that group will show minus M effect. Now people, if this is clear, I'm giving you certain groups. You have to identify which group will show plus M, which group will show minus M. I think you're sleeping. Are you sleeping? Quickly, let me know. Quickly. Don't sleep. You are not. I'm not letting you sleep. I'm not going to let you sleep. I need some fire emojis in the chats first. I need some fire. Guys, I don't know how my energy is getting increased slowly. Do you realize that? So your energy should increase drastically, right? It should increase drastically. First, I would want fire emojis from everyone. Let the chats be fast. Then only It will give me the idea of that you guys are in the session. Perfect. Go ahead. Tell me whether this group shows plus M or minus M when it is attached to the conjugated system like benzene. When it's attached to a conjugated system like this, will it show plus M or minus M? Have a look. It is negative with a lone pair, right? It will show resonance. So this will be plus M, right? This carries negative. This will be plus M, right? Carrying lone pair, right? If you attach this with this particular ring, what's going to happen? It will increase the electron density through resonance, plus M. What about this one? Again a lone pair. It will show plus M, right? OR. It will show plus M. Correct? It will show plus M. Now, what about this group? OH2 positive. OH2 positive. Will it show minus M? I told you if the first atom of the group, it can carry positive or cannot carry positive. Will it show plus M or minus M? Quickly. Quickly. People are saying minus M. Is that? I'll say it is neither going to show plus M nor minus M. I'll say it is neither going to show plus M nor minus M. Why is that? See, when you attach it with a conjugated system, this is your conjugated system, for example. There's a positive charge on oxygen, right? There's a positive charge on oxygen, no doubt. No doubt. But how many lone pairs oxygen has? 2. They say one lone pair will be there only with oxygen. There will be one lone pair with oxygen, right? Check the octet of oxygen. It's forming 3 bonds. 3 bonds means 6 electrons. 6 plus 2 is 8. Its octet is complete. There is no vacant orbital. The condition is the first atom of the group should have vacant orbital. There is no vacant orbital. There is no vacant p orbital here. So if it is not vacant, it's not going to show plus M. Sorry, it's not going to show minus M. Yeah? Look at this one. OR2. OR2 positive. There will be a lone pair here. One lone pair. Oxygen has 2, but 1 will be there. Due to the other one, there is positive. Again, 1, 2, 3. 3 bonds means 6 electrons. 6 plus 2, 8. No vacant orbital. Nitrogen. Octet complete. No vacant orbital. Nitrogen. Octet complete. No vacant orbital. SH. There are 2 lone pairs. There are 2 lone pairs, right? So it will give away lone pair, right? Or resonance. So plus M. Correct? Look at this one. Look at this one. Attach this with conjugate system, right? Attach this with conjugate system. What is going to happen? This will shift here. This will shift here. So it is pulling the electron density towards itself, right? Through resonance. So minus M. PR3 positive. Minus M or plus M? Quickly. Quickly, guys. Is it minus M or plus M? See, phosphorus carrying positive, right? See, no doubt it's forming 4 bonds. So the octet is complete. But phosphorus, it has got vacant d orbitals. There is a vacant d orbital. If there is a vacant orbital, that means minus M. Vacant orbital, minus M. Here, lone pair, plus M. Right? Vacant orbital, minus M. Clear? This is how you identify which group shows plus M and which group shows minus M. Right? This is how you identify which group shows plus M, which group shows minus M. I hope this is clear to everyone. Right? All right. Identify the group showing plus M, minus M. Identify the group showing plus M and minus M. Quickly. Identify the group showing plus M and minus M. Quickly. See, if it is attached to a conjugated system, what will it do? What will it do? This is basically X double bond or triple bond Y. X double bond or triple bond Y. And Y is more electronegative than X. So this minus M, if you remember. If you remember. If you remember. Right? If you remember. This oxygen, it carries a lone pair. It carries a lone pair. If it is attached to a conjugated system. If it is attached to a conjugated system, it can donate this lone pair through resonance. Right? So this will show plus M. Right? This nitrogen carries a lone pair. It will donate this lone pair. It will also show plus M. Correct? This. What about this one? If you're attaching this with a perfectly conjugated system, what is going to happen? What is going to happen? This is X double bond Y. Y is more electronegative than X. This will show minus M. Even this will show minus M. Same reason, right? This will show minus M. Same reason, right? Now you tell me. BH2, what is it going to show? What is it going to show? Boron. Octet is not complete. It's forming 3 bonds. So 6 electrons. So it will be having a vacant p orbital. It will show minus M. This carbon, it will show minus M. Case 2 group, right? Because there's a vacant p orbital. Perfect. Now people, fluorine, chlorine, bromine, iodine. What do they show? Since they have got lone pairs. All the halogens, they have got 3 lone pairs, right? They have got 3 lone pairs. So they can give away, they can contribute these lone pairs, right? Through resonance. So they'll show plus M. They'll show plus M. They'll show plus M. But particularly, my dear students, when you talk about halogens, halogens, they, as per mesomeric effect, they should show plus M. But at the same time, they show minus inductive effect as well. Particularly in case of halogens. If halogens show plus M, they are going to be electron donating. Due to minus side, they are electron withdrawing. But let me tell you, halogens, they are net electron withdrawing. Halogens show both plus M as well as minus side. But inductive effect dominates over mesomeric effect only in case of halogens. Inductive effect dominates over mesomeric effect. Inductive effect dominates over mesomeric effect in case of particularly halogens. So halogens will be net electron withdrawing. I'm particularly talking about halogens. I'm particularly talking about halogens, right? I'm particularly talking about halogens. Okay. Now, few points to remember, then we'll start the questions. What are the points? Have a look. Plus M power of anionic group. This is the anionic group is greater than that of plus M power of neutral group. Something which we discussed in inductive effect as well. Right? Plus I power of anionic groups used to be greater than that of plus I power of neutral groups. Similarly here also. Plus M power of anionic groups will be greater than that of plus M power of neutral groups. Number 1. Minus M power of cationic groups. Minus M power of cationic groups will be greater than that of minus M power of neutral groups. Right? Will be greater than that of minus M power of neutral groups. Perfect. Mesomeric effect is directly proportional to extent of overlap. What does it mean? Have a look. I've taken 2 examples. So, imagine this is your conjugated system and you're attaching OH with it, right? Similarly, you have got one more conjugated system and you are attaching SH with it. Sulfur also has 2 lone pairs. Oxygen also has 2 lone pairs. Now, since this is going to show resonance, even this lone pair is going to participate in resonance, due to which this will also show plus M and this will also show plus M. Now, since the group and the system is showing resonance, what is resonance? Overlap, partial overlap of orbitals. Partial overlap of parallel orbitals which are coplanar, right? Since this contains p orbital, this contains p orbital. So there will be this carbon. It will be having 2p, this will be having 2p. So the overlap here is going to be 2p, 2p. And the overlap here is going to be 2p, 3p. Right? Now, extent of overlap, effective overlap will be here, 2p, 2p. If more effective the overlap, more is the extent of resonance. More the extent of resonance, more will the plus M power. So do remember, plus M power of OH will be greater than that of plus M power of SH. Simple. Plus M power of OH will be greater than that of plus M power of SH. Because here it's going to be 2p, 2p overlap. Here it's going to be 2p, 3p overlap. Right? Got it? Got it, guys? All right. Arrange the following as per their mesomeric power. Arrange the following. I think these sort of questions you can do on your own. Arrange the following as per their mesomeric power. For example, OH and OR. This will show plus M, this will show plus M. Now, which one shows more plus M? Which one shows more plus M? Which one shows more plus M? How you are going to remember them? How you are going to remember it? See, bond is between O and H. Here the bond is between O and C carbon. Electronegativity difference here is more. If electronegativity difference here is more, that means oxygen will be getting more delta negative. Here oxygen will be getting less delta negative. More delta negative means more plus M. So this will show more plus M. Correct? This is how you are going to remember it. Look here, nitrogen, hydrogen. Here nitrogen, hydrogen as well as carbon. Right? So negative charge will be maximum in the first case. Right? More negative charge, more plus M. Perfect. Now my plus M power of anionic groups, that is greater than plus M power of neutral groups. So 1 and 2 will have more plus M than 3 and 4. Now among 1 and 2, which will have more plus M? See, this is oxygen, more electronegative. It will hold its electron pairs towards itself. So availability of this is less. So extent of resonance is less. Here comparatively extent of resonance will be more. So 2 more plus M followed by 1. Now among these two, it will be 3, then 2. I hope this is clear. Right? Now at the same time, fluorine if attached to a conjugate system, see, fluorine has got the lone pair. So this group, this fluorine and the conjugate system, they are going to show resonance. What is the resonance? Partial overlap of parallel orbitals which are coplanar basically. Right? So here the overlap has to be due to resonance. What is the resonance? Overlap, right? Here the overlap will be, this is P, this is P. Now this is 2P, this is 2P. The overlap here is 2P, 2P. Here the overlap will be 2P, 3P. Here the overlap will be 2P, 4P. Here the overlap will be 2P, 5P. More the extent of overlap, more the plus M power. So this is the plus M power of these halogens as well. Right? This is the plus M power of these halogens as well. Right? I believe this is clear. Now guys, this is your plus M series which needs to be remembered at any cost. This is your plus M series which needs to be remembered. NH2, its plus M power is maximum. Then O negative, NH2, NHR. You have to remember this particular series. Similarly, minus M series also you have to remember, then only we can do questions. Minus M series also we have to remember, then only we can do the questions. This is your minus M series. So it is my request to remember plus M series, minus M series as well. Right? And once you remember these two series, you can easily solve the questions. But before solving the questions, there are a few more points which I would want to share with you. Then we'll go ahead with the questions. I told you halogens, they are electron donating as per plus M, withdrawing as per minus I. But for halogens, inductive effect dominates over mesomeric effect. That is the reason why halogens are net electron withdrawing. So for halogens, minus I dominates over plus M. Right? Okay. Now, when halogen is conjugated with reference, net electron withdrawing nature of Cl is more than that of F. This is the scenario which I want to show you. Fluorine is attached to the conjugate system. Chlorine is also attached to the conjugate system. So fluorine, its lone pair, it will donate its lone pair, it will show plus M, as well as fluorine shows minus I. Right? This will show plus M as well as minus I. If you talk about the plus M, for the plus M to happen, it's going to be 2P, 2P overlap. Here it's going to be 2P, 3P overlap. Right? Perfect. So I would say plus M power of fluorine should be more. Plus M power of chlorine should be comparatively less. Minus I power of halogen of fluorine is more. Minus I power of chlorine is less. You know it. Right? Okay? Plus M power of fluorine is more than the plus M power of chlorine. Because here it's 2P, 2P overlap. Here it's 2P, 3P overlap. If I talk about inductive effect, minus I power of fluorine is more. Minus I power of chlorine is comparatively less. But we know halogens, what are they? They are net electron withdrawing. If you compare the magnitude of both these effects, eventually you'll get to know fluorine is electron withdrawing. This is also electron withdrawing. And do remember, in this particular case, electron withdrawing nature of chlorine will be more than that of electron withdrawing nature of fluorine. It will be more than that of electron withdrawing nature of fluorine. Remember this particular point. Remember this particular point, right? This shows plus m minus I, plus m minus I, plus m is more, plus m is less. Minus I is more, minus I is comparatively less. But do remember, both of them, they are net electron withdrawing, and net electron withdrawing nature of chlorine here will be more than that of fluorine. I hope this is clear. I hope this is clear. And guys, one simple thing, and we'll start the questions. One simple thing, and we'll start the questions. Mesomeric effect, it always dominates over inductive effect, except in case of halogens. For example, you have got a group. The group has got the tendency to show mesomeric effect as well as inductive effect, as well as hyperconjugation. I shall leave hyperconjugation. For example, you have got a group, it has got the tendency to show mesomeric effect as well as inductive effect. Remember, mesomeric effect always dominates over inductive effect. Always dominates over inductive effect. Mesomeric effect always dominates over inductive effect, except in case of halogens. Except in case of halogens. For example, you have got a group X, right? Let's say it can show plus M. It can show plus I as well, right? You'll be considering it's plus M. This will be given the priority. This will be given the priority. Perfect. Let's say you've got a group. It can show minus M. It can show minus I as well. But you'll be prioritizing mesomeric effect. So mesomeric effect dominates over inductive effect. Except in case of halogens. In halogens, inductive dominates over mesomeric. And already one thing which you must be knowing. Mesomeric effect does not operate at meta position. It does not operate at meta position. Okay. Now people, we have got a lot of questions. And in order to solve the questions, let me tell you certain tricks. First of all, if you talk about the stability of the carbocation, carbocations are stabilized by electron donating group, destabilized by electron withdrawing groups, right? All the plus showing groups, they are donating, all the minus groups, they are withdrawing, correct? So people, if you want to arrange, whenever you'll be given certain carbocations and you have to arrange them on the basis of their stability, you know, mesomeric effect dominates over everyone. First, you'll prioritize plus M showing group. Plus M showing group is going to stabilize the carbocation in the maximum. Then plus H. Then plus I, right? After plus I, it's going to be minus I. After minus I, it's going to be minus H. After minus H, it's going to be minus M. Since H we have not discussed yet, you just note it down. That's it. This is going to be the order which you'll be following. Plus M showing group, it's going to stabilize the carbocation in the maximum, right? Then you'll be prioritizing plus M, right? Plus H. After plus H, you'll be prioritizing plus I, right? Similarly, whenever you'll be asked a question in which you have to give the stability order of the carbenions. Carbenions are stabilized by electron withdrawing groups and destabilized by electron donating groups. Electron withdrawing, minus. And we know minus M will dominate over minus H. Minus H will dominate over minus I. After minus I, it's going to be plus I. After plus I, it's going to be plus H. And then at the end, it's going to be plus M. This is the sequence which you have to follow. That's all. Sequence which you have to follow, right? Similarly, third, strength of acid. Strength of acid is directly proportional to Ka, which is inversely proportional to P of Ka, right? Which is directly proportional to stability of the conjugate base. Stability of the conjugate base of the acid, right? And conjugate bases are stabilized by electron withdrawing. So, directly proportional to electron withdrawing, inversely proportional to electron donating groups. And in electron withdrawing, which one to prioritize? Minus M to prioritize the maximum, then minus H, then minus I, then plus I, then plus H, then at the end plus M, right? This is the order which you'll be following. Similarly, strength of a base. Strength of the base is directly proportional to Kb, which is inversely proportional to P of Kb, right? Perfect. And strength of base. Electron donating groups increase the strength of the base. Electron withdrawing groups, they decrease the strength of the base, right? And here, plus M dominates over plus H. Plus H dominates over plus I. plus I dominates over minus I, then you have got minus H, then at the end you have got minus M. So my dear students, this is the sequence which you have to follow, and different types of questions can be asked different types of question can be solved if you remember these particular sequence. If you remember these particular sequences, right? And I hope you guys are going to remember them from now onwards. This is the final order which you have to remember, and you can easily solve the question. Easily you can solve the questions. Have a look. Understand one thing. If you properly have a idea of certain things, this series and this series, it is same. This order and this order is same, right? Similarly, first and the fourth order is also same, right? First and the fourth is also same. First and the fourth is also same. Now let's try to solve the questions. Let me see if you can solve these questions or not. See guys, arrange the following according to their stability order. These are your carbocations, right? Carbocations are stabilized by electron donating groups, and you know, plus M dominates over plus H dominates over plus I dominates over minus I dominates over minus H dominates over minus M. This is the order which you have to understand. First of all, understand, this is carbon carrying positive, carbon carrying positive, carbon carrying positive. You have checked your site. This is your site, common site everywhere. Now this is OH here. OH at para. Oxygen has got the lone pair, right? It's going to donate this lone pair in the form of resonance. So it is going to show plus M, right? OH at meta. At meta, you are not going to operate mesomeric. What you'll operate here? This oxygen, more electronegative. You'll operate, it's minus I, right? You'll operate minus I from here. Nitro at para. Nitro at para. Nitro at para. It's going to show minus N. Nitro is minus M showing group, right? Nitro at meta. Minus I. SH. Sulfur has got the lone pair. It can donate. So plus M at para. Okay. Your carbocations are stabilized by plus M showing groups. Which one is plus M? This is plus M. This is plus M. Now which one shows more plus M? OH shows more plus M. OH shows more plus M. So first one is maximum stable, followed by fifth. So plus M we have prioritized. Now is it anyone plus H? We have not discussed plus H yet. Leave it aside. Now plus I. Which one is plus I? Nobody is plus I. Leave plus I also. Now minus I. Minus I. This is minus I. This is minus I. Right? This is minus I. Even this is minus I. Minus I means electron withdrawing. Electron withdrawing groups, they destabilize the carbocation. Right? Which one among the two is more withdrawing? This is showing more minus I. This shows more minus I. More withdrawing. This is going to destabilize more as that of this. Right? So I'll say 2 will be more stable than 4. And at the end, you'll be prioritizing this 3. So is this the order? What people have written 1, 5, 2, 4, 3. 1, 5, 2, 4, 3. Absolutely correct. Wonderful. Wonderful. Yes? Perfectly done? Okay, this was our first question. Look at the second question. Look at the second question. These are the carbanions, carbon carrying negative. These are the carbanions everywhere. These are the carbanions, people. These are the carbanions. And carbanions are stabilized by electron withdrawing. Priority order, minus M, minus H, minus I, plus H, plus M. This is the priority order. Now understand, this NH2, nitrogen carrying lone pair, it will show resonance, right? It will go in this way. So it's plus M, right? At meta position, nitrogen is more electronegative than carbon, so minus I. So at para, will give away. So it is going to show plus M. This PR3, vacant d orbital. Phosphorus has vacant d orbital. It will show minus M, right? Now, which one is showing minus M? There is only one showing minus M. That has to be prioritized, which is going to be more stable. So 4 is more stable. Followed by minus M is gone. Now minus H, leave it aside. Minus I. Anyone showing minus I? Yes. Second is showing minus I. After second, after minus I, is there anyone showing plus I? No. Now there are 2 plus M showing. This is plus M showing. This is plus M showing. Now which one has got more plus M? Which one shows more plus m power? Nitrogen carrying lone pair, oxygen carrying lone pair. Now tell me, nitrogen, less electronegative. This lone pair is more available for resonance. So it will show more plus m, right? It will show more plus m. This is more plus m, this is less plus m, right? More plus m means more electron donating, which will destabilize it maximum. So 1 at the end. Before 1, it's going to be 3. So this is going to be the order. Stability order. Agreed? People are saying 4, 2, 3, 1. 4, 2, 3, 1. Yes, 4, 2, 3. Correct? Correct, guys? Perfect. Moving ahead. Look at this particular question. Arrange the following as per the Ka order. That means acidic strength order. Acidic strength order. How do you compare the acidic strength? What is the order? Acidic strength is directly proportional to stability of conjugate base. Right? Acidic strength is directly proportional to stability of conjugate base. Conjugate base is stabilized by electron withdrawing. Minus M dominates over minus H dominates over minus I, then comes your plus I, then comes your plus H, then comes your plus M. Now have a look. This is OH everywhere. You saw your reference. This is NO2. From para, it will operate minus M. CN, from para, it will operate minus M. Right? For these two, inductive effect dominates. So I'll consider it's minus I, it's minus I. Even though it shows plus M as well, Due to which, both of them are electron withdrawing, but chlorine comparatively is more electron withdrawing than fluorine, right? That's something which we have discussed already. Now, first of all, you have to prioritize minus M. This is minus M, this is minus M. Which one shows more minus M? Nitro shows more minus M, right? So 1 is maximum, followed by 2. Now, here this is withdrawing, this is more withdrawing. So 4, then 3. This is the order. Yeah? Is it clear? You should be able to solve these sort of questions now. All right, look at this particular question. Let me see if you can solve this one or not. Again, you have to arrange them on the basis of acidic strength. Again, you have to arrange them on the basis of their acidic strengths. Okay, acidic strengths. Acidic strengths. Quickly, what do you think about this particular question? What do you think about this particular question? What do you think about this particular question? Guys, it's again very simple. This is OH. Everywhere the reference is same. Now you have to arrange them on the basis of Ka order. Step Ka, acidic strength. Acidic strength is directly proportional to stability of conjugate base. Conjugate base is stabilized by electron withdrawing. In electron withdrawing, minus M dominates over minus H. Then you have got minus I. Then you have got plus I. You have got plus H. You have got plus M. This is the order which you'll be following. Right? Now people tell me whether this particular group, is it going to show minus M or plus M? This is N positive, forming 4 bonds. There is no vacant orbital. It is not going to operate minus M from here. It's not going to show minus M, by the way. Okay, if you remember. It does not have the vacant orbital. Okay, so it will directly show minus I. Right? It will directly show minus I. Perfect. What about this one? There is a vacant d orbital. It will show minus M. It will show minus M. This will show minus I. This will also show minus I because they are present at the meta positions. Now, tell me the order. Tell me the order, people. Tell me the order. Which one is showing minus M? There is only one showing minus M. That's 2. Followed by minus H. Leave minus H aside. We have not discussed that yet. Then minus I. Minus I. Minus I. See, guys, if this is carbon number 1, this is 2, this is 3, this is 4. So minus I is operating from 4th carbon. But we know inductive effect we do not consider up to 3 carbon atoms. So you do not consider its inductive effect. Don't consider its inductive effect. Now look at these two. Look at these two. Nitrogen carrying positive, phosphorus carrying positive. Nitrogen, phosphorus. NMe3 positive, PMe3 positive. Which one shows more minus I? Nitrogen, phosphorus. They belong to the same group. In the group, VCD plays a role. So here, volume charge density, positive volume charge density will be more. Positive volume charge density means more electronegative, more minus I. So this will show more minus I. So after 2, it's going to be 3. After 3, it's going to be 4. And at the end, it's going to be 1. Did anyone give this particular order? 2, 3, 4, 1? Wonderful. 2, 3, 4, 1. Yes, it's the correct order. Okay. I hope this sort of a question you can also solve from now onwards. All right. What do you think about these two? Arrange the following according to their Ka order. I mean, which one among the two is more acidic? HCOH or PHCOH? HCOH or PHCOH? HCOH or PHCOH? Quickly. What do you think? HCOH or PHCOH? See guys, if you talk about this PHCOH, PH means this is a phenyl ring, right? This is your C, double bond O, and this is OH, right? Look at this particular one. This is X double bond Y. Y is electronegative than X, right? Perfect. Y is, so this will operate minus M. What does that mean? That means this operating plus M. So this pH is operating plus M from here. And here there's hydrogen, nothing. More acidic, more acidic. This is operating plus M. Acidic strength is directly proportional to stability of conjugate base. Conjugate bases are stabilized by electron withdrawing, right? Electron withdrawing. This electron donating, less acidic. So first one will be more acidic. First one will be more acidic, right? First one will be more acidic. Now guys, here you can do a mistake. Here you can do a mistake. I want you to do that mistake. What should be the answer of this? What should be the answer of this? Quickly. What should be the answer of this question? What should be the answer of this particular question? See, first of all, if you look at these particular carbons, which carry the negative charge, if you look at these particular carbons which carry the negative charge, be careful with this question, guys. Be careful with this question. See, first of all, if you look at this particular carbon, first of all, just let me make you understand it like this. Just a second, Now it's fine. Perfect. Now, if you look at this particular carbon, carbon's configuration is 2s2, 2p2. So this is 2s and this is 2p. 2s and 2p, correct? This carbon, it has already formed a pi bond. So one of the p orbital has already participated in the parallel overlapping. So this p and this p, this p and this p, they have overlapped. Now the hybridization is sp2, right? So how many hybrid orbitals do we get? 3 hybrid orbitals. One hybrid orbital has formed a bond here. One hybrid orbital has formed a bond here. And one hybrid orbital that will be containing this negative charge. One hybrid orbital will be containing this negative charge, right? And all these 3 hybrid orbitals, this one, and this one, they'll be present on the same plane because it's sp2. sp2 means trigonal planar. sp2 trigonal planar. So this hybrid orbital, this one, and this one, they are present on the board. And there is one p which is already participating in the overlapping, right? So this nitro at para, we know it shows minus M, but this minus M. Tell me one thing, whether I'll be considering minus M of nitro here or minus I of nitro. What do you think? Whether I'll be considering minus M of nitro or minus I of nitro. See guys, if this negative charge was in p orbital, then only this negative charge would have spread through resonance, right? Then only this negative charge would have spread through resonance. Then only stability would have increased. But this negative charge, it is out of plane of resonance. It is not in the plane of resonance. This negative charge, it is not in the plane of resonance. It is not in the plane of resonance, right? It is not in the plane of resonance. If it was in the plane of resonance, if it was present in the pure p orbital, then I would have taken minus m. Then minus m would have stabilized it. Then minus m would have stabilized. Okay, but this negative, it is not in the plane of resonance here, right? So you'll be taking, since we are talking about the stability of carbanions, you'll be considering its minus I here, right? Even though this is carbon number 1, 2, 3, and 4, it is operating from at 4th carbon, right? And inductive effect dies after 3rd. Okay, here it is meta, so minus I. Here it's again minus I. You are not going to consider it. Perfect. And here CH3, it's going to be plus I. I believe you can easily give the order here. I believe you can easily give the order here. My point is, this negative charge here is present in sp2 hybrid orbital. It is present in sp2 hybrid orbital. It is not present in the plane of resonance, right? It is not present in the plane of resonance. If it is not present in the plane of resonance, then if it is not present in the plane of resonance, then there'll be no overlap. No overlap means no spreading of this negative charge. No spreading of negative charge means no increase in stability through resonance, right? I hope this sort of a question you can easily solve. Okay, tell me about this one. Tell me about this one. Again, guys, this is positive, this is positive, this is positive, right? Positive, positive, positive. So again, the positive charge is present on the benzene ring, basically. Positive charge is present on the benzene ring. In the earlier case, negative charge was present on the benzene ring. Whenever you see such kind of scenarios, positive charge present on benzene ring or negative charge present on benzene ring, mesomeric effect does not stabilize them. Mesomeric effect does not stabilize them. Because those positive and negative charges, they are out of the plane of resonance. They're out of the plane of resonance. So which effect you'll be operating here? Inductive effect only. Right? Inductive effect only. Perfect. I hope you can easily solve this one as well. Only inductive effect you will operate. Only inductive effect you will operate. Okay. One last question on mesomeric effect. Okay. Last but one, this is last but one. Last but one. Arrange the following as per the KB order. KB means basic strength. First of all, this is the site. This is the basic site here, which is common everywhere. This is the basic site here, which is common everywhere. Now see, NH2, it will operate plus N. OH, it will also operate plus M. This CH3, it will operate plus I. This will operate minus M. And when you talk about the basic strength, your plus M groups, they increase the basic strength to the maximum, followed by plus H, followed by plus I. After plus I, it is minus I. After minus I, it is minus H. After minus H, it is minus M. Okay? Now, which one is showing plus M? This is showing plus M, this is showing plus M. Right? Plus M of NH2 is more. So one is more basic than second. Right? Then plus I. So 1, 2, 3, 4 is the order. 1, 2, 3, 4 is the order. 1, 2, 3, 4 is the order. Anyways, this is something which you call as gonadine, right? Which is maximum basic. This is maximum basic already. This is something which you should know. Gonadine, maximum basic. Correct? Correct, guys? Now there is one question. There is one question. Have you seen this particular sort of question before? Just tell me that. Arrange the following according to the bond angle around nitrogen. Bond angle around nitrogen. Have you seen this sort of a question before? Just tell me that. Just tell me that once. See guys, what this question is all about and how do we solve this? Arrange the following according to what? According to the bond angle around nitrogen. Around nitrogen. See, this is CHO here, right? This is your CHO here. This is CHO. CHO means this is C double bond O and this is H. Correct? First of all, if I talk about this particular nitrogen, if I talk about this particular nitrogen and this particular nitrogen, both these nitrogens, they have got lone pairs, right? Are these lone pairs conjugated? Yes, these lone pairs are conjugated. Yes, these lone pairs are conjugated, right? Yes, these lone pairs are conjugated. Are these localized or delocalized lone pairs? These are delocalized lone pairs because this is pi sigma lone pair. Delocalized lone pairs these are. If they are delocalized, should I consider them while calculating the hybridization of nitrogen? I'm not going to consider them, right? I'm not going to consider them because delocalized. Here also it is delocalized. My dear students, imagine if this was localized lone pair. Then the steric number of nitrogen would have been 3 bonds, 1 lone pair, 3 plus 1, 4. Its hybridization should have been sp3 at that time. If this was localized. If this was localized, its hybridization should have been sp3, right? Due to delocalization, if the lone pair is now delocalized, so 3 sigma bonds, its hybridization is coming out to be sp2, right? Due to delocalization, its hybridization is coming out to be sp2. Bond angle here was 109 degree 28 minutes. Here the bond angle should have been 120 degree, right? Here it should have been 109 degree 28 minutes. Here in case of sp2, it is 120 degree. Perfect. If the lone pair was localized, hybridization of this nitrogen should have been sp3. But due to resonance, it is sp2. Due to resonance, it is sp2. And due to resonance, you are getting the partial double bond character as well. Due to resonance, you are getting the partial double bond character as well. So tell me, due to resonance, is the bond angle increasing or decreasing? Due to resonance. If there was no resonance, if this lone pair was localized, hybridization should have been sp3. But since it's participating in delocalization, it's participating in resonance, so its hybridization is changing from sp3 to sp2. So bond angle is increasing. So due to resonance, bond angle is increasing. Due to resonance, bond angle here also is increasing. Bond angle here is also increasing. And due to resonance, this gets double bond character, even this gets double bond character. If I ask you where is the extent of resonance more, can I say extent of resonance is more in this case? Extent of resonance is more in this case. So more the extent of resonance, more the bond order. I mean, more the bond order, more the double bond character. More the extent of resonance, more the double bond character here. Can I say something like that? Can I say something like that? See guys, try to understand one simple thing which I'm trying to convey. Due to resonance, bond angle is increasing. Bond angle is increasing. So where is the extent of resonance more? Extent of resonance is more in the second case. More the extent of resonance, more the increase in bond angle. So where is the bond angle more? Bond angle around nitrogen is more in second than first. Simple. Tell me you got this question. Due to resonance, bond angle is increasing, right? Now, wherever extent of resonance is more, increase in bond angle will be more, as simple as that. Yeah? Got it? Perfect. Now, guys, there's a topic called as aromaticity. Aromaticity. Tell me, first of all, if mesomeric effect is clear to everyone. See, this is a simple topic. This is not difficult or something. Tell me if mesomeric effect is clear to everyone. Tell me if mesomeric effect is clear to everyone. Tell me if mesomeric effect is clear to everyone. Guys, you will have to revise this lecture tomorrow, by the way. You will have to revise this lecture. Otherwise, it will be all over. Otherwise, it will be all over. And you have to remember all the things, whatever I have told you in the session. You will have to revise this particular lecture again tomorrow. Otherwise, it's going to be really difficult to remember this. All right, let's talk about something called as aromaticity. See, very simple and basic thing. I'm not going into the details. I'll just tell you that amount of theory required, which is used to solve the problems. Okay? Now, people, try to understand what exactly I'm going to say. Let me tell you, in organic chemistry, there were some organic compounds which were experimentally found out to be extra stable. In organic chemistry, let me write it over here. In organic chemistry, experimentally, some of the compounds were found out to be extra stable. Than expected. In organic chemistry, there are some compounds which were experimentally found out to be extra stable than expected. And those compounds which were experimentally found out to be extra stable than expected, those compounds were given a name as aromatic compounds. Similarly, one more set of compounds was found experimentally, which was found out to be highly unstable than expected. And those compounds were termed as anti-aromatic. And there were few compounds in the organic chemistry which were found out to be, whose stability was found out to be between these two. Those were called as non-aromatic compounds. So let me repeat it. In organic chemistry, a particular set of compounds were found experimentally which were having stability extra than expected. Those compounds were given the names aromatic compounds. Some more compounds were there which were found out to be highly unstable. Those were given the name as anti-aromatic. Some compounds were seen experimentally whose stability was between aromatic and anti-aromatic. Those were called as non-aromatic. Now guys, first of all, if I ask you what is the stability order of these? What is the stability order of these particular compounds? You will say aromatic compounds will be maximum stable, followed by non-aromatic, followed by anti-aromatic. This is something which has been observed experimentally, right? Okay. Now guys, the point is, what is the point here? The point is, in aromatic compounds and anti-aromatic compounds, there were some things which were common. In aromatic compounds, there were some common features which were seen. Similarly, in anti-aromatic compounds, some common features were present. What were those common features? In aromatic compounds, they were found out to be cyclic. They were found out to be planar. There was complete cyclic conjugation present. And there were 4n plus 2 pi electrons were involved in the cyclic conjugation. That means these compounds were following the Huckel's rule. These were the few things which were common in these aromatic compounds. See, a particular set of compounds were found out to be experimentally in organic chemistry, which were found out to be extra stable than expected. Those were called as aromatic compounds. In aromatic compounds, few things were common. They were cyclic, they were planar. Complete cyclic conjugation was there. 4n plus 2 pi electrons were involved in the complete cyclic conjugation, right? 4n plus 2 pi means if n is 0, that means either 2 pi electrons were involved. If n is 1, 4 plus 2, 6 pi electrons were involved. Or n is 2, 10 pi electrons were involved. N is 3, 14 pi electrons were involved in the complete cyclic conjugation. Now, in anti-aromatic compounds, again, there were some common features. They were again cyclic. They were planar also. It was observed that there is complete cyclic conjugation. But there were 4n pi electrons involved in the complete cyclic conjugation, right? If n is 1, that means either 4 pi electrons were involved in the complete cyclic conjugation, or 8 pi electrons, or 12 pi electrons, or 16 pi electrons, etc., etc. Non-aromatic, see, they are planar. These are also planar. These were non-planar. If the molecule is neither aromatic nor anti-aromatic, then what is it? It is non-aromatic. Now see how I'm going to utilize this particular concept. Try to understand, guys. Rest, no need to remember anything. Look at this particular molecule. All the carbon atoms are sp2. They are sp2 hybridized. Absolutely. It's a benzene ring, sp2 hybridized. Right? sp2 means trigonal planar. So first of all, the molecule is cyclic. The molecule is planar as well because every carbon is sp2. Right? Now, is there complete cyclic conjugation? Pi, sigma, pi, sigma, pi, sigma. Complete cyclic conjugation. How many pi electrons are participating in complete cyclic conjugation? 2, 4, 6. 6 pi electrons. That means this comes under the category of, this is your aromatic. Right? This is your aromatic. Because 6 pi electrons involved in the cyclic conjugation means aromatic. Perfect. This is your aromatic. Look at the second one. See, this is sp2, this is sp2, this is sp2. That means planar. sp2 means planar. Cyclic as well. See, pi sigma positive, complete cyclic conjugation. Only 2 pi electrons are involved in the complete cyclic conjugation. 4n plus 2 pi. That means this is aromatic. 2 pi electrons means aromatic. Following the Huckel's rule. Right? Look at this one. Cyclic. Right? All the carbon atoms sp2. Cyclic, planar, 2, 4. 4 pi electrons involved in the complete cyclic conjugation. If 4 pi electrons are there, that means it's supposed to be anti-aromatic. Right? This is anti-aromatic. Simple. Look at this one. Simple. Look at this particular carbon. There will be one hydrogen here, one hydrogen here. So 1, 2, 3, 4. 4 sigma, so this is sp3. Planar or non-planar? sp3 means non-planar. Non-planar means non-aromatic. Right? Because aromatic as well as anti-aromatic, they are planar. If it is non-planar, it's non-aromatic. Look at this one. This particular carbon. It is sp3 hybridized. So non-planar means non-aromatic. Simple. Non-planar means non-aromatic. Where did this slide go? Why is not showing anything? Guys, just a second. We need to give some rest to the screen. I think something is wrong here. Stopped working. Yeah. Finally. Now it's fine. Just a second. Okay. All right, guys. First of all, tell me, is this lone pair in conjugation? This lone pair is not in conjugation. Is it conjugation? It's not in conjugation, right? If it is not in conjugation, you have to consider this also for hybridization. So 1 sigma, 2 sigma lone pair, 2 sigma and 1 lone pair. This is sp2 hybridized. sp2 hybridized nitrogen, right? sp2. This lone pair is not involved in the conjugation. Okay. Now, all the other atoms are also sp2, so planar. How many pi electrons? 2, 4, 6. 6 pi electrons are involved in the complete cyclic conjugation, so aromatic. Right? Look at this one. Among these two lone pairs, only one lone pair is conjugated. Pi sigma lone pair, pi sigma lone pair. Only one lone pair is conjugated. So leave that aside. And the other one count for hybridization. 1 sigma, 2 sigma, 1 lone pair. 2 sigma, 1 lone pair. Steric number 3. So this sp2. So this is planar. All the other carbon atoms are already sp2 planar. Right? Planar cyclic 2, 4 and 6. 6 pi electrons are involved in the complete cyclic conjugation. So this is aromatic again. Right? Exocyclic bonds you are not going to consider. Exocyclic bonds you are not going to consider. Now, this is cyclic. Every carbon is sp2 and there are 2 pi electrons involved in the complete cyclic conjugation. So this is also aromatic. This is also aromatic, right? This is also aromatic. I believe it's clear. I believe it's clear. My dear students, for aromaticity, what is happening? Screen is not responding properly. Just give me a second. Not showing the slides. Just wait, guys. Just wait. It will respond. It will respond. What do I do with the screen? Let's wait for 1 minute. Okay. Let's wait for 1 minute. Let's give it some rest. I don't know. Let's wait for 1 minute. What's up? How are you all? Screen wants break, yeah? Screen wants break. Okay, I'll go a little slow. So what's up? What's happening? Are you all alive? Are you all alive? Are you all alive? Someone is saying my brain is not braining anymore. Good. Nice. Brain should not brain anymore. I'll do one thing. I'll save this part of the slide. Save these part of slides and then we'll upload it again. I think the screen is stuck. Screen is stuck, I think. Something is wrong. Something is wrong. Oh, this happened in HSP sir's class also. And what he did exactly? Not doing anything. Stuck. Okay, I'll also leave it for some time. Let's leave it for some time. So guys, how is the preparation going? Tell me. How is the preparation going? Till then, let's chit chat. How is the preparation going? All well? On the scale of 10? On the scale of 10? On the scale of 10? Are you sure? 7, 8? That's great. That's nice. Nice. Great, guys. That's amazing. Good. So are you following all the marathons? All the marathons? Zifan, where are you studying exactly? Which offline you're studying? That's amazing, guys. Follow biology as well. Why you're not following biology? Guys, follow biology as well. That's again important. That's great, Srinath. That's great, Saucy. Following from day 3. Dharma will decide that. We have not decided who is going to take this isomerism. Guys, the screen is stuck, by the way. Neelam, you have Ambika ma'am teaching you, right? Ambika ma'am, consider I rate her at the top when it comes to content. Nobody can beat Ambika ma'am in the content. Trust me on that. Nobody. Nobody. Mhm. I think I'll have to restart the screen, but I don't know whether I would be able to give you the handwritten slides then. Wait, I'll just restart the screen once. I don't know what will happen. It's not shutting down also. Wait, 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 wait. Guys, I'm not sure about the slides now. Okay? I'm not sure about the slides now. I don't know whether the slides will be saved or not. Please don't blame me. Don't blame. I'm really sorry. The slides are gone. If anyone among you like have taken down the notes, please take the photos of that and put on the Telegram. Okay, so that everybody can have it. Uh, 2 more minutes, guys. 2 more minutes. And yes, you'll be getting the handwritten slides. There is something wrong. Wait, yeah. Let's wait. Let's wait, guys. Let's wait. Something happened. Did you? All right. Yes, we are back. Still, it's okay. I'll give you the slides, okay? So am I again audible, visible to you? Am I again audible, visible to you? Chalo, perfect, guys. Let's continue. Let's continue, guys. Let's continue. So basically, for the molecule to be aromatic, it has to be cyclic, it has to be planar, there should be complete cyclic conjugation, and there should be 4n plus 2 pi electrons involved in the complete cyclic conjugation. That means either it can be 2 pi or it can be 6 pi, right? Or it can be 10 pi, etc., etc. Now, guys, try to understand. First of all, if I ask you whether this lone pair is conjugated, whether it's localized or delocalized, whether this lone pair is localized or delocalized. Look at this particular nitrogen, right? There is a double bond here. There is a double bond here. Is it localized or delocalized? Tell me that. It is localized lone. It is not going to participate in the resonance. If it is not participating in the resonance, we have to count this lone pair for hybridization. So 1 sigma, 2 sigma, and 1 lone pair. So 2 sigma and 1 lone pair. 2 plus 1 is 3. That means this is sp2. sp2 means planar. All the other carbon atoms, they are already sp2. So this molecule overall is planar. Point number 1. The molecule is planar. This is cyclic as well. Is there complete cyclic conjugation? See, pi, sigma, pi, sigma, pi, sigma. There is complete cyclic conjugation. How many electrons, how many pi electrons are participating in the complete cyclic conjugation? 2, 4, 6. 6 pi electrons. If 6 pi electrons are participating in the complete cyclic conjugation, tell me, is it following Huckel's rule? Huckel's rule was 4n plus 2 pi electrons should participate. If n value is 1, so 4 ones are 4 plus 2, 6, right? So 6 comes in this category, right? So this molecule is going to be aromatic. I hope this is clear. Look at this particular thing. Oxygen has 2 lone pairs, out of which one is delocalized. Pi sigma lone pair, pi sigma lone pair. This is conjugated. One of the lone pair is conjugated. So leave that one lone pair, right? Now, 1 sigma, 2 sigma, and 1 lone pair. 1, 2, 3. Only localized lone pairs are taken into consideration when it comes to hybridization. Localized lone pairs are taken into consideration when it comes to hybridization. So 1, 2, 3. 2 sigma, 1 lone pair. Steric number 3. Steric number 3 means sp2, right? All the other atoms are already sp2. Perfect. So cyclic, planar. Now, 2, 4, and 6. 6 pi electrons are involved in the complete cyclic conjugation. So this is again going to be aromatic, right? As I told you, exocyclic bonds are not taken into consideration. Number one. Number two, all the atoms in the ring, they are sp2, right? It is cyclic. There are 2 pi electrons involved, right? 2 pi electrons means if n is 0, you get 2 pi. That means it is following Huckel's rule. So it has to be aromatic as well. Correct? It has to be aromatic. I hope this is clear. Now, guys, for aromaticity, we have to consider only the circumferential resonance. For the aromaticity, only circumferential resonance has to be taken into account. What is circumferential resonance? Say this is pi, sigma, pi, sigma, pi, sigma. This is something which you call a circumferential resonance. So you do not have to consider this particular pi bond when it comes to aromaticity. Only circumferential resonance you have to consider. Only those pi electrons which are showing the circumferential resonance, only they have to be taken into consideration. Perfect. So see, every carbon here is sp2. Okay, so it is cyclic as well as planar. Now, complete cyclic conjugation, complete circumferential resonance is there. Absolutely. Now, how many electrons? 2, 4, 6, 8, 10, 12, 14. So there are 14 pi electrons involved in the complete cyclic conjugation. Right? So is it following Huckel's rule? If n is 3, 4 3s are 12, 12 plus 2 is 14. So this is going to be aromatic. It is following Huckel's rule. Correct? Now, tell me about this one. This is benzene. 6 pi electrons, everything is there. It is aromatic. We know it. Look at this one. Look at this one. Every carbon is sp2. Cyclic, planar. Now, 2, 4, 6, 8, 10, 12, 14. 14 pi electrons are involved. So it is going to be aromatic. Absolutely. Right? It's going to be aromatic. Right, guys? It's going to be aromatic. Now, see. All the atoms here are sp2 hybridized. So it is planar. It is cyclic at the same time. Planar as well as cyclic. Complete cyclic conjugation is also there. Pi, sigma everywhere. Right? Now, 2, 4, 6, 8, 10. There are 10 pi electrons involved. Right? There are 10 pi electrons involved. So it is following the Huckel's rule. Because if n is 2, 4 2s are 8, 8 to 10. So 10 pi electrons, that means it is supposed to be aromatic. Right? 10 pi aromatic. Moving ahead. Moving ahead. Okay. This is something which we already discussed. Correct? Look at this one. Look at this one. First of all, the compound overall is cyclic. Now let's see whether it's planar. It will be planar only if all the atoms are sp2 hybridized. It will be planar if all the atoms are sp2 hybridized. Tell me whether this is localized or delocalized. This is localized. You have to consider this for hybridization as well. So 1 sigma, 2 sigma and lone pair. 1, 2, 3. 3 means sp2. This is sp2 and all the other carbons are already sp2. So this is planar. This is cyclic. Now how many electrons? Is there complete cyclic conjugation? Pi, sigma, pi, pi, sigma, pi, sigma, pi, sigma, pi, sigma, pi, sigma, pi, right? There is complete cyclic conjugation. Now, how many pi electrons? 2, 4, 6, 8, 10. There are 10 pi electrons involved in the complete cyclic conjugation. This lone pair, it is not participating in the resonance. It is not conjugated, right? So 10 pi means this aromatic. Correct? Now, this particular lone pair, have a look. Pi sigma lone pair, pi sigma lone pair. Is this localized or delocalized? This is delocalized. This is delocalized. Don't consider for hybridization. 1 sigma, 2 sigma, 3 sigma. 3 sigma means sp2. So this is cyclic, this is planar as well. Planar as well. Now, complete cyclic conjugation, pi sigma lone pair, pi sigma lone pair. Complete cyclic conjugation. How many pi electrons are participating in complete cyclic conjugation? 2, 4 and 6. 6 pi electrons means, following the Huckel's rule, it's aromatic. Correct? What about this one? Oxygen has 2 lone pairs, out of which 1 is in conjugation, 1 is delocalized. 1 is delocalized, right? So this is 1 sigma, 2 sigma and lone pair. 2 sigma, 1 lone pair. Steric number 3. So this sp2. sp2 means, since all the carbons are sp2 involving this oxygen, this also sp2. So this molecule is planar. And how many pi electrons? 2, 4 and these 2, 6. 6 pi electrons are involved in the cyclic conjugation. So this is going to be aromatic, right? This is going to be aromatic. Perfect, guys? Perfect. Look at this one now. Look at this one. Cyclic as well as sp2. Every carbon is sp2, so planar. pi sigma positive. Complete cyclic conjugation. 2 pi electrons are involved in the complete cyclic conjugation. Following Huckel's rule, so aromatic. Right? Look at this one. 2 and 4. 4 pi electrons. 4 pi electrons means anti-aromatic. Because 4 pi comes into the category of 4n pi. Right? This comes into the category of 4n plus 2 pi. Perfect? Right? So this is anti-aromatic. Look at this one. 2 plus radical, 2 plus 1, 3. 3 pi. 3 pi does not come into any category. So it has to be, it is neither aromatic nor anti-aromatic. It is non-aromatic. Yes? Look at this one. First of all, this boron, it's sp2 hybridized. This is sp2, this is sp2. So it's planar, it is cyclic, right? This is pi sigma. Boron has got the vacant p orbital. Pi sigma vacant orbital, pi sigma vacant orbital. So complete cyclic conjugation. How many electrons? I'll say 2 pi electrons are participating in the cyclic conjugation. So it is following the Huckel's rule. So it is supposed to be aromatic. Now look at this particular carbon. It's sp3 hybridized. sp3 means non-planar. Non-planar. Aromatic as well as anti-aromatic. They are planar. Aromatic as well as anti-aromatic. They are planar. Right? This is non-planar. That means it's non-aromatic. Non-planar means non-aromatic, right? Perfect. Look at this particular case. Leave exocyclic aside. sp2, 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 sp2 everywhere. Cyclic also, planar also, right? Yeah, cyclic also, planar also. Now tell me. Is it going to be aromatic or anti-aromatic? Quickly. Aromatic or anti-aromatic? Aromatic or anti-aromatic? Quickly. Aromatic or anti-aromatic? Quickly. Absolutely. This will be aromatic. What about this one? Cyclic. Planar also, because every carbon here is sp2. Cyclic conjugation also pi sigma negative, pi sigma negative, pi sigma pi. Complete cyclic conjugation. 2, 4, 6. So 6 pi electrons are involved in the complete cyclic conjugation. So this is aromatic, right? See, this is sp3. If this is sp3, that means it is non-planar. Non-planar means non-aromatic. Yeah? Perfect. I hope you're following this properly. Okay. Tell me, what about this one? What about this one? See, 2, 4. 4 pi electrons. That means anti-aromatic. Correct? Anti-aromatic. Look at this one. This particular carbon, it's sp3 hybridized. sp3 means non-planar. Non-planar means non-aromatic. Right? Non-aromatic. This is 2, 4, 6 and 8. 8 pi electrons means anti-aromatic. 8 pi electrons means anti-aromatic. Right? Look at this one. 2, 4, 6. 6 pi electrons means aromatic. 6 pi electrons means aromatic. Okay, I hope you are easily following this. What about this one? 2, 4, 6. 6 pi electrons. This is aromatic. Right? 2, 4, 6. 6 pi electrons. This is aromatic. Because they are already planar. They are cyclic as well. Complete cyclic conjugation is also present. Now see, 2, 4, 6. 6 pi electrons. So they are also, this is also aromatic. Right? This is also aromatic. Now, look at this particular one. Planar, cyclic conjugation, everything is there, right? Then have a look. 2, 4 and 6. 6 pi electrons, that means aromatic. Right? Perfect. 2, 4 and 6. 6 pi electrons, aromatic. Out of these two lone pairs, one lone pair will participate. So 2, 4 and 6. 6 pi electrons means aromatic. Why are all these aromatic? What is happening? See guys, 2, 4, 6, 8 and 10. 10 pi electrons means Huckel's rule, 4n plus 2 pi, right? So this again aromatic, right? See, in the middle you have to do nothing. You have to talk about the circumferential resonance, right? All the atoms present at the circumference, they are sp2 hybridized as well as it's cyclic. So 2, 4, 6, 8, 10. 10 pi electrons means aromatic, right? Uh, Look at this one. So nothing to do with this. 2, 4, 6, 8, 10. 10 pi electrons means aromatic. Perfect. This is parabenzoquinone. This is parabenzoquinone. 2 and 4. So 4 pi electrons. 4 pi electrons means it has to be anti-aromatic. It has to be anti-aromatic. It should be anti-aromatic. But I told you all this aromatic, non-aromatic, this is all experimental. So as per us, it should be anti-aromatic. But it has been observed that it is stable at room temperature. At room temperature, it is stable. If it is stable at room temperature, it from anti-aromatic, we say it is non-aromatic. It is comparatively stable. Okay? This is all experimental data, by the way. These are all experimental facts, which I'm telling you right now. As per our rules, it has to be anti-aromatic, but experimentally it has been seen that it is comparatively stable. So from anti-aromatic, it becomes non-aromatic. Okay, you have to remember this directly. Okay. Now, what about this particular case? What about this particular case? Quickly, what about this particular case? Quickly, what about this particular case? See, guys, remember aromatic plus non-aromatic. Or let me write it like this. Aromatic plus anti-aromatic makes the overall molecule as anti-aromatic. Aromatic plus anti-aromatic makes the overall molecule as anti-aromatic. Right? Perfect. Okay. This particular ring, this is aromatic, 2, 4, 6, 6 pi. And this sp3, this non-aromatic. So aromatic plus non-aromatic. Remember, aromatic plus non-aromatic makes the overall molecule as aromatic. So overall molecule over here is aromatic. Because this aromatic plus non-aromatic makes it aromatic. Okay? Aromatic plus anti-aromatic makes it anti-aromatic. Aromatic plus non-aromatic makes it aromatic. Right? For example, say, this is aromatic, this is non-aromatic. Aromatic plus non-aromatic makes it aromatic. Okay? This is aromatic, this is aromatic. Overall molecule is aromatic. Right? Now, what about this one? See, I can make it like this as well. I can make it like this as well. Absolutely, you can make it like this as well. Now, what about this ring? This aromatic, 2, 4, 6. What about this ring? This is 2 and 4. So this ring is aromatic, this ring is anti-aromatic. So aromatic plus anti-aromatic makes it anti-aromatic. Okay? Getting it? So this is anti-aromatic. Perfect, guys? Now, among these, identify which one is aromatic, which one is anti-aromatic, which one is non-aromatic. Have a look. This oxygen has got 2 lone pairs, out of which one will participate in resonance. One will be counted for hybridization. So 2, 4, and 6. 6 pi electrons involved in the complete cyclic conjugation. This again aromatic. Right? Perfect. Right, guys? Is it clear? This nitrogen, it has got a lone pair. Pi sigma lone pair. Pi sigma lone pair. So again, pi sigma lone pair, complete cyclic conjugation. So how many electrons? 4 pi electrons are involved in the complete cyclic conjugation. So it has to be anti-aromatic. Right? Now this ring, this is aromatic. This ring, it's aromatic because 6 pi plus 6 pi. 6 pi here also, 6 pi here also. So this is aromatic, this is aromatic. So aromatic plus aromatic makes it aromatic only. Right? Now, guys, understand, you have to remember these things, okay? This particular structure, the cyclic conjugated unsaturated hydrocarbons, these are called as annulenes. This is cyclic. This is conjugate as well, pi sigma, conjugate as well. Unsaturated, double bonds, unsaturated as well. Cyclic unsaturated hydrocarbons, these are called as annulenes. And this contains 4 pi electrons. So this is what you'll be calling as annuline 4. This is what you'll be calling as annuline 4. Perfect. This is what you'll be calling as annuline 8. This is what you'll be calling as annuline 8. Now, annuline 4. Since there are 4 pi electrons means It's going to be anti-aromatic. It's going to be anti-aromatic. This is going to be anti-aromatic, right? But aniline 8 as well as aniline 12. Aniline 8 as well as aniline 12. Okay? Aniline 8 as well as aniline 12. If I talk about aniline 8, it actually has got a tub-like structure. It actually has got a tub-like structure. Due to which it was looking like planar, but then it becomes non-planar. And when it becomes non-planar, automatically it becomes non-aromatic. So your aniline 8 and aniline 12, it is the example of non-aromatic. It is tub-shaped. It is tub-shaped. Do remember this particular thing as well. Do remember this as well, right? Similarly, I told you aniline 12, that is non-aromatic. What is this? This is basically benzene. This is aniline also, right? I'll be calling this as aniline. This is aniline 6. This is aniline 6 basically, right? What is it? It is aromatic, right? 6 pi electrons. Following the Huckel's rule, aromatic. Perfect. All right. Look at this. Look at this. 2, 4, 6, 8, 10. 10. So it has to be what? It has to be aromatic. It has to be aromatic because it's following the Huckel's rule, 4n plus 2 pi. But, if you look at this particular carbon, how many bonds it's forming? 1, 2, 3. So there'll be one hydrogen here. This is also forming 1, 2, 3. So there'll be one hydrogen here. Between the electron clouds of these hydrogens, the molecule overall becomes non-planar. So if it is non-planar, it becomes non-aromatic then. It becomes non-aromatic, right? Here, I think this molecule we've already done. This is 2, 4, 6, 8, 10. 10 pi electrons. 10 pi electron means following Huckel's rule. So it is going to be aromatic. It is going to be aromatic, right? It is going to be aromatic. So tell me whether all the things still here are clear or not. Tell me whether all the things are clear here or not. So for the molecule to be aromatic, it should be cyclic, it should be planar, complete cyclic conjugation should be there, and 4n plus 2 pi electrons should be, 4n plus 2 pi electrons should participate in the cyclic conjugation. Okay? 4n plus 2 pi means it can be either 2 pi or 6 pi or 10 pi or 14 pi, etc., etc. Right? If in the ring all the atoms are sp2, then the ring is planar. Right? Then the ring is planar. That's again something which we already know. Clear till here? I believe all the things are clear till here, yeah? For the molecule to be anti-aromatic, it has to be cyclic first. Then it has to be planar. There should be complete cyclic conjugation. But there should be 4n pi electrons involved in the complete cyclic conjugation. That means either 4 electrons or 8 electrons or 12 electrons or 16 electrons, etc. Yeah? Okay, now comes one more point, that is resonance energy. What is resonance energy, guys? See, I'll write its two definitions. The amount of energy which is used for delocalization. The amount of energy which is used for delocalization. The amount of energy which is used for delocalization. That's what we call as resonance energy. Or I will say the energy difference between the resonance hybrid and the most stable canonical form. Energy difference between the resonance hybrid and the most stable canonical form is something which is what we call as a resonance energy. So basically, if you talk about the resonance hybrid, or let me make you understand it like this, just a second. Let me take this example. CH2 double bond CH and H2, yeah? CH2 double bond CH. This is NH2. This is the molecule which I've taken, right? So first of all, this nitrogen, it has got the lone pair. Is this lone pair in conjugation? Yes, it's in conjugation. So this is basically one canonical form which is given to me. Can we make it another canonical form? We can do that, right? This will shift here. This will shift here. When you make its one more canonical form, it becomes CH2 negative CH2 negative, it becomes single. This is CH, this is double bond. This becomes NH2 positive. This is its one more canonical form. This is the second canonical form. Correct? This is the second canonical form. If I would want to make its hybrid also you can make. This is CH2, put a single bond first of all everywhere, right? Put a single bond, then get the partial double bond character here. Here is the partial double bond character. This is your delta negative. This is your delta positive. So this is your resonance hybrid. This is your hybrid, right? Now guys, if you remember, if I ask you, is the delocalization present in the canonical forms, or the delocalization is present in the hybrid? Where is the delocalization present? Delocalization is present in the hybrid, right? Delocalization is present in the hybrid. What is delocalization? What is delocalization? Delocalization of what? Delocalization of high energy electrons. My dear students, that amount of energy which is used for delocalization of high energy electrons, that amount of energy which is used for the delocalization of high energy electrons, that amount of energy is what you call as resonance energy. Point number one. What is resonance energy? It is the amount of energy which is used for delocalization. Delocalization is present in the hybrid. It is present in the hybrid. So in the hybrid, whatever amount of energy is used for delocalization, that amount of energy is what you call as resonance energy. Okay, that's called as resonance energy. Or there is one more way. The energy difference between resonance hybrid and most stable canonical form. These are the two canonical forms. Now, if I ask you among these two canonical forms, which canonical form is more stable? More stable. The one which does not carry any charge, right? Here the atoms do not carry any charge. So this is more stable. More stable means lesser energy. So energy of canonical form 1 will be less than that of energy of canonical form 2. So stability of canonical form 1 will be more than that of stability of canonical form 2. And resonance hybrid, it is the maximum stable among all, right? So my dear students, if I plot the energy diagram here, let's say this energy, if this is energy. If this resonance hybrid is the highest stable, so its energy will be the least. Let's say this point, this line represents the resonance hybrid, right? Now, this canonical form, it is more stable, means less energy. So C1's energy will be less than that of C2. Let's say this is C1's energy and this is C2's energy, right? The energy difference. Now, among these two canonical forms, which one is most stable? C1 is the most stable canonical form, right? The energy difference between the resonance hybrid and the most stable canonical form, that is something which you call as a resonance energy. So this energy gap here, I'll be calling as a resonance energy. Or I can write it like this. Resonance energy is basically, it is the energy of resonance hybrid minus the energy of most stable canonical form. Well, energy of hybrid is less than that of energy of most stable canonical form. So I would say the overall value will come out to be negative. So what does this negative sign signify here? This negative sign, I'll say negative sign signifies, negative sign tells us how much resonance hybrid is stable. How much resonance hybrid is stable? As that of what? As that of the most stable canonical form. This negative sign, it indicates that, it tells you that, it gives you the idea about how much resonance hybrid is stable than that of most stable canonical form. Okay? Right? Right, guys? Is it clear? Now, as I told you, the amount of energy which is used for delocalization is called as resonance energy. People, delocalization is present in the hybrid. So in the hybrid, some amount of energy is used for delocalization. If some amount of energy is used for delocalization, the amount of energy left with hybrid, will it be more or less? If some amount of energy is used for delocalization, the amount of energy left with the hybrid will be less. Lesser the energy, more the stability. That is the reason why hybrid is maximum stable. Because some part of energy is used for delocalization, and the energy carried by the hybrid after that is less. Lesser the energy, more the stability. Let me know once in the chats if it's clear. Let me know once in the chats if it's clear. Let me know once in the chats if it's clear. Quickly, guys. Let me know once in the chats if it's clear. Everyone. Everyone means everyone. Everyone means everyone. Look at one more case. Let's say I've got the molecule M. Here I've got the molecule N. I've got two molecules, right? Okay. Let's say I'm making one energy diagram for this particular molecule. Okay. This is its, for example, energy of resonance hybrid. And this is the energy of most stable canonical form, right? Similarly, for this particular molecule, let's say I'm making energy diagram. This is the line which represents energy of the resonance hybrid. And here somewhere, it is the energy of most stable canonical form. Now, you know, whatever is the difference between the hybrid and the most stable canonical form, that's called as a resonance energy. And over here, this is called as a resonance energy as well. Perfect. Now, where is the resonance energy more, M or N? So I'll say resonance energy of N is greater than that of resonance energy of M. Now you tell me, wherever resonance energy is more, I'll say there only more energy is utilized for delocalization. And wherever more energy is utilized for delocalization, there only energy with the molecule remains less, energy with the hybrid remains less, stability is more, right? So more the resonance energy, more is the energy used for delocalization. Lesser the energy hybrid has, more is the stability, right? So which one is stable among the two? If you talk about the stability order, the one which has more resonance energy will be more stable. So in short, you can say something like this. Stability is directly proportional to resonance energy. Stability is directly proportional to resonance energy. Is this clear? Stability is directly proportional to resonance energy. And you can see this resonance energy, it is directly proportional to number of conjugating sites as well. Number of conjugating sites. What is meant by the number of conjugate sites? You'll get the idea in some time. First, tell me whether this point is clear to you or not. Tell me whether this particular scenario is clear or not. Right? Stability is directly proportional to resonance energy. Right? And here, my dear students, we are now fit to solve the questions. Among these two, where is the resonance energy more? What do you think? Among these two, where is the resonance energy more? Where is the resonance energy more? Guys, have a look. Pi, sigma, negative, pi, sigma, negative. Here, pi, sigma, negative. Where are the conjugating sites more? First or second? Quickly. Where are the conjugating sites more? Conjugating sites are more here. Because throughout there is conjugation. More the conjugating sites, more the resonance energy, more the stability. Resonance energy is directly proportional to stability, okay? More the conjugating sites, more the resonance energy, more the stability. That's all. That's all. Look at this one. Pi, sigma. Everywhere there is conjugation, right? All these are conjugating sites. Look here. Pi, sigma, pi. And similarly, pi, sigma, pi. So, conjugating sites here are comparatively more. Conjugating sites here are comparatively more. Okay. Conjugating sites here are comparatively more. Correct? Correct? Correct, guys? So I believe you should be able to give the answer easily. Right? More the conjugating sites, more the conjugating sites, more the resonance energy, more the stability. Yes? Correct? All right. Look at these two. Look at these two. Look at these two. Look at these two. Where is the resonance energy more? See, pi sigma lone pair. All are conjugating sides. But here, this is the case of cross conjugation, right? At once it will be conjugated. At once it will show resonance with one of the two, right? This lone pair is conjugated from here. This lone pair is conjugated from here as well. At once it will show conjugation with one of the two. Now tell me where are the conjugating sides more? Here the conjugating sides are more. It's a linear conjugation, right? More conjugating sides, more resonance energy, right? More conjugating sides, more resonance energy. Perfect. Now guys, tell me one thing. Can you make the canonical form of this one? Can you make one more canonical form of this one? You should be able to make one more canonical form of this particular one, which will be like this. It will be like this. This is one more canonical form. Well, what about the stability of these canonical forms? They are different canonical forms, but their stability and energy is same, right? And these canonical forms, whose stability and energy is same, we call them as, I'll be calling them as equivalent resonating structures. Equivalent, I'll be calling these two as equivalent resonating structures, right? Well, if you make its resonating structure, if you make its one more resonating structure, it will come here, this will go here, right? So its resonating structure will be like this. Its resonating structure will be like this. Perfect. Now, should I be calling them as equivalent? They are non-equivalent. Do you remember? Resonance energy of equivalent resonance energy of that molecule, which forms equivalent resonating structures, right? That is always more. That is always more. These two are equivalent resonating structures. They have got same energy, same stability. Equivalent resonating structures these are, right? These are non-equivalent. That molecule which can form equivalent resonating structures, its resonating energy is always more, its stability is always more. Remember it directly. Remember it directly. Okay? Remember it directly. Tell me one thing now. Tell me one thing now. Among these two, what do you think? Among these two. I think these should be your homework questions now. These should be your homework questions now. Yeah? Which one? One or two? One or two? If you look at the first case, guys, it will undergo resonance. It will be like this. O negative, double bond O. These are equivalent resonating structures. Look at this. These are equivalent resonating structures. This is R, C double bond O, O negative, C double bond O, O negative. These are equivalent resonating structures, right? And that molecule which forms equivalent resonating structures, its resonance energy will be more. Okay, its resonance energy will be more. Now, among these two, where is the resonance energy more? What do you think? Among these two, where is the resonance energy more? Quickly. So this is your homework question. You can give it a try afterwards. Okay. All right. Among these two, I hope it is visible to the screen. Among these two, which one has got more resonance energy? First or second? Quickly. Where are the conjugating sites more? 6, more than 6. 2 benzene rings fused, right? Perfect. Correct. So more the conjugating sites, more is the resonance energy. Correct. Now look at this one. Look at this one. This is aromatic. 2, 4, 6. 6 pi electrons. Aromatic. This is non-aromatic. This is open. This is aromatic. This is non-aromatic. Okay. For the molecule to be aromatic or anti-aromatic, it has to be cyclic. If it is open, then it is non-aromatic. So this is aromatic, this is non-aromatic. It is more stable. More stable means more resonance energy. Right? You can solve questions like this as well. Perfect. Right? See, this is non-aromatic. And this one, 2 to 4. 4 pi means anti-aromatic. Which one is stable? Non-aromatic. More stable, more resonance energy. Right? Look at this one. Look at this one. Look at this one. See, this is pi sigma negative. Here, pi sigma negative, pi sigma negative. More conjugating sites. More conjugating sites means more resonance energy. More resonance energy. Right? Now, guys, these are two rings which are fused. Right? Two fused rings. Similarly, here you have got two fused rings. How do you check which one does have more resonance energy? This is decided as per the Fry's rule. What does Fry's rule say? Fry's rule says that more the benzene-like rings, more the benzene-like rings, more the benzene-like rings, more the resonance energy. Now have a look. This is your benzene ring, absolutely. This is benzene ring. Now, is this your benzene ring? For the benzene ring, there should be 3 pi bonds, but there are only 2 pi bonds. So, in this particular molecule, how many benzene-like rings are there? Only one benzene-like ring, one benzenoid ring. Here, if you look at this particular one, 2, 4, 6, this is a benzene ring. If you look at this one, 2, 4, 6, this is the benzene ring. So, 2 benzene-like rings, 2 benzenoid rings. More the benzenoid rings, more the resonance energy. Right? Look at the next one. Look at the next one. See, this is benzene-like, this is not benzene-like. So, one benzenoid ring, benzene-like, benzene-like. So, 2 benzene-like rings, more the benzene-like rings, more this resonance energy, more the stability. Correct? Now, here, this is benzene-like, 2, 4, 6. This is not, this is not. So, one benzene-like ring. Here, it is like this. This is benzene-like, even this is benzene-like, even this is benzene-like. So, 3 benzene-like rings, more benzene-like rings, more the resonance energy. Correct? Yes? I think all these things are clear. I think all these things are clear. Guys, I think let's take a break for 10 minutes. Okay? My legs are hurting a lot. Let's take a break for 10 minutes. This is the last topic which we have to complete. This is the last topic which we have to complete. We'll just take a break for 10 minutes, but everyone be back after 10 minutes. Okay? Everyone be back because this is the last topic which we have to complete. It will not take more than an hour. Right? So I'll be back. Just a second. The time right now is 2:04. Session resumes at 2:15. Right? Or 2:15, let's keep it as 2:18 or 2:20. Is it AM or PM? AM. 2:20. Take a break, freshen up, come back. At this time, where to go? Nowhere. I just want to sit for by like 10-15 minutes so that I can teach you this concept and we'll be done. Okay? So be back at 2:20. Until then, you guys. I'll see you in some time. Is anyone alive? Is anyone alive? Is anyone alive? Is anyone alive? Quickly. Let me know in the chats. Is anyone alive? Yeah? Okay, one last topic which is left in GOC, that is hyperconjugation. So guys, this is again one of the important topics of the chapter, right? Let's see what this hyperconjugation is all about and what kind of questions are asked from the topic hyperconjugation. See, I'm not going much into the details of the theory, right? I'll only tell you that part of the theory which is required to solve the questions of the term hyperconjugation. So first of all, let's get to know, when does hyperconjugation take place in a molecule? When hyperconjugation takes place in a molecule. The way in the resonance I told you, when resonance can happen in the molecule. In the similar way, let's get to know first of all, when hyperconjugation can happen in a molecule. See guys, look at this particular statement. Whenever CH sigma bond is adjacent to sp2 hybridized carbon, at that time a phenomenon operates which is something what you call as hyperconjugation. Try to understand what exactly I'm going to talk about. My dear students, for example, let's say you have got a molecule which has got an sp2 hybridized carbon. You have got a molecule that contains sp2 hybridized carbon. Adjacent to sp2 hybridized carbon, imagine there is one sp3 hybridized carbon. Adjacent to sp2 hybridized carbon, imagine there is one sp3 hybridized carbon. And with this sp3 hybridized carbon, if there is hydrogen or halogen attached, remember in the molecule, hyperconjugation is going to operate. In the molecule, hyperconjugation is going to operate. Right? So if in a molecule adjacent to sp2 hybridized carbon, there is sp3 hybridized. And towards this sp3 hybridized carbon, if there is hydrogen or halogen attached, remember, hyperconjugation is going to operate in such a molecule, right? Now, this sp2 hybridized carbon, it can be what? It can be either a carbocation like this. It can be a carbocation, right? It can be a carbon-free radical. It can be carbon-free radical. This is sp2 hybridized, even this sp2 hybridized. It can be carbon double bond carbon, right? It can be the carbon of this particular double bonded carbon. This is also sp2, this is also sp2. Or it can be a phenyl ring. Right? It can be the carbon of the phenyl ring, right? Whenever you see such kind of the scenario in the molecule, wherein with the sp2 hybridized carbon, there is sp3 hybridized carbon attached, and towards this sp3 hybridized carbon, there is hydrogen or halogen attached. Remember, I would say in the molecule, hyperconjugation is going to operate, right? Remember, in the molecule, hyperconjugation is going to operate. So first of all, before making you understand what this hyperconjugation is, let's exactly see whether you will be able to identify whether in the molecule hyperconjugation is there or not. Have a look, people. Have a look. For example, this is one of the scenarios. These are some molecules. Just a second. Let me just arrange them. Just a second, people. Just a second. Just a second. So, for example, this is hydrogen. This is hydrogen. Okay. Just a second, let me just, there is a, this is CH2 positive. This is CH2 positive, this is this, okay? And here, just a second. This is CH2 positive here. And in this case, in the last case, this is the CH3 which is attached here. Can you let me know, out of all these molecules, where do you exactly see the hyperconjugation getting operated? Can you let me know in the chats? Is hyperconjugation going to operate in the first molecule? Try to understand. Try to understand, people. I already told you the criteria for hyperconjugation. See, this is, if you look at this particular carbon, this is your sp2 hybridized carbon, right? Because this carbon double bond, this sp2. Towards sp2, this is your sp3 hybridized carbon attached. And with this sp3 hybridized carbon, there is hydrogen attached, right? So in the first molecule, hyperconjugation is going to take place, right? Yes. Look at the second one. Look at the second one. This is your sp2 hybridized carbon, absolutely sp2 hybridized. Adjacent to this, this is sp3 hybridized. And with this sp3 hybridized, hydrogen is attached. So it will show hyperconjugation, right? It will show hyperconjugation. Look at the next one. Look at the next one. Look at the next one. Is this going to show? Is hyperconjugation is going to operate here? What do you think? Will hyperconjugation operate here in this? Quickly. Quickly. What do you think? In this one? Yes or no? Yes or no? Yes or no? Yes or no? Quickly, guys. The answer is a big no. Why? Because this is sp3 hybridized carbon. This has to be sp2. Okay, look at this one. This is CH2 radical. This is sp2, this is sp3, and hydrogen is attached with the sp3. So hyperconjugation is going to operate, right? This is sp2. This has to be sp3, but it's also sp2, right? In this one, it's not going to operate. In the next one, this carbon right here is sp2, right? This carbon here is sp2, and adjacent to that, you have got sp3, of course, and with this hydrogen is attached, so hyperconjugation is going to operate here. Perfect. So you got to know how to identify whether in a molecule hyperconjugation is going to operate or not. Perfect. You got to know in a molecule hyperconjugation is going to operate or not. Well, my dear students, one more thing. That sp3 hybridized carbon, which is attached to sp2 hybridized carbon, this is something which you call as alpha carbon, right? And the hydrogens which are attached with the alpha carbon, these are called as alpha hydrogens. These are called as alpha hydrogen, right? These are called as alpha hydrogen. Now let's have a look exactly, since you got to know how to identify, whether hyperconjugation is going to operate in a molecule or not. Now it is the time to understand what this hyperconjugation exactly is all about. Try to understand few things. Look at the definition. It is the sigma electron delocalization. It is the sigma electron delocalization due to the overlap of p orbital of sp2 hybridized carbon with the adjacent CH sigma bond. Now, what is meant by this? What is meant by this statement? See, guys, try to understand. For example, I'm taking the molecule CH3, CH2 positive. Okay? CH3, CH2 positive. My dear students, if you look at the hybridization of this particular carbon, it's sp2 and this is sp3. Correct? sp2, sp3. Right? And with this sp3 carbon, there are hydrogens attached. So hyperconjugation is going to operate here. Okay. Now, what is hyperconjugation basically? How can we understand this? See, first of all, if this carbon is sp2 hybridized, that means if I talk about carbon in particular, carbon has got 2s and 2p, right? 2s and 2p. If this carbon is sp2, so this is s, this is p, and this is s and these are 2p. So it has undergone sp2 hybridization, and there is one pure p orbital as well, right? So whenever there is sp2 hybridization, how many hybrid orbitals do we get? We get 3 hybrid orbitals. Perfect. So this particular carbon, if I talk about, there will be 3 hybrid orbitals basically. For example, this is one hybrid orbital, this is one more hybrid orbital, and this is one more hybrid orbital. Perfect. These are the 3 hybrid orbitals of this particular carbon. Perfect. And apart from the 3 hybrid orbitals, there will be one p orbital which will be perpendicular to the plane containing these hybrid orbitals. So there is one pure p orbital like this. There is one pure p orbital like this. This is sp2 hybridized. This is sp2 hybridized orbital. This is sp2 hybridized orbital. This is pure p orbital, right? Now guys, as you can see, two hydrogens, one hydrogen has come from this side and made a sigma bond. One more hydrogen would have come from this side, made a sigma bond, right? Now one more sp2 hybridized of this particular carbon, right? See, this particular carbon is sp3. If this is sp3, can I say, if this is sp3, can I say sp3 means 4 hybrid orbitals? Let's say this is one of the hybrid orbital of this sp3 hybridized carbon, or let me make it bigger in size. This is sp3 hybridized orbital of this particular carbon. There are in total 4 hybrid orbitals, out of which 1 I have made, and this is the sigma bond which is formed in between, right? Direct overlap. Similarly, this is, for example, one more hybrid orbital sp3, this is one more sp3, and this is, for example, one more sp3, right? And since there are 3 hydrogens attached, so one hydrogen would have overlapped here, one hydrogen would have overlapped here, and one hydrogen would have overlapped here. So this is the orbital diagram of the molecule which I took. This is the orbital diagram. This is the orbital diagram of the molecule which we took. Perfect. Now, my dear students, this particular bond, it is between what? It is sp3 hybrid orbital of carbon and s orbital of hydrogen, right? Now, among hydrogen and carbon, which one is more electronegative? Carbon. So can I say the sigma electron density will be more towards carbon? The sigma electron density will be more towards carbon? Absolutely. The sigma electron density will be more towards carbon. The sigma electron density will be more towards carbon. Correct? Now guys, try to understand. See, this is sp2, this is sp2, and this is sp2. So this is trigonal planar. sp2 means trigonal planar. So this particular bond, and this particular bond. Imagine these 3 bonds are present on board. And this p orbital, it is perpendicular to the plane containing these 3 bonds. So imagine one of the lobe of p will be towards you, and one more lobe will be behind the board. One lobe is towards you, and another lobe of p is behind the board. Right? Similarly, this is sp3. So if this is sp3, I'll say this particular orbital, this sp3 hybrid orbital, one will be towards you, this particular one will be behind you, and this one will be also behind the board. Correct? So can I say this p orbital, which is towards you, and this sp3 hybrid orbital, which is also towards you, can I say they are going to overlap? They are going to partially overlap. What kind of overlap this is? Right? So this is the overlap. This is the overlap which is happening. This is the overlap which is happening. So what kind of overlap this is? Can I say this is sigma p overlap basically? Right? This was your CH sigma bond. Right? Consider one thing. This p orbital, one of the lobe is towards you. Right? Similarly, this sp3 hybrid orbital, it is also towards you. So they are parallel. They are parallel. They'll do the sideways overlap. Okay? Perfect. Perfect, guys. So should I call this as sigma electron delocalization or pi electron delocalization? This is something which I'll be calling as sigma electron delocalization. And this sigma electron delocalization is something which you call as hyperconjugation. This is what you call as hyperconjugation, or what you call it simply as, you can call it as sigma p overlap. You can call it as sigma p overlap. And this sigma p overlap This is something which we call as hyperconjugation. I hope this is clear to everyone. Right? I hope this is clear to everyone. Yes, let me know once in the chats if this concept is clear. The sigma p overlap is something which you call as hyperconjugation basically. Yeah? Right, people? Let me know once in the chats. See, basically, this particular bond, this bond, and this bond, right? They were present on the board, right? This p orbital is perpendicular to the board, one towards you and another lobe behind the board, right? Similarly, imagine this sp3 hybrid orbital of the carbon. It is towards you. If this is towards you, this is towards you. I'll say these two are parallel. They'll show the parallel overlapping. And this is the basically delocalization of what? This is the delocalization of sigma electrons. This is the delocalization of sigma electrons, right? And sigma electron delocalization is what you call as hyperconjugation, which is also called as sigma p overlap, right? Or you can call it as sp3p overlap as well. sp3p overlap as well. You can call this overlap as sp3p overlap as well. I believe this is clear. This is the orbital diagram first of all. This is the orbital diagram first of all. Now every time you're not supposed to make this orbital diagram. See how exactly you guys will be making the hyperconjugated structures. This is CH2 positive. First of all, tell me one thing. What happened here? Sigma electron delocalization took place. And you know, due to delocalization, whether the delocalization is sigma or pi, due to relocalization, what happens? Due to delocalization, what happens? What happens? Due to delocalization, what happens? Stability increase or decreases? Due to delocalization, what happens? Stability increase or decreases? Stability increases. Right? So this was basically your carbocation. So can I say, due to this hyperconjugation, the stability of carbocation would have increased? Absolutely, the stability of carbocation would have increased. Right? Perfect. So can I say hyperconjugation increases the stability of carbocation? I hope this is clear. I hope this is clear to everyone. Yes. Now, how do we exactly make it? You are not supposed to make the orbital diagram every time. Just remember one simple thing. See, this is your sp2 hybridized carbon. Adjacent to it, it is sp3, right? That means this is your alpha carbon. These are your alpha hydrogens. So first of all, let me make it like this. This is C, this is H, this is H, and this is H. This is sigma, this is CH2 with a positive here, correct? Now, this is the perfect candidate for hyperconjugation, right? Now, how you are going to show it? Just guys, do one thing. You just have to shift this sigma bond over here, right? You just have to shift this sigma bond over here. Like what happened here, right? What happened here? You just have to shift this sigma bond over here. When you shift this sigma bond over here, what will happen? This is C, this is H, this is H, and there'll be H. This H is not completely lost as H positive. Why is that? I'll tell you the reason. This is a double bond. This is now CH2. Now this H positive, which was supposed to be completely lost, it is not completely lost here. It is still influenced by this electron density. This electron density will be holding this H positive comparatively. So this H positive is not completely lost, right? This H positive is not completely lost here. This electron density will be holding this H positive comparatively towards it. Okay. Now similarly, guys, similarly, since it is a carbon single bond carbon, and towards this carbon single bond carbon, free rotation is possible. You know it. So in one scenario, this particular orbital would have come towards you and done the overlap with this one. In another scenario, this particular orbital would have come towards you, right, and done the overlap with what? With the p orbital. Perfect. So it is not only this H positive which can do the, which can participate here, right? It can be this H positive as well. It can be this hydrogen as well. Yeah. Okay. So One more hyperconjugating structure will be like this. This is carbon. This hydrogen will be as such. Now this hydrogen will be lost as H positive. Not completely lost though, right? This is H. This is double bond. This is CH2, right? Similarly, in one more scenario, this is carbon. This is hydrogen. This is hydrogen, and here you'll be writing H positive. There's a double bond here. This is CH2. Perfect, right? These are the possible cases which can happen. Correct? What I'm trying to say? Along this single bond, free rotation is possible. Free rotation is possible. If along this single bond, free rotation is possible, that means in one scenario, these two will overlap. In another scenario, this particular one and this particular one, they'll overlap. In another scenario, this particular one and this particular one, they will overlap, right? So tell me, how many alpha hydrogens it had? How many alpha hydrogens were here? 3 alpha hydrogens. 3 alpha hydrogens were here. Perfect. 3 alpha hydrogens. Right? So can I generalize the statement here? Number of hyperconjugating structures involving CH cleavage. Is always equal to the number of alpha hydrogen. Is always equal to the number of alpha hydrogen. Is always equal to the number of alpha hydrogen. So in total, this was already one hyperconjugating structure. This is one more, this is one more, this one more. In total, how many hyperconjugating structures are there? 4. 4, right? So can I say total number of hyperconjugating structures? Total number of hyperconjugating structures is equal to number of alpha hydrogens plus 1. Number of alpha hydrogens plus 1, right? These are the total number of hyperconjugating structures. These are the number of hyperconjugating structures involving CH cleavage. Right? Clear, guys? So can I say more the hyperconjugating structures, more the delocalization of sigma electrons? And more the delocalization means more the stability, right? Yes? You can say something like that. Perfect. You can say something like that. I hope you got to know the exact idea. Now tell me, if you want to make the hybrid, over here, how this hybrid will look like? Can you tell me that? See, this is the carbon and this is your CH2. Perfect. I'm putting a single bond here, right? As per this structure, there is a single bond. As per this structure, there is a double bond. So it's a partial double bond, right? Perfect. In one of the cases, this hydrogen is leaving as H positive. In one more case, this hydrogen is leaving as H positive. In one more case, this hydrogen is leaving as H positive. Perfect. Right? Right, guys? Is this clear? This structure is telling you that carbon carries positive. This structure is telling you carbon is not carrying any charge. So I'll write it as delta positive over here. So this is your hybrid. This is your hybrid over here. Right? This is your hybrid over here. Perfect. This is your hybrid over here. Right? So my dear students, I hope this particular point is clear. Hyperconjugation, it's also called as sp3p overlap, or you can call it as sigma p overlap. Now, let's have a look on the types of hyperconjugation. Let's have a look on types of hyperconjugation. Let's have a look exactly on types of hyperconjugation. So first of all, look at this particular molecule. This is sp2 hybridized carbon. Adjacent to it, there is sp3, right? This is called as alpha carbon. And these are the alpha hydrogens. So this will undergo hyperconjugation. It will show hyperconjugation. And which hyperconjugation I'm talking about? Sigma pi hyperconjugation. So how you are going to make its hyperconjugating structures? See guys, first of all, you just have to shift this bond here, and this pi bond will be shifted in this direction. So what do you get? You get the first structure like this. This is hydrogen as H positive. This is hydrogen as such, hydrogen as such. There is a double bond here, right? This is CH, this is single bond. This will be CH2 negative. Perfect. This is one hyperconjugating structure. In another case, this hydrogen would have left as H positive, right? So another hyperconjugating structure will be something like this. This C, this hydrogen as such, this is H positive here, and this is hydrogen. There is double bond here, right? This is your CH, and this is your CH2 negative. Perfect. In another case, this hydrogen would have left as H positive. So this was H, this is H, and this is H positive, double bond, CH, single bond, CH2 negative. Perfect. Now tell me how many alpha hydrogens were here? This is alpha hydrogen, alpha hydrogen, alpha hydrogen. There were 3 alpha hydrogens. So if I ask you, how many hyperconjugating structures will be there which involve CH cleavage? This involves CH cleavage, this involves CH, this involves CH. Number of alpha hydrogens is always equal to the number of hyperconjugating structures involving what? Involving what? Involving CH cleavage. Right? How many total hyperconjugating structures are there? How many total? 1, 2, 3, 4. 4, right? You already know total number of hyperconjugating structures is equal to number of alpha hydrogens plus 1. Okay? Right? So what kind of hyperconjugation this was? This was sigma pi hyperconjugation. This was sigma pi hyperconjugation. Correct? This was sigma pi hyperconjugation. Right? Now there is one more hyperconjugation, which is going to be sigma positive hyperconjugation. There is one more hyperconjugation, which involves sigma positive hyperconjugation. Have a look. This is sp2 hybridized carbon. With this, it is sp3. That means this is the alpha carbon. These are the alpha hydrogens. So hyperconjugation will be there. Right? How do you exactly show the hyperconjugating structures over here? See, first of all, if I ask you how many hyperconjugating structures will be there which involves CH bond cleavage, number of alpha hydrogens are 3, and you know number of alpha hydrogens is equal to number of hyperconjugating structures involving CH bond cleavage. If I ask you how many total hyperconjugating structures will be there, number of alpha hydrogens plus 1, 3 plus 1, that is 4. Right? That is 4. Total hyperconjugating structures. Now, make the structures. Shift this bond over here. Shift this sigma bond over here. This will be C. This will be H positive. Right? This will be your H. This will be your H. This is double bond. And this is CH2. Correct? Now, in one more case, I would say this hydrogen would have lost. Right? As H positive. Not completely lost. You know it already. What is the logic? Right? This is CH2. In one more scenario, this carbon, this hydrogen will be as such, this hydrogen will be as such, and here you'll be writing H positive, and this is CH2. Perfect. So these are the possible 4 hyperconjugating structures over here, right? Okay. And you know, I've already told you, number of hyperconjugating structures involving CH cleavage. Involving CH cleavage. It is always equal to what? It is always equal to the number of alpha hydrogens. It is equal to the number of alpha hydrogens. Here the alpha hydrogens were 3. So there are 3 hyperconjugating structures which involve CH cleavage. Right? If I ask you how many total hyperconjugating structures will be there, that is total hyperconjugating structure. Total hyperconjugating structures will be number of alpha hydrogens plus 1. So 3 plus 1 comes out to be 4, which you can see over here, right? I hope this is clear. So this was your sigma positive hyperconjugation. Now similarly, there is sigma odd electron hyperconjugation. There is sigma odd electron hyperconjugation. There is sigma odd electron hyperconjugation. There is sigma odd electron hyperconjugation as well. Sigma odd electron hyperconjugation. First of all, this is sp2 hybridized carbon adjacent to this sp3, right? So this alpha carbon, these are alpha hydrogens. So it will also show hyperconjugation. How will you make it structures? How will you make it structures? How will you make it structures? You'll make it like this. See, You will make it like this. So first of all, this odd electron will come here. One of the electron from here will come here, and one of the electron will go towards hydrogen, right? So you'll be getting C. This will be H radical. This will be H. This will be H. And in the middle, it's going to be a double bond. And this is going to be CH2 here, right? This is one of the structures, hyperconjugating structures. Similarly, one more. This is C. Above hydrogen as such. This will be H radical. This will be H. And this is double bond CH2. This is one more hyperconjugating structure. Similarly, one more. This is H. This is H. And this is H radical over here. This is double bond. This is CH2. This is one more hyperconjugating structure. So structure over here. Perfect. Now you tell me one thing. How to make the hybrid over here? How do you make the hybrid? How do you make the hybrid? So I'll write first carbon. Then I'll write CH2. Then I'll put a single bond. Right? Here there is a single bond. Here there is a double bond. So it's going to be partial double bond. Right? Partial double bond. Right? So here it's H radical. Or you can say H delta radical. Right? H delta radical. This is also H delta radical. Correct? And this carbon is having radical. This carbon is not having any radical. So this is delta radical. This is delta radical. Right? So similarly, guys, we did not make the hybrid in this particular case. How the hybrid will look like here? How the hybrid will look like here? See, this is C, single bond CH2. Right? As per this structure, there is a single bond, but here is a double bond. So it's a partial double bond here. Right? Rest, you know, this is H. This is H, this H positive. So it's H delta positive. This can be written as H delta positive. This can be also written as H delta positive. This can be written as H delta positive, right? And what all? See, as per this carbon carrying positive, here it's not carrying positive, so it is delta positive here also. So this is your hybrid in this particular case, right? This is your hybrid in this particular case. Did we make the hybrid in the first case? First hyperconjugation was sigma pi. Second was sigma positive. Third was sigma radical, right? What about the hybrid in this particular case? What about the hybrid in this particular case? So this is carbon, right? Single bond, CH, right? I'll put single bond everywhere first of all, right? Now, the first structure, this is going to be H delta positive. This is going to be H delta positive. This is going to be H delta positive, right? Here's a single bond, but this structure says it's a double bond. So partial double bond. Double bond, here is a single bond. So partial double bond. Correct? Partial double bond. Perfect. And here I'll be writing delta negative. So this is your hybrid over here. This is your hybrid over here. This is your hybrid over here. Perfect. So you have got three types of hyperconjugations which we discussed. One was sigma pi hyperconjugation. Another was sigma positive hyperconjugation. Another one is sigma odd electron hyperconjugation. Right? Now, my dear students, generally, according to Muller and Mulliken, hyperconjugation is exactly of two types. One is called as sacrificial hyperconjugation. One is called as isovalent hyperconjugation. Now, what is sacrificial and what is isovalent? My dear students, just look at the definition. Look at the definition. The type of hyperconjugation where charge separation takes place. Where charge separation takes place. The type of hyperconjugation where charge separation takes place. See guys, just a second. If you look at this hybrid, has the charge separation taken place? This is positive, this is negative. Charge separation has taken place. And that particular hyperconjugation wherein charge separation takes place. Over here, positive, this is negative. Charge separation has taken place. And let me tell you, that type of hyperconjugation in which charge separation takes place, that is something which you call a sacrificial hyperconjugation, and its example is sigma pi hyperconjugation. Its example is sigma pi hyperconjugation. Right? Right? Perfect. Similarly, my dear students, one more is isovalent, wherein charge separation does not take place. For example, sigma positive or sigma odd. See, this is sigma odd. Is there any charge separation? There is no charge separation. Similarly, sigma positive. Everywhere there is positive. There is no charge separation here. There is no charge separation. Right? There is no charge separation here. So you have got two types of hyperconjugations. One is sacrificial and one is isovalent. One is sacrificial and one is isovalent, right? My dear students, this is something which I've already told you. Number of hyperconjugative structures involving CH cleavage. Involving CH cleavage is equal to what? Is equal to the number of alpha hydrogens, right? Is equal to the number of alpha hydrogens. Now, my dear students, the point is, this hyperconjugation also we break into two parts. One is plus H, one is minus H. One is plus H and one is minus H. Plus H, plus means donating, minus means withdrawing. Donating, withdrawing. Now try to understand. Over here, this is a CH3 group. This is the CH3 group which is attached with the conjugated system. This is the CH3 group which is attached with the conjugated system. If you look at the particular case, this is sp2, this is sp3. So this alpha carbon, these are alpha hydrogens. So hyperconjugation will operate, right? This bond will shift here, this bond will shift here, right? Perfect. So let me tell you one thing. I mean, if I ask you whether this group is increasing the electron density in the conjugated system or not, quickly, whether this particular group is increasing the electron density in this conjugated system through sigma electron delocalization. What do you think? Yes or no? See, this bond you're shifting here, right? And these bonds you're shifting. Perfect. So can I say this particular group, it is increasing the electron density in the conjugated system with the help of sigma electron delocalization. And that group which increases the electron density in the conjugate system through sigma electron delocalization, we say that group shows plus H effect. That group shows plus H effect. So CH3 group, what does it show? It shows plus H effect. It shows plus H effect, right? It shows plus H effect. It shows plus H effect. As I told you already, mesomeric effect, it is not going to, mesomeric effect that does not operate at the meta positions. Similarly, hyperconjugation. Hyperconjugation also does not operate at meta position. Hyperconjugation does not operate at meta position. See, this is your CH3 group attached, right? This is your sp2 hybridized carbon, this is sp3. These are alpha hydrogens, right? So plus H hyperconjugation will happen here, right? Plus H hyperconjugation will happen here. If you look at all these scenarios, negative charge getting created at ortho, negative charge getting created at para, right? Perfect. So can I say, due to hyperconjugation, the charges, they also get created only at ortho and para positions? So I would categorically say your hyperconjugation, it operates at ortho para. It does not operate at meta position, right? Your mesomeric effect as well as hyperconjugation, they do not operate at meta. They do not operate at meta positions. Okay. Now, guys, what are the applications of this hyperconjugation? What are the applications of this hyperconjugation? Let me tell you, plus H effect. Plus H effect. It stabilizes the carbocation. It stabilizes the carbocation. Plus hyperconjugation, plus H effect, it stabilizes the carbocation, right? Similarly, my dear students, your hyperconjugation, it stabilizes your alkene as well. It stabilizes your alkene as well. It stabilizes your alkene as well. For example, have a look. Plus H effect, it increases the stability of alkene. It increases the stability of alkene. Try to understand. This is alkene. Here you have got alkene. Here you have got alkene. Right? Now, this is sp2. This is sp2. This is the sp3. Right? So these are the alpha hydrogens. So how many alpha hydrogens are here? 3 alpha hydrogens. sp2, sp2. This is sp3. This is sp3. These are alpha hydrogens. These are alpha hydrogens. So how many? 6 alpha hydrogens. Over here, 0 alpha hydrogens. Right? More the alpha hydrogens means more are the hyperconjugative structures. More the hyperconjugative structure means more is the delocalization of sigma electron, right? More is the delocalization of sigma electrons. And more delocalization means more stability, right? So wherever alpha hydrogens are more, directly you will say that alkene is more stable. So I'll say third alkene is more stable, followed by 2, followed by 1. Just you have to count the alpha hydrogens. That's it. Just you have to count the alpha hydrogens. That's it. More the alpha hydrogens, more the stability. Right? More alpha hydrogens, more is the stability of the alkene. Okay. Does plus H effect apply on carbocations? This is CH3. This is first of all sp2 hybridized. This is sp3 hybridized. Right? So these are your alpha hydrogens. Perfect. Is hyperconjugation going to happen here? Yes. Hyperconjugation will be operated. Due to hyperconjugation, what will happen to the stability of carbocation? Will it increase or decrease? Will it increase or decrease? My dear students, plus H effect. See, this CH3 group, it shows plus H. It shows plus H. And plus means donating, right? And all the electron donating groups, they increase the stability of carbocation, right? Okay? So do remember plus H groups, plus H showing groups, they also increase the stability of the carbocations. They also increase the stability of carbocation. Right? They increase the stability of carbocations. Now, if you remember, earlier I gave you the series for plus M, plus I, minus I. In the similar way, I want you guys to remember this particular series. This is the plus H series. This is the plus H power. Plus H power of CH3 is more than that of CH2D, where D is deuterium, CHD2, CD3. This is something which again you have to remember. This again something which you have to remember. And if you remember, guys, I have already told you mesomeric effect. How many effects we discussed till now? Mesomeric, hyperconjugation, and inductive. Remember, mesomeric effect, it always dominates over hyperconjugation, and hyperconjugation always dominates over inductive. That is the reason, if you remember, I used to give you that series minus M, minus H, minus I, right? Perfect. If you remember, I used to give you that series for solving the questions. Remember, mesomeric always dominates over hyperconjugation. Hyperconjugation always dominates over inductive. Right? One more important thing. Now, let's have a look on few questions and we are almost done. See guys, carbocations. Plus H increases the stability of carbocation, right? Is there any alpha hydrogen here? No. How many alpha hydrogens do we have here? We have 3 alpha hydrogens. How many alpha hydrogens do we have here? We have 2 alpha hydrogens, right? More the alpha hydrogens, more the hyperconjugated structures. That means more the stability of carbocation, right? So 2 is greater than 3, greater than 1. This is the stability order of these carbocations, right? Your alpha hydrogens, they stabilize the carbocation. How many alpha hydrogens here? This is your sp2, this sp3. Hydrogen is attached here, so only 1 alpha hydrogen, right? Over here, this is your alpha carbon, this is your alpha carbon. 2 hydrogens are attached here, 1 hydrogen is attached. So 3 alpha hydrogens. So this carbocation is stabilized by 3 alpha hydrogens. This carbocation, 1, 2, 3, 3 alpha hydrogens, 2 and 2, 3 to 5 to 7. This carbocation is stabilized by 7 alpha hydrogens. More the alpha hydrogens stabilizing the carbocation. More the alpha hydrogens stabilizing the carbocation. More is going to be the stability of the carbocation, right? More alpha hydrogens means more hyperconjugated structures. More hyperconjugated structures means more stable the carbocation, right? Correct? Correct, guys? What about these two? This is your sp2. This is your sp2 as well. sp3, sp3, right? Perfect. sp3, sp3, right? Now you tell me, which one is going to be more stable? This is CD3. This is CD3. Over here you have got CH3. Plus H power of CH3 is more than that of CD3. Right? We have discussed it. Plus H power of CH3 is more than that of CD3. Right? Now you tell me the answer. Plus H power of CD3 is more than that of, sorry, CH3 is more than that of CD3. Tell me, which one is more stable? Quickly. Which one is more stable, 1 or 2? Guys, you should answer this now, yeah. Plus H of CH3 is more than that of CD3. And plus H, what does it do? It increases the stability of the carbocation. So first one is more stable than second. Right? Look at this one. Do you see any alpha hydrogens here? This is C and 3 methyl groups. This is C and 3 methyl groups. C and 3 methyl groups. It's like this. If I talk about this carbon, this is C and this is CH3 whole thrice. Right? If I talk about this, this is the carbon which I'm talking about, correct? C, CH3 thrice. This is sp2. Towards sp2, sp3 is attached, but this sp3 carbon does not have any alpha hydrogen. It does not have any alpha hydrogen because this carbon is attached to 3 other carbons. So no alpha hydrogen. Over here, 3, 3, 6, 3, 9, 9 alpha hydrogens. More the alpha hydrogens, more the stability of the carbocation. Right? More the stability of the carbocation. My dear students, still now I was showing you plus H. Now there is a group which can show minus H as well. Which can show minus H as well. There is a group which can show minus H as well. For example, you have a CX3 group. CX3, where X is a halogen. CH3 group, it shows plus H. CX3 group, it shows minus H. It shows minus H. Have a look. This is your sp2 carbon. This is sp3, which is your alpha carbon. And I had told you in the beginning, towards this alpha carbon, if either hydrogen is attached or halogen is attached. If either hydrogen is attached or halogen is attached, hyperconjugation is going to operate, right? But here, this hyperconjugation, if you look at this hyperconjugation, this group is not going to show plus H, it is going to show minus H. Why is that? Look at this one. Imagine this is your conjugated system. Imagine this is your conjugated system. You are shifting this bond in this direction and this bond in this direction, right? And you are getting this kind of the structure. Similarly, one more. Similarly, one more. So in the conjugated system, when you attach CX3, did the electron density in the conjugated system increase or decrease through sigma electron delocalization? It decreased. It decreased. That's the reason why I'll tell you, that's the reason why you'll remember that your CX3, it is going to show minus H effect. It is going to show minus H effect. CH3 shows plus 3, CX3 shows, sorry, CH3 shows plus H, CX3 shows minus H. One is donating, another one is withdrawing. CX3 is withdrawing. It is withdrawing, as simple as that. And there, look at this one. This is CX3. This is CX3. This is not CH3. This is CX3 attached to a conjugated system. Is it increasing the electron density or decreasing the electron density in the conjugated system? It is decreasing the electron density in the conjugated system through sigma electron delocalization, right? So this is what is showing minus H here, right? CX3 decreases the electron density in the conjugated system. Therefore, it shows minus H. Remember, CH3 shows plus H, CX3 shows minus H, right? Okay. Already I told you. CH3 plus H operates at ortho and para. That means due to plus H of the group, the charges in the conjugated system are generated at ortho and para. In the similar way, when you attach minus H group with the conjugated system, again the charges will be present, again the charges will generate at ortho and para. So what does that mean? That means your minus H. It also does not operate at meta position. If you have a look, this is your CX3. This is your CX3 group. It shows minus H. So when you shift this bond here, a positive charge gets created. Here. So positive charge will either get created here, then it will get created here, or it will get created here, right? So due to the hyperconjugation, either plus H or minus H, charges get created only at ortho and para positions. Charges do not get created at meta positions. It is just the difference is simple. When plus H group is attached, negative charges are generated at ortho para. When minus H group is attached, positive charges are generated at ortho and para. Positive charges are generated at ortho and para, right? So your plus H minus H, they do not operate from meta positions. They do not operate at meta positions. Now, this is the series of minus H, which you need to remember. CI3, it shows maximum minus H. CBr3, CCl3, CF3. This is the minus H series. Minus H series. This is the minus H series, guys, which you have to remember as well. Okay? So there are few questions which you need to solve, and we are done. And we are done. And we are done. Arrange the following as per Ka. Ka means acidic strength. Acidic strength. If you remember, when you talk about acidic strength, first you give priority to minus N, then minus H, then minus I, then plus I, then plus H, then plus M. Right? Because acidic strength is directly proportional to stability of conjugate base, and conjugate base is stabilized by electron withdrawing groups, right? And minus M will dominate. Mesomeric will dominate over hyperconjugation, that will dominate over inductive. Now you give me the answers. You give me the answers. First of all, look at the common site. This is the site which is common to everyone. This is the site which is common to everyone here, right? This is the site which is common to everyone. This is the site from where hydrogen is going to leave as H positive. Okay, now tell me one thing. This CH3, it is present at para. So CH3 is going to operate plus H. CH3 at meta, you do not consider hyperconjugation. You'll be taking only its inductive effect, plus I, right? CX3 at para, minus H, right? CX3 at para, minus H, right? CX3 at meta, minus I, right? Now, which one is showing minus M? Nobody is showing minus M, so leave minus M aside. Which one is showing minus H? This is showing minus H, this is showing minus H. Now, which one shows more minus H? CBr3 as per series shows more minus H. So, 1, 2, 3, 4. 4 will be maximum acidic followed by 3, right? Then comes your minus I, right? Now 1 and 2, 1 and 2, 1 and 2. Minus I is gone. Now plus I plus H. This is plus I, this is plus H. So 2 at the end, it's going to be 1. Did you get this order? Let me see the chats. 3, 4, 5, 2, 1. 3, 4, 5, 2, 1. 4, 3, 5, 2, 1, right? CBr3 has got more minus H power than CCl3. The series which I gave you a few minutes back. The series which I gave you a few minutes back. The series which I gave you a few minutes back. Basic strength. KB order. Basic strength. Basic strength. Basic strength. Plus M will be given first priority. Then plus H. Then plus I. Then minus I. Then minus H. Then minus M. Right? This is your site. This is your basic site, right? This CH3, what is it going to operate? Plus H from para, right? CX3 minus H from para. From meta, plus I. From meta, minus I. Now, is there anyone showing plus M? No. Is there anyone showing plus H? Yes, this is showing plus H. So 1 will be maximum basic, followed by H is gone. Is there anyone showing plus I? Yes. So 3. So 3 is also over. Then minus I. Minus I is the fourth one. After minus I, minus H, that is the third one. That is the second one. Did you write this answer in the chats? People are writing 1, 3, 4, 2. 1, 3, 4, 2. Absolutely correct. Absolutely correct. Wonderful. Wonderful, guys. One last question of the session. And I think I should keep this as the homework. What do you say? Should I keep this as the homework or should I solve this? Arrange the following as per acidic strength. Acidic strength mein minus M dominates over minus H. Minus H dominates over minus I. Then you have got plus I. Then you have got plus H. Then you have got plus M. Right? Call this as 1. This is 2. This is 3. This is 4. This is 5. And this is 6. Quickly, give it a try. First you give it a try, then I'll solve. First, you are going to give it a try, then I'll solve. First, you are going to give it a try, then I'll solve. And the answer has to be correct, guys. Answer has to be correct, I'm telling you. Answer has to be correct. This is the last question of the session. And with this, our general organic chemistry will be done and dusted. Quickly, quickly, quickly. Quickly. First, you solve this question, tell me its answer, then we can talk. I want its answer, guys. I want its answer. I already gave you the series, right? Right? Quickly. Someone is saying our brain is not proceeding, yeah? See, guys, it's very simple. First of all, this is your acidic site from where hydrogen is going to leave as H positive. This is your acidic site from where hydrogen is going to leave as H positive, number one. Number two, this CH3 is present at the para position, so plus H. At the meta position, plus I, right? CX3 at para, so minus H. OCH3. This is OR basically. OR shows plus M. This is OCH3. OCH3 at meta. OCH3 at meta shows minus I because mesomeric does not operate, right? Nitro at para, it shows minus M. Now, can you prioritize it? First of all, is there anyone showing minus M? Yes, I can see there is one showing minus M. So 6 is maximum acidic. So this is gone. Is there anyone showing minus H? Look at all these. Yes, third one is showing minus H. Minus H is gone. Is there anyone showing minus I? Yes, there is one showing minus I. That's fifth, right? So minus I is over. Is there anyone showing plus I? Yes, second is showing plus I. So write second afterwards. After I, is there anyone showing plus H? Yes, I can see there is one showing plus H. So 1. After plus H, is there anyone showing plus M? Yes, there is fourth showing plus M. So did anyone write the order like this? 6, 3, 5, 2, 1, 4. 6, 3. 6, 3. Someone has written 6, 3, 4, 1, 5, 2. 6, 3, 4, 1, 5, 2. No, right? This is OCH3, right? This is plus M. Yeah? This is the actual order of this particular question, guys, right? And with this, our general organic chemistry is done and dusted, right? General organic chemistry is done and dusted. Right, people? Okay. Now, one thing is there. Guys. please and please do watch the same session again at 2x or 1.5x tomorrow. Okay? Do watch the same session at either 1.5x or 2x tomorrow. Otherwise, you are going to forget everything. Otherwise, you are going to forget everything. Right? It is 3:21 right now, by the way. This session needs to be watched again. Because the kind of questions which I've showed you, I deliberately came up with some questions which are tricky basically, which I don't think you would have solved in your earlier GOC classes. Okay? So I want you guys to remember them. I want you guys to remember them. Exactly. From 700 to 62 live watching. Do you see where the competition lies? This is the actual competition which I keep on telling you all the time. This is the actual competition. That is not the actual competition. That is just fake. Right? A PDF I will have to see. I don't know whether I'll be able to send you the PDF. Right? I think I need to sit for like 2 minutes. Yeah. And tomorrow at 11 a.m., what do we have? We have got extra question practice, right? At 11 a.m. tomorrow. Extra question practice is there. Extra question practice. Do attend that as well. So this was our day 13. Day 13, I mean night 13. It is over. So tomorrow there is one surprise. Tomorrow, matlab today, there is one surprise in the evening. Do join that session as well. Okay, do join that session. Someone is saying in half an hour, milkman will be there in our house. Is that? Is that? Yeah. Hmm. Yes, 10 a.m. Ambika ma'am has kept the special class. At 11, I have kept. So guys, are you like in any offline institution or you guys are doing the self study? Everyone is sleeping in my house too. You need not to worry. I'm the only one who is awake. All right. So majority are doing the self study. Perfect. Is anyone from you? I mean, is anyone among you from Chennai? Anyone among you from Chennai? Yes or no in the chats? Okay, a lot of people are from Chennai. So the ones who are from Chennai will be waiting you on 23rd of December, right? I hope you know the venue where to come. 23rd December, Saturday, 5 p.m. Yeah? Remember the date. No, it's not being jealous with Chennai people. It is just that we are starting the offline journey from Chennai. After Chennai, we'll come to like Andhra, etc., etc. Everywhere will come. We're starting from Chennai. So you guys are most welcome there. Chalo guys, I think it's time for you and me to sleep, take rest, right? Let's catch up tomorrow in the special class. Okay. Hello guys, you take care. God bless you all. See you tomorrow at 11 a.m. Yeah. God bless you. Take care. Take care. Take care.